Okay. As is the way with academic conferences, we're incredibly good at organizing things on the weekend and on national holidays. So today is Juneteenth. This marks the end of slavery in the United States and is a holiday that extends to tomorrow on Monday when there is a new national holiday. So we just want to mark this. New Orleans obviously is a city with significant history and has many celebrations to commemorate Juneteenth. So the CVPR organizers have arranged a webpage for you to go and see all of the things that are happening to mark this occasion. So please check that out for yourselves. Okay, some housekeeping rules. The remote audience will be muted during talks. We're going to try and keep to a schedule. More on that later. For the invited speakers, I'm going to give you a warning when you're getting up to your time. For the remote people, please post your questions on chat. For the in-person people, there's a microphone in front of the projector where you can ask questions at the end of talks, but please hold your questions until then. This is a recorded session, and this will be posted online later, so moderate as you will. For the in-person attendees, CVPR organizers have asked us to ask you not to join the Zoom link because the conference center needs bandwidth. Okay, thank you very much. All right, and then for the poster sessions, the workshop organizers are still slightly unsure where they are. So we'll keep you up to date. We may have to do some last minute emergency changes, but when we know, you will know. For the remote people, we're using Gatherly. The link is there, and I've sent all of the authors the link ahead of time, so you should be able to log in by now and get set up there. Okay, we had 56 submissions this year. 17 of them were already accepted to other venues, like this year's CVPR, and so they were automatically accepted. And then of the remaining 39 that were peer reviewed, we accepted 19 posters and then 3 oral papers. Okay. We have a best paper and a best paper runner-up award that I will announce now. And then we also have a best poster prize that will be announced after the workshop. We have 2 prizes, one for the physical posters and one for the virtual posters. All submissions are eligible for these prizes, and an awards committee will participate in both poster sessions, both physically and virtually, to assess this. Okay, so then on to the best papers. The best paper goes to Fix the Noise, Disentangling Source Features for Transfer Learning of Style GAN by Dongyang Lee, Jaeyoung Lee, Doyoung Kim, Jaeyoung Choi, and Jungmo Kim. So congratulations to that paper. A round of applause, please. And the prize is depending either a GPU or an equivalent amount of cash. Everybody likes cash, right? Okay, and our best paper runner-up is then Rick's a 2D self-occlusion map for harmonizing volumetric objects from Yunseok Chang, Ruben Villegas, Jimei Yang, Duyu Seilan, Shisun, and Honglak Lee. So another round of applause, please. We actually have physical certificates for you. So if the authors are around, please come and see Sanjan, and we will pass those to you. Okay, let's get on with the schedule. The schedule is online, aicc.net. Our first speaker, Michael, unfortunately couldn't be here. He had a change of plans. And so he has recorded a talk for us, and I will leave it to Sanjan to switch that over. So welcome, everybody, and let's get started.
Let's start a video from.
Okay, just a second, because you can't hear this. We know.
Let's see. Can you hear the voice?
Nobody, right?
No.
Why I think the most digital content contains you.
There's no other speaker outlet, right? That's the HDMI. Let's just drop that.
No, it's just.
It's basically why don't we get hard to give his talk. See what it's muted. Actually, can you give it?
This one, no, it's what is it?
Do it. Just it's muted. That's right.
No, it's not speaking.
That's not coming out of there. Yeah. Would you be allowed to give your talk? Would you be allowed to give your talk?
Sure. I mean, that's okay.
Let's switch the schedule around because we know people in the room cannot hear, and we'll see if we can fix the AV, and then we'll come back to Michael's talk.
Switch that. Sure. Switch the speakers.
Yes, it's just a speaker.
So can we switch the speaker back?
I switch it to E.
Where's the mic?
Okay.
Can you hear me? You good? This was fun, right? Okay, hello everyone. There's some feedback. Cool. How about now? Echo, echo, echo. We good? Yeah?
Good.
Yeah, we're good? Okay. Hi. Hello, everyone. Hello, everyone. Apologies for the technical difficulties. Let's start. Let's start. No worries. Should just
Go ahead.
okay. Okay. Cool. Okay. So welcome everyone. I'm Ohad Fried. I'm an assistant professor at Reichman University, and I want to try to talk to you today about the right amount of machine learning for content creation. And I'm going to do that via two recent projects that we had. So let's dive right in. First project I want to talk about is a blended diffusion. Okay, so I'm going to stop and I'm going to wait until it is resolved.
Go ahead.
Hello. If I mute this computer, will this help? Maybe you get an echo through the computer. You don't know?
Check, check. Good evening, ladies and gentlemen. Hey, how are you doing? Check, check, check. Does everyone hear me?
Okay.
That's good.
Okay. So let me go back. So I want to talk to you today about the right amount of machine learning for content creation, and I'm going to do that via two recent projects that we had. First project, blended diffusion for text-driven editing of natural images. This is with Omri that did all of the hard work, and with Danny Lishinsky from the Hebrew University. I'm assuming most of you know about diffusion models, right? Really cool. I'm showing you two recent examples, DALL-E 2 and Imagen. And diffusion models prove to be very good image synthesizers. They can create images from scratch, high fidelity images. For example, here, these are text-based, meaning you give a text prompt, for example, a teddy bear on a skateboard in Times Square, and you get an image of a teddy bear on a skateboard, kind of in Times Square. Right? Really impressive, same on the right for Imagen. These models mainly generate images from scratch. In this project, we wanted to edit specific regions of an image, right? So let's say we have an input image. I can draw a mask on the plate region, saying I want to just edit the plate, and give a text prompt saying pizza. And now the output is, there's a pizza on my plate. And this is the actual output from our method, okay? Here's another example. Let's say we have the Mona Lisa. We draw a mask on the head. We say neat beanie, and we get a neat beanie. And it's kind of in the style of the input image, right? That's important. Cool. So what are our goals? Let's reiterate. We want region-based text-driven editing. We want to operate on real and diverse images. What I mean by that, so diverse. Some methods only work on specific domains, like faces and like bedrooms. And when I say real, I mean that those are actual images and not, for example, the result of some other GAN-based model that generated the images. Okay, so you give me an image and I can edit it. Background preservation, the region outside. So can you hear me okay? Because I'm not sure, because I'm hearing echoes. Not so much. Does it help if I speak like that? People at the back, can you hear me? People at the back, can you? No, okay. You know what? I know that there are people back home, but if people hear this theory, okay. So let's do that. I apologize. I apologize for the people.
Hey, why if you speak in the mic and just turn down the loudspeaker? Then people can hear you and they hear you as well.
I don't care whichever setup works. I can do this.
Check, 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 check. I don't know what's wrong with that speaker. I'm sorry.
Okay.
You tell me what you prefer for me to do. Either
You
one.
just speak.
Yeah.
Please speak.
We'll just do that. Okay, okay. Cool. I like this better. Okay. Okay, so should I go back? Or no. So these are our goals. Interface testing, we want to operate on real diverse images. We want to preserve the background of the mask region should change and
text will stay as it is. We want to allow multiple results for the same input. And we also don't use models we want to require millions and millions of images of text and learn forest. Cool. So, one slide about diffusion models for those who don't know it. DDKM, denoising diffusion probabilistic models. Here's okay, so that's the trick, really elegant. As I said, at least at the beginning, this was about generating whole images from sketch. Our key idea in this project, and it's kind of inspired by Laplacian pyramids, for those who know what it is that we're going to treat each noise level as a different level of details, and we're going to somehow blend things over all these different levels. What do I mean by that? So, all right. Okay. So we're going to blend the noisy input, so that's outside the mask region, with some guided edge inside the mask region. More details the next slide. Okay. Just want for now to say that the blending, we're going to have a blending step and a diffusion step. The blending step is going to pass away from the manifold, but produce the edge, and then the diffusion step is going to back to the diffusion. So more details. This is our method. Start from input. Green flame, that's like text font in this case. You have an image, and you have the mathematics. Our goal is to create a flame at the top of the torch of the statue of the statue of Liberty. Now, given the image, it's really easy to apply noise in all these different places. Right? Lots of noise. It's easy. Just now we can do a step, I call it diffusion. So meaning doing that step of removing a bit of noise that I showed you in the previous slide with guidance. So we use clip embedding. For those who know clip, it's a space that somehow connects between text and images. So we are guiding the denoising process towards the prompt. So it's denoised, but also it's a bit more of a green film. Okay, in more details in the page. But all I need for you to understand right now is that you're doing denoising plus moving towards the text prompt. Now, these two images are the same level of noise. That's really important. Because now we can use the mask and just copy pixels, right? We are copying the mask region from here, and we are copying all the rest from here. Okay? So we're blending these two things. We moved away from the natural image manifold, but we have our edit, or at least we're closer to our edit. Now we do a diffusion step, and we come back to the natural image manifold with the appropriate level of noise. We do this process many times for all the diffusion steps, and then we get our output. In this case, we have a Statue of Liberty with a diffusion step. Okay, so this was kind of a bit of a hand-wavy explanation of what's going on. More details. Good. There are other minor details, like important details that make this work. For example, we use augmentation in order to avoid adversarial examples, and we do result ranking, meaning we actually produce many different results, and then we use automatically use the click embedding space to select the best results according to the. Okay, let's look at some results. So we can add objects. For example, here we have our mask. There's a dog there behind the mask. If the text prompt is completely empty, we remove the dog. example, are you touching? Because I'm losing focus every time. Sorry, like that. For example, here we do a really large mask, and now the entire background can be a big wall or New York City or an oasis or a festival, etc., etc. Good. As a reminder, we support multiple options. So if I want a rock, I don't get just one rock, I get many, many rocks, and I can pick. And also we support scribble-based editing, right? I'm not a good artist at all. I cannot draw a blanket. But what I can draw is a rough estimate of what I want the color and the shape of the blanket to be. And then I feed that to the model, and we get a somewhat realistic blanket. All the creases and shadows appear, but we still have the rough shape of what I specified at the point. Good. Because the inputs are real images and not some gun version result, whatever, we naturally support iterative editing. So the output of one editing step can be the input of the next step. For example, here we did an editing session, right? We start from the top left image. We draw a mask on the head region. We say curly blonde hair, we got curly blonde hair. Now that image is the input to the next edit. We want a shiny purple tie, we got a shiny purple tie. And that image is the input to the next. We added some scribbles, we want a floral jacket, we got a floral jacket according to the scribbles. Okay. Good. There are limitations, as always. For example, sometimes there's no sense of object scaling. Here we asked for grapes, but we got huge grapes. Okay. Another limitation, typographical bias. Here we asked for a rubber toy, and we just got the text rubber toy. That's very common for diffusion models. Diffusion models learn a lot about text. They're very good at producing. Another problem or limitation, let's say, is that the inference time is long, right? It takes about 30 seconds per image for this. And if you're producing multiple versions, that means you need to multiply that by the number of images that you are creating. Okay? How to solve that? One way is to do the blending diffusion in a latent space. We are working on that. I have more to say later on. Okay, so this was kind of like a brief intro to this work. This is actually a CVPR 2022 work. So if you want more details, please check out our poster at the Friday morning's poster session. We had comparisons and a user study and more results. The code is available. There's a website, so please check it out. Okay. So I promised you 2 projects today. Let's jump on to the second one. And the second project I want to talk about is endless loops, detecting and animating periodic patterns in still images. This is a work with the Lightrix, all these great people, and led by Tavit. And this was presented at SIGGRAPH 2021. What are cinema graphs? Okay, cinema graphs are something which is interesting. It's kind of in between images and videos, right? I'm showing you here a bunch of cinema graphs. You can see most of the frame is static, but there's an element which is moving in a looping way, in an interesting way. Our goal in this project is to create these cinema graphs from a single image. We want to do it in a way that every user can use it, okay? Specifically, we have an app, right? It's not just a research project and a paper, it's an actual app. We are really excited that many people are using it, hundreds of thousands of people. They're very excited about it. We got a bunch of rewards, so really cool. I'm going to show you a live capture of the app. So we have an image. You draw a mask on the region that you want to animate. It doesn't have to be accurate. You can draw it with your fingers. And then you add a direction, you hit play, and you get your cinema. Okay? We have some controls. For example, you can play around with the speed of the animation. So I can get these dots to move faster, slower, etc. So that's all gone. One option to create these cinema graphs is to start from an input video and then tone down the motion in all the regions that we want to keep static. That's too complex, right? You have to capture a very specific type of video. You need to have a tripod. You need to really control everything when you capture that video. And also, there's lots of manual work. drawing out masks and defining which region should be kept static and which should move, etc. So that's a no-go here. Another option is to use a single image as input and use a video data set for training, right? This is a great work from Belinsky et al. Basically, they had a data set of, for example, waterfalls, and the neural network learned how a waterfall behaves. So now I can give it an image of a static waterfall, and it creates a nice moving waterfall. The downside of this is that what if you want to create surreal motion, right? There's no image, video data set that contains the Colosseum moving. That doesn't happen in the real world. So you can't have training data for this sort of an application. And I apologize for the choppy video. This is going through Zoom. That's why it's choppy. It's supposed to be smooth. Cool. So let's reiterate our goals here. We want a single image as an input. We want to support both real and surreal results. We want a simple UI usable by everyone. And we want the runtime to be interactive. Real versus surreal, I already talked about. We can't rely on a video data set, or at least it's not trivial to rely on a video data set. In interactive runtime, we do that by splitting the algorithm into a 1D step and a 2D step, which I'm going to talk about in a second. Cool. So let's do an overview of the method. We start from the input. The input is an image, a mask, and a direction. 1D step, we estimate a repeating pattern in 1D. 2D step, we extend it to a 2D repeating pattern. Then we use that to warp the image in order to create the looping. Okay, so that's the general overview. Let's dive in a bit deeper. Here's the input photo, right? The 1D step says that let's take the mask, calculate a distance matrix. So for each column of this mask, we're calculating distances. And now we're going to use dynamic programming to find the shortest path within this distance matrix. And the path should be continuous and with a bounded slope. That translates to nice motion in terms of that we're not moving adjacent pixels to very different locations. And just this 1D step, and again, I know I'm kind of hand waving everything, more details in the paper, so this is kind of a brief intro. Once you do that, you already get kind of nice results for some inputs. Here I'm showing you a result of only the 1D step. Since the background here is a flat wall, it's fine, because we need motion which has the same angle and similar magnitudes. But what if we try to use the 1D step on something, let's say, like this? It's not that great. You can see on the edges, we have a bunch of artifacts. And the reason is that this is no longer a flat wall. This is a curved wall. We need to somehow capture that. We can't use just one direction of motion. Okay? So the output of the 2D step is going to give us this, which is much, much better. Okay? I'm not going to go into too much details about the 2D step. Just in one slide, we're using a CRF, a conditional random field, which is a way to assign these directions and angles to each of the pixels to create the warp field. What I do want to say is that the cost function for the CRF, or one part of the cost function, uses a perceptual patch similarity. Okay? Why is that important? Because that's the only deep neural network in this paper, and it's pre-trained. We didn't even train. We use it because we know that deep features of neural networks are very good at perceptual similarity between patches. Okay? Good. I'll come back to that point in a second. Let's just do a recap. So we have our input. We estimate 1D motion. We refine it to 2D motion. We use that to generate the looping output. We do support a few extensions. For example, what if the user draws a bunch of lines? That's fine. We take the mask, we split it into different regions, and then we go back to the procedure I just explained to you. Still works. We also support a video as input. Again, sorry for the choppy video. It's not choppy in the real world. By basically back projecting to a single object, we can get the object to move even though it's a video and not a static image. Okay. And let's look at a few more results. You notice that many of these contain very obvious textures and patterns, but not all of them. You see here, we also support somewhat circular motion. And here, it's very simple, right? You don't have a real data set for that. Movie, corn, etc., etc. We support buildings and natural phenomena such as waterfalls, alligators, smoke. There's plenty of examples. Good. Yes, that's what I'm watching.
Headphone.
What about runtime? So as I said, this is on a phone. We want it to be fast. It's fast. Here we're comparing to two other methods. I already briefly mentioned Olinsky or related methods. They take tens of seconds on a very powerful GPU. It takes 1 second on an iPhone. Good. There are challenges, as always. For example, if there are strong perspective distortions, doesn't always work. If the pattern changes throughout the mask, doesn't always work. Now I can fix that by drawing a bunch of arrows, not just one, but that requires more input from the. Good. Don't take my word for it, right? Try that. That's out there, now again. You can do it right now or later on. Play around with it. It's kind of fun. I'm here. I would like to get some feedback. Oh, is it scanning? I'll wait 1 more second. Okay. Come see me if you didn't get a chance to scan it. Now, we have, yeah, good. We have this project, and then a prominent YouTuber that talks about projects of vision and graphics. They contacted us. He wanted to highlight it on his channel. We were excited. We had a bunch of back and forth, and then we got this email. Dear Tavi Noad, I'm currently working on the episode. It appears to me that the technique is almost entirely handcrafted. It is a very impressive achievement, and I wanted to make note of that in the video. Right, so we got to the point that if you do something which is not neural networks, it's impressive or weird or exciting or whatever. It's kind of the reason why I want to do this, right, to highlight this point. So back to the original question. What's the right amount of machine learning for content creation? Today I showed you 2 projects, arguably successful projects. First one, heavier than machine learning. Everything is about diffusion models, heavy math, etc. There's nothing there which is not machine learning. Second one, just a bit, which is machine learning. And even that part, we could have probably used something else. Okay? So what is the right amount? If you're expecting an answer, so it will disappoint you, of course there's no answer, right? The answer is that it depends. It's complicated. So I'm not going to give you an answer today. I just wanted to raise the issue, cause you to think about the fact that maybe we shouldn't run to machine learning every time. It's an amazing tool. I love neural networks, right? They're awesome, but for 95% of the time, maybe not for 100% of the time, right? 100% neural networks is not always the best. And we need to think about that in all our roles, right? People here in the audience, some of us are researchers, authors, developers, managers, reviewers, that's really important, right? I'm one of those people that sometimes I have projects with no neural networks. There will always be a reviewer that says there are no neural networks, that equals the project is not good. So let's be mindful about the fact that there are other solutions, not just machine learning. So what are possible alternatives? I showed you a couple, right? Classical, quote unquote, classical methods are an alternative. A good UI is an alternative. Don't run towards complete automation all the time. Sometimes we want to give the user the option to decide. And that's pretty much it, right? So just as a reminder, I showed you 2 projects today. All these amazing people did a lot of work. I did just a bit. Hopefully, I made you think a bit about the role of machine learning in content creation. I want to thank you for listening. Sorry for the technical difficulties and the questions if you have any. Thank you.
So you mentioned that in the second project, perspective projection is like a trinity for animating repetitive tasks.
Yeah, let me go to the microphone. Okay.
I mean, in the second project, you mentioned that perspective projection is like a trinity. So So I was wondering if they would look at that, they could help you alleviate that. So have you ever considered that?
Right, definitely. So we actually, I kind of cheated here. I said that we can use a neural network. Of course we can. And we look at trying to use a neural network that learns from a data set in order to understand localized behavior. Right? So something like perspective behavior, doesn't matter what your object is, doesn't matter if you have a coliseum, you just want to understand how perspective works. So we try to take a network to alleviate that. It was a process, not because it can't work, just because we didn't push it. All right. That's a very good. Yeah.
Hi, super. I'm really glad that I have. Thank you for the great talk. When I see the images from diffusion models, it's amazing. It's always mind-blowing. And well, currently it's still 2D images, right? If we want to extend this idea or methods to higher dimensions, like 3D models, light transportation, motion, and stuff, what do you think is the most, what do you think is the biggest challenge here? Is it like a large data set or is it dimensionality?
Yeah, that's a great question. I would start by saying I have no idea, but I see it. So first of all, you need lots and lots and lots of data. For example, for the DALL-E 2 and Engine, etc., those are hundreds of millions of examples of paired images and text. Right? I don't know the equivalent 3D data, for example. So we either need that data or we need a way to synthetically generate the data. I'm not sure. Once we have the data, I personally think that the models should be able to render 3D also, but that's a complete guess. Right? It's one of those things that we have to try and then see what's going on and how it breaks, etc. So, but that's all I have.
All right, let's leave it there. Yeah. Let's thank Ohad again. Jane, do you want to take over from here?
Sure. Okay. Yeah, it's my personal great honor to introduce my PhD advisor, Michael Black, which I don't think need introduction in the room, but I would like to say something very personal. I would like to take this as an opportunity to thank Michael for his mentorship and advice in the past. So what I feel most inspired and encouraged is Michael's courage to always pursue new ideas and new domains. And so let's see what Michael has to say about digital avatar for content creation.
Volume.
Thanks, Sachin. Can you guys hear me?
Yes.
All right, and I'm going to, let's see if the technical difficulties are behind us. Hang on a second. Can you see my screen? You see the right thing?
Yes.
Super. All right, stop me if something goes wrong and you can't hear me. Otherwise, I'll just keep going. Yeah, so Deching, thank you very much. You're always too kind, which is a wonderful property. And it's my real pleasure to be here at this workshop. I'm sorry I'm not there in person in New Orleans. I would have loved to have been. But I want to tell you a little bit about some work going on in my department in Tübingen. And I repeat quite often that the age of avatars is coming, and it's coming to content creation. So I want to walk you through what I think that means. And I think the most important digital content contains humans. That's what we care about. We're interested in each other. We're interested in ourselves. Humans are what drive our emotions, our passions. But it's unfortunate that the most difficult digital content also contains humans. And we've seen a lot of progress in the last few years on creating synthetic faces, and it's improving for creating 2D images of full bodies and doing virtual try-on and things like that. But I'm going to argue that we need to do this in 3D for many applications, and that's where it gets really tricky. So I really believe that digital human content is going to proliferate, and the avatar, which I'll define for you in a bit, is a key enabler of the metaverse that everybody's talking about. Now, by avatar, people mean all kinds of things from cartoon Roblox characters to photorealistic renderings, or like something like metahuman models. But it's going to mean all of those things. People are going to have multiple avatars. They'll have physically realistic ones that they use for their shopping and digital fashion and their fitness and health. Of course, we want realistic ones for training AI systems. We'll probably want physically realistic ones for augmented reality as well, because we're going to want to try on different clothes or see people with things on them. And characters have to come out of the virtual world into our physical space. And so avatars are going to proliferate across all of these different applications through multiple vertical markets, and they're going to have a big impact on our lives. But there's a lot of challenges to getting there, and I'm going to focus on two in this talk. One is about making it easy to create realistic people in varied clothing that they can be animated realistically. Today, this is still a labor-intensive process. And then putting them into scenes automatically, doing the things that people do naturally. This is even a more challenging process. Now, of course, you can go out today and buy good-looking 3D characters like these ones from Render People, and you can even buy 4D characters, that is, ones that have built-in animation. They're not smart. They don't do anything other than, they're just captured scans, but they look pretty good. And of course, you can also go out and get lots of realistic 3D scenes with nice material properties, and you can render them beautifully, and you can do it in real time and all of that. But this is the thing that's a problem, and where you see a lot of rendered scenes with no people in them, and you see a lot of people not in scenes. And when you see them together, some human has done a lot of work to place the people in the scenes. How do we automate this so that automatically we can have scenes populated by people doing things that might make sense in that scene and with each other, right? And the approach that, this is really something that my group spends a lot of time thinking about, and we do it using computer vision, machine learning, virtual humans or avatars, and computer graphics. And we use computer vision to capture humans in videos and other data sources to capture their movement. We use machine learning to model how they behave and how they interact with each other in the world. We use that to create avatars that have the ability to move and act. We use computer graphics, both modern and old-fashioned, to synthesize images and videos. And then we use that to train more computer vision algorithms in a virtual flywheel. Okay, so that sounds maybe sensible to you. So why is it so darn hard? Well, people are pretty complex. We come in a wide variety of body shapes. We wear clothing that we layer on in all kinds of ways. We have glasses and headphones and all kinds of other stuff we attach to our bodies. We move in complex ways. We communicate through gesture. We communicate through facial expressions about our emotions. But we communicate with each other in complicated ways. I'm just picking up an echo now, which wasn't there a moment ago. So somebody unmuted recently. If you could just mute again, that would be great. Thanks. We contact our bodies regularly throughout the day. We're always touching our faces and so on. This creates all kinds of problems for modeling humans and their behavior. We interact with objects, not just with our hands, but with our full bodies. And then we interact with each other. We touch each other, we shake hands, we hug, we kiss. All of these things, modeling all of this is necessary to create avatars that behave realistically, emote realistically, and that we can really identify with. So what's an avatar? Our foundation is a 3D virtual human. It's a simple mathematical model of body shape. It should look like a real person. It should move like a real person. It should be compatible with existing graphics tools. if we want to use it today. And it should be able to interact with people in scenes. Now, to interact with scenes, it needs to have a 3D shape, a surface that can touch and not be interpenetrated or not interpenetrate. And it has to have the ability to emote and gesture. And should also be able to wear clothing. Here I'm showing you minimally clothed avatars, but we'll talk about clothing in a bit. So several years ago, we created, we've made many body models over the years. We created Simple in 2015. Simple stands for Skinned Multi-Person Linear Model. And the idea is it's a function, M, which takes pose and shape parameters, theta and beta, and it returns vertices. Now, the trick to Simple was just to design it around something that already worked really well, but required manual labor, and then get rid of the manual labor by having a lot of training data. So what we chose was linear blend skinning, which is the simplest thing that's used in graphics to animate characters. But we pulled out all the guts and we replaced it by things that we could learn. So for example, there's a template mesh that is a function of the shape and pose of the person. That's really critical. The joints of the person are a function of their body shape, and the weights and other parameters of this model are all learned from a data set of 3D scans of people of varying body shapes and in varying poses. So we ended up with something that's actually very accurate, but is also compatible with graphics packages and is simple to use, which is probably why it's become relatively popular. So, but that's not enough. The body alone is not what we need to create interesting content. We need to be able to put that body into scenes. And to do so, we need to know, what do people do in scenes? How do they interact with scenes? How do they support themselves, et cetera? So we captured 21 people interacting with a wide variety of scenes with an RGBD sensor. We also scanned those scenes. We have 12 scenes that we scanned at Max Planck, and then we also used the PyGraphs data set. And this work is a PROX data set that was published at ICCD in 2019. And this shows you an example of a scene on the right, a 3D scan, and the person interacting with it. There's a long video, so I'll just jump around. There's people touching things like desks and chairs and putting their hands on things. The motions are not perfect, they're a little bit jittery, but there's all kinds of motions. People do all kinds of things, interacting with furniture, and so on. So this kind of data set gives us the training data we need to begin to think about how do people interact with 3D scenes. And from this, we could compute the contacts between the surface of the body and the world. Okay, here at CVPR, we have a new data set. It's called Rich, and Rich goes beyond PROX. It's much more accurate. It uses a multi-camera markerless mocap system. There's also a moving camera, and that's at poster session 3.1 on the 23rd. And what you see here are simple bodies. It's actually simple X, which is expressive. It has hands and feet, and the bodies are interacting with the scene. We have 3D scans, very, very detailed scans. Some of these they're 60 meter squared scenes in terms of area. And we use a very high quality scanner. And using that, we can get contact with the scene. And so here, the meshes at the bottom, the green bits are all the parts of the body that are in contact. RICH stands for real scenes, interaction, contact, and humans. There's a wide variety of subjects. There's multiple people in the scene interacting, and it's all captured in 4K. And you see some of the moving cameras here, as well as the static cameras. So this data set's available, and I think it goes beyond existing data sets in terms of ground truth quality and the richness of the interactions with the world. And this is just an example of some of the 3D scenes here. So that's the rich data set. We don't use that in the rest of the work I'm talking about because it's just new. We're going to use the PROX data set and come back to this question of how do we take scans of people like this, high quality scans, and put them in a scene like this automatically. And our idea, this is from a work from last CVPR called POSA, was to use a new kind of body human-centered representation of human scene contact. So we represent how a person interacts with the world on the body itself. So here on the left, you see in blue regions that are in contact with the environment, and on the right, the semantic labels. The feet are on the floor, the behind is on the sofa, the hand is on the table, for example. And we get all this data from procs. We have lots of examples of this. And then we train a conditional VAE to represent this. So we have vertices of the body, the X, Y, Zs here. We have the contact binary labels, and we have the semantics. And we encode this into a latent space, Z here, and then conditioned on the body. So if you give me a body with particular pose, I can sample a Z, and I can and then decode that to get the contact and semantic labels. And so that's what you're seeing here. You input is a posed body, and the output is a sample, an example of contact and the kinds of semantics. Here's someone sitting on a chair, touching the table again. This one's sitting on a bed. And I can sample Z multiple times, and I'll get different semantics. So with this, I've got a approach we can take now. So you give us a body mesh like the one on the left. We fit a simple X body model to it. In fact, we do take that from the Agora data set, because Agora comes with simple X fits to render people and other 3D human data scans. And so then we have a posed body. Once we run that through POSA, we get possible contact maps and semantics. And then given a 3D scene, we have a search problem. We want to look for places in the scene where that contact relationship could hold. And then we want to optimize the pose of the body, or the 3D rotation translation of the body, to match that, to satisfy that. And then once we have the body in the scene, we swap out the body for the original mesh. And so given a 3D scene like this, we can render it, we can put simple bodies into it, and then swap them out for the 3D meshes from Render People or other commercial scans. Okay, I don't know why the woman in the hat is like exploring the wall and so on. The people are all put in there completely independently. They're not interacting with each other, but that would be an obvious, really exciting next step to have them interact. Here's just another example of a scene with people placed automatically. Here's a case that I consider an interesting failure. You know, this woman is holding a knife and fork. Our data set doesn't know anything about knives and forks, and that they're usually used around things like plates and not laptops. So a richer semantic labeling of the world would be necessary to push this further. But that's not the only problem. Putting static people in the scene makes a nice picture. It could be useful for architectural renderings, but really people move in scenes, and we want to synthesize realistic human motion. Most of the work on synthesizing human motions just focuses on the mocap piece itself and ignores the interaction with the scene. There's obviously some nice work, particularly Sebastian Starker's work, that tries to address this. But there's still a lot to be done. And so at ICCV last year, we proposed this method SAMP that has basically three pieces: a goal network, a path planning approach, and then a motion network. And I'll just walk you very briefly through that. The motion network just generates human motions in an autoregressive style by conditioning on past motions and on the environment. So it needs to know something, an encoding of the environment, as we'll see in a minute. And then it autoregressively generates the next motions. To train that, we need a bunch of training data. We capture some in our mocap lab, but we need to enrich it so we have a lot more. So we capture people doing various motions like sitting or lying on an object, and then we change the objects out synthetically. So we have many of them of different heights and sizes and so on. We maintain the contact relationships and use inverse kinematics to adjust the body. So now we get lots more bodies, a much richer set, interacting with all kinds of objects. And in this way, the motion network learns to generalize to a wide category of objects. So here's just examples of somebody in a very simple scene now. The task is known, the goal is known. It just generates a motion like lying on the sofa, and it can generalize to sofas it's never seen before, or chairs, or whatever. So that's the motion piece. But given a new scene, you have to figure out what it is you've got to do in that scene. So that's where GoalNet comes in, and it tries to infer the affordances of an object. What can I do with this object? Where can I sit on it, for example? It takes in a voxel representation of the object, and there's a conditional variational autoencoder that learns to predict goal positions and directions on the object. And by directions, I mean these arrows here. So here's the sofa, another sofa. The circles are where you could sit, and the arrows are the orientation at which you would sit. So on a chair with a high back, you sit only facing, you could sit in 3 directions, and a chair that with high arms, you can only sit facing in 1 direction. And again, we synthetically augment the data set, so we have lots of training examples. And then given a new object like this, the network predicts where you can sit and the orientation of your body when you're sitting. You're sitting on a view of a table from above, you can sit in any orientation. Here's a chair, of course, you can sit in 3, and this chair, you can only sit in 1 orientation. Okay. So given that and the motion network, you put those 2 together, and then given a new object, GoalNet predicts places to sit and orientations to sit. Here we're just sampling 2 locations, and then MotionNet generates an appropriate motion from a starting point to the goal location. Okay. We need one more piece, which is the motion planning. And here we compute free space, and we use an A-star or path planning algorithm to get close to the goal. And once you're close to the goal, the motion network takes you through to complete the task. Now, if you don't do this kind of path planning, of course, it doesn't work very well. So you turn that off, and then you just walk right through objects. And I mentioned Sebastian Starka's excellent work. We tried that as well, and it tends to ignore objects that it hasn't learned about. So you really need this kind of path planning. And then you put it all together in a novel scene that the agent's never seen before. It walks through the scene. It actually moves its head in a pretty realistic way. And its task is to sit on the sofa. GoalNet figures out where to sit, and then it sits down. And despite the fact that it's been successful, it looks somewhat depressed. The emotional state is not being not one of the goals here. Okay, so that is a step. It's not fully realistic yet. Notice the avatar is a little bit simplified, but we're beginning to get there in terms of putting together more complex motions. Now, there is a piece missing, however, and that's interaction with objects. So here the objects were big things like sofas, but many things like cameras and apples we pick up and manipulate. So this manipulation problem is something we address in a paper called Goal, which is in poster session 3.1 on the 23rd in the morning. So I encourage you to check out Goal. What we do here is we, given a novel object that the network hasn't seen before, a novel body shape and a starting pose, the network generates a motion that takes the body from the starting pose to the object, orients the head properly, moves the arm out, and makes a grasp of the object. Now, in previous work, people have looked at the grasping problem. Just given an object, how could you possibly grasp it? Lots of people have looked at the motion generation problem, but putting these 2 things together turns out to be really hard. You have to satisfy all kinds of constraints. The feet have to move properly on the ground and not slide. You have to get to the goal in the right number of steps. You have to reach out and grasp it. And then you have to do fine motor control to really grasp the object. So to do that, we rely on a training data set called GRAB, which is something that we published previously. And this is a really nice, high quality motion capture data set, which is, in addition to capturing the full body, including the fingers, we capture the objects, and you can see in red on the objects is the contact regions where the fingers have touched them. So we have a lot of information about how people interact with objects. And we use that to train this, to train goal. And the first piece is GNet. GNet takes some conditions, which is the state of the environment, including the object, and it learns to predict body poses that are appropriate for those conditions. So it predicts the pose of the simple X body model. That's the top picture under outputs. That turns out to be a hard problem, to predict the whole pose of the body, including the fingers, such that it perfectly contacts the object. And you're predicting joint rotations, and the whole thing is actually a little bit hard. So one of the key novelties of this paper is to introduce auxiliary interaction features. So in addition to predicting the pose of the body, we predict the displacements from the vertices of the body to the object in the goal position. Okay, so some will be in contact, they'll have zero displacement, others will be further away. These live in a Euclidean space and are easy for the network to predict. And we also predict a head direction vector because that's critical for orienting the head. And the network has an easier job predicting these interaction features than the joint angles. And so we then run an optimization step starting from the output joint angles to satisfy the interaction features. And this really improves the results. On the left is the prediction before that optimization step, and the hand is in roughly the right place, but it's not really grasping the apple or whatever, yeah, the apple here. But after optimization, the posture is much better. Okay. Then MNet, again, is an autoregressive model. It takes the past 5 frames and the goal frame and predicts the next frames. It iterates doing that until it gets close to the goal. And then there's an optimization that takes it, the pose through to the final generated goal pose. So here's some results. Goal, starting in a T pose, the body moves forward, grasps the object. Here's just with a little bit of texture on it. It's not perfect. I think there's still work to do in this space, but we're moving in the right direction, I think, of being able to grasp it. Now, of course, we want the character to manipulate it and be able to do things with it. And so we've still got a lot of work ahead to make really realistic 3D content. And that's not the only problem we have. Here I've been talking about the simple X body model in the middle here, but it lacks all this detail like hair and clothing, shoes, all this personal stuff. So we really need a much richer visual representation. And so I want to point you to another paper here at the conference on the 24th in poster session 4.2 in the afternoon. It's called GDNA. And I believe it's the first generative model of 3D clothed people. So we've seen a lot of work on using implicit surfaces and neural networks to model the shape of people in clothing. This method goes a little bit beyond that to provide a generative model that we can sample from, and samples give new people with new shapes, with new kinds of clothing. And behind this is also simple parameters so that the bodies are parameterized in terms of pose, and we can also vary their shape. So I'm not going to go into details here, just say that we're making progress on moving beyond these very simple bodies to something more. One more, I'm almost done. If I'm out of time to change, just say so.
Yeah, I think, could you please finish in 1 minute?
Oh, I'll finish in 5 minutes, no problem.
1 minute,
here's
1 minute.
1 minute, no problem. Okay, so here's another paper I want to point you to called I Am Avatar. It's an oral on the 23rd. And this is one of the authors, Otmar, and this is his avatar. It's created just from a video sequence. I'll skip how we do that. I'll point you to one other paper. Sorry, I'm having a little lag here with my computer. I don't know what's going on. As soon as I try to rush, it slows down on me. So icon, the last one I'll tell you about is icon. The goal here is to go from a single image of someone in any pose, in any clothing, to create a 3D representation of that person. That's a poster on the 23rd. And I'll have to skip exactly what we do there, but we could take a wide variety of images like this and construct avatars of these people. And they're not perfect, but we're going in the right direction. So let me just summarize where we're headed. 3D avatars from images are definitely coming. Implicit surfaces, neural rendering, radiance fields, et cetera, are all progressing and really driving this field very quickly. But putting those kinds of avatars into scenes with realistic behaviors, high-level goals, all of this remains super challenging, and getting training data for that is really hard. There's lots of training data of images, but what's going on with people and their interactions with the 3D world, this remains really limited. So there are other kinds of methods, reinforcement learning-based methods and so on that need to be explored here. And I will just end with one thing, since this is a talk about the age of avatars. I won't finish my talk. I'll let my avatar finish my talk for me.
Get your avatar today. Here it is. I am Avatar. The best avatar out there, easy to make, easy to create, easy to control. It's you, only better, because you don't have to be there. So get your I am Avatar and get it now.
So maybe some future CVPR, I won't even give this talk. I'll just let my avatar do it for me. Thanks for listening. I'm happy to take questions if there's time to change.
One quick question for Michael while we switch.
Mm-hmm. Is there a question? I'm not hearing anything. So
okay, I'll ask you a quick question. How long until we're done? Like, how long until we can really use these things?
Yeah, it's a great question. Until they're visually appealing and could be puppeteered, it's just a few years. Until they really are autonomous and have goals, well, that's an AI complete problem. So imagine I have a 3D scene and I put an avatar in it and I just leave it there. Like, it should do what a human would do. But to do what a human would do, it would really have to have a bunch of desires and goals, and it should want a cup of coffee, and so it would go make it. I mean, I don't know what it would do, but I think that's really a general intelligence problem, and we're quite a ways from solving that.
Great. Thank you very much, Michael.
You're welcome.
All right, let's thank Michael again. Okay, we're now going to switch to Björn Almer. Björn is a full professor at Ludwig Maximilian University in München and Munich in Germany, where he leads the machine vision and learning group. He got his PhD from ETH, where his thesis won the ETH medal. He postdoc with Chandra Malik, and much of his work covers image and video understanding, especially generative methods. I'm very pleased that we have Björn here because he's been a big supporter of the workshop. In fact, in the past 2 years, his lab won best paper, both in 2020 and in 2021. So he fits in right at home here. With that, please take it away, Björn. Thank you.
Can you hear me all right? Yeah, okay. Okay, good. I hope camera and so on is also working. And great to be here at a physical CVPR again. Great to have made it through the lines. Closer? Yeah. Is that loud enough? Is that better? No, not. Should I do it without again? No. Is that better? Not yet? Closer. Closer? Okay. Okay. That one? Good. All right. So rather than, okay, good. Yeah, perfect. So rather than just giving you like an advertisement of the last 10 papers or so, I thought I'd do it a little bit different this time to give you something for your very own research and talk a bit about the recent great progress that there has been in powerful generative models, in particular autoregressive models, transformers, and diffusion models. talk about the very particular limitations that these methods actually have, and essentially what you should and should not be using them for, and then discuss two solutions, yeah, to get the best out of these models for the very problems that we're looking at, and some unpublished work. So I guess we're here all because we want to create content, for most of us that is visual content. And that essentially means drawing some images here or drawing some videos from the set of all images and videos that are out there. But wait, right? I mean, it's not all images and videos that we're interested in. We are probably interested in what's on the right, but not so much this noisy pattern that's there on the left. And that's where things get tricky, right? What is meaningful content for you? In preparation for this talk, I saw that there's an entire sub-community on the internet interested in JPEG artifacts and artifacts on SD card that you can create. And if you move it further, there's this iconic black square painting by Malevich. So the tricky question is really, what is meaningful content for you, right? And that means if we can't define it, we need to learn it. Learn it means we need to learn the distribution of all the meaningful images, for you, which evidently changes depending on the setting. And in addition to that, you don't just want to draw meaningful images up, you also want to have control in that process. So you want to guide your synthesis process by means of some semantic segmentation that you have provided, maybe style transfer in painting questions and the like. So generative models have made huge progress. We evidently want to have great quality of the samples that we are producing. Best thing that first of all comes to mind are generative adversarial networks, high quality, super fast, but as we all know, they're prone to mode collapse, tricky to train, they're unstable there. And the reason for that is evidently that they're concentrating, like homing in on part of the distribution, doing the best that they can do there, but with that losing data coverage. So answer to data coverage would evidently be variational autoencoders, a likelihood model which gives you the explicit density and is super fast, but it only provides you with a lower bound on the density, and therefore we do have a trade-off between what we have on the left and what we have on the right, between sample quality and data coverage. Can we do better? Well, answer yes. And that's eventually the modern models that we all know about and come to love. Autoregressive models, which have this autoregressive factorization of the density. Exact likelihood model, great, yeah, so no trade-off there anymore. Data coverage and quality all secured. And because there are exact likelihood models, you can also directly compare between different models. But we have first this unnatural ordering, right? I mean, reading images like you would read text, not too good if there's a tiger hiding in the bottom right corner, right? And secondly, no Latin variable, I mean, super slow if you always need to sort of parse through the sequence. And then the other model are evidently diffusion-based models. We've seen them this morning already. Score-based models, so you're working on the gradient of your likelihood function, not gradient with respect to parameters, but with respect to the samples, a little bit like the deep dream sense. And they provide you with a lot of flexibility regarding the architecture. So you can actually even utilize them with transformers, with GANs, UNets, and you name it. They these days provide the state of the art when it comes down to image synthesis. So if anything wants to sort of convince you there, I mean, one title was diffusion models beat GANs. I guess that says everything. And we do have, I believe, several talks today from other sort of companies, other speakers who have been using diffusion models for the state of the art that's out there. So great results. And in addition to that, stable training, this adversarial problem is eventually gone. We do have a Latin variable that we can sample from and efficient convolutional backbone, but they're expensive, right? They're expensive because we have a lengthy Markov chain. So let's look at that in a tiny bit more detail. We're starting with an image and then applying noise to this image a lot of times until the content is eventually gone. So essentially we did content destruction. Maybe that might be a title for a follow-up version of this workshop. kind of interesting one. And we evidently do this for a purpose, as you know. We turn this process around, have then a denoising autoencoder, which tries to learn to make up for this noise, to reconstruct the original image step by step in this process, reconstructed. And amongst the many things that make this really work, I want to highlight one key point there, which I believe is really a driving force, and that is that we do have the same denoising autoencoder at all the different noise levels that are there in the image, and all of them working at the same resolution. So as opposed to progressive growing of GAN architectures or something like that, hierarchical models, we're working at the same scale, but we're working at different levels of content granularity by adding more noise to the images. And that means that rather than getting a blurry and blurrier hierarchy of representations, we are getting a semantically coarser and coarser hierarchy. So here's a snapshot from Europe's publication that we had last year, where you see this, what I mean. So rather than the images getting blurrier towards the right, they're just losing content, but they're all staying as sharp as the original image that you see on your left. So what are the challenges that we now need to tackle? Autoregressive models and diffusion models have this great mode coverage, but this strength actually becomes also key for a key limitation that they actually show. And with that, I mean that they get lost in imperceptible details. They try to describe each bit and piece of the likelihood function that we have there. And with that, they lose track they lose track of the big semantics that we actually would want to have. So if you look at really like where all the bits go, then you observe that most of the bits are devoted to imperceptible details that you have there. And only very few are used to encode really true semantics. If you look at the images which you see at the bottom there, then only few bits encode, for instance, this difference between gender that you have on the left, and most bits are on the right for things that we cannot even see what's going on. So what we have done in essence is learn a very fancy kind of JPEG compressor dealing with all of these imperceptible details, but most of the training signal is not where we actually would want to have it, on semantic sort of features and characteristics in this scene. So where should we go? I guess the main trend these days is on just scaling up the architecture, the models, and the compute that we have behind that. Just look at DALL-E 1 there, 12 billion parameters. That's a wobbling number. But if we look at the data distribution, it's actually heavy-tailed, meaning there are lots of images out to the right where each individual image is an individual artifact. And there are no two Da Vinci's or Mona Lisa's or whatever else, right? Each of them is a separate sort of entity. And if you would want to take care of them just by means of scaling up, you eventually are in an exponential problem, if you can follow me. I mean, that becomes eventually exponentially harder to deal with each of them out there. And that means that we do have an enormous cost in terms of money, but also in terms of the carbon footprint and so on. If you just look at the latest and greatest in models, I mean, the numbers are not really like published, but what you see on the internet, talking about like hundreds of thousands of GPU hours, GPT-3, like millions of dollars just going into training these models. Implications are clear. There are few key players out there that do have the necessary resources. And well, I mean, with that comes evidently less of a diversity and less of creativity if we just sort of continue that in the future. We do have monopolies on other commodities as well, which typically is a reason for concern. But here I just want to highlight that this domain is a bit special, a bit particular, in the sense that already a single synthesized image or video, as we've recently seen in politics, can really tip the balance. And if you imagine that you just have few key players out there who would in the future hold it in their hands and maybe don't sign that they don't want to be evil, then you could imagine where things could potentially go. So how could we democratize research in visual synthesis? How could we make sure that we render smaller architectures more effective, so that it's essentially like you say with a camera. Yeah, the best camera is the one that you do and that you are able to take with you. How can we make this possible for generative models as well? Well, we've seen that these powerful models are expressive models of long-range content, long-range context, but they are very expensive when it comes down to local details. Yeah, transformers typically quadratic complexity. There have been ways to deal with that, but still. And with the diffusion models, most of the training, as you can see here on the x-axis, are the different iterations of your denoising process. Most of the iterations are on negligible semantical details. I should say that transformers, diffusion models bring with them the way to implicitly undersample this part of your distribution, but still we would waste most of our diffusion steps essentially on not learning semantics. Yeah, at the best you would then learn nothing, and why should you spend so much computational power on essentially doing nothing? So how can we do it more effectively? Well, we could combine this with the power with something which is kind of exactly on the other end, and that would be convolutional networks. They offer us very effective inductive biases, but at the same time can only model local interactions. And I hope that you see that this nicely complements what we have here at the top. So the idea is eventually to combine their strengths. And that leads to a two-stage approach, which we also have here with CVPR, a two-stage approach where you start with your diffusion model. At the top, like you add noise to the image, and then at the bottom, you have the encoder. So you need to read it from the right to the left. You have the encoder and then the decoder, and repeat this lots of times to make up for this noise that's being added. But rather than doing that in the pixel space and learning this fancy JPEG compressor, we add another autoencoder beforehand that moves from the pixels over to some space which is then semantically more accessible. We back then coined that VQ-GAN. So this approach takes the encoder output, quantizes that, like VQ-VAE, for instance, did. But here, in addition to that, adds a perceptual loss in the pixel domain and an adversarial loss to favor realism over a perfect reconstruction. And if you then, for instance, would add a transformer to make sure that these individual sites are contextually linked together, then you get this VQ-GAN approach with the transformer. Here just one slide example of the results. So DALI, which came out, I believe, like 2 weeks after this VQ-GAN approach compared to VQ-GAN. And you see that our approach there has like 4 times higher compression. That on a transformer model means a wobbling 16 times computational gain over the model. And I believe, like on the top row, you can easily see that the visual quality in that case is not diminished. Now, back to diffusion models. We can now utilize the same encoding architecture there, but in addition to that, the diffusion model allows us to add arbitrary conditioning. So you take these arbitrary conditioning signals and simply concatenate them through cross-attention with your UNet type autoencoder approach to do the denoising. And this simple sort of concatenation approach gives you a very versatile mechanism to make this model generically applicable to a wide range of guided and unguided synthesis tasks. I can here only highlight a few. You can utilize semantic segmentation, for instance, to render these images and many more images in very high resolution. We've been applying this on conditional single class labels from ImageNet, where it achieves the state of the art in FID when combined with a classifier-free guidance here compared to the ADM model. This condition, this simple concatenation of condition information allows also to train latent diffusion models for inpainting. So you simply concatenate the mask with a masked image and the noisy representation, and then the image synthesizes what you see on the right-hand side. And this works well, both qualitatively and quantitatively. It actually achieves the state of the art in terms of FID. Here's some more examples for text-to-image synthesis. I need to be a bit quick here. So trained on the Lion data set, and you can train this model on very small res images and then upsample that to resolutions that you did not have in your training data. But there was one thing that I actually wanted to now discuss with you, going beyond what we have so far. So far, we've seen how these models can learn representations more effectively. But the real question should be, what should we learn at all? Yeah. If you look at a famous painter like Monet, he was always out in the wild and he was always looking at reality. Why is that the case, right? I mean, isn't it like Ronald Reagan to his shame once said, a tree is a tree, how many more do you need to look at? Yeah, why did Monet need to always look at all of these objects out there and could not, like our models these days, just paint them from his head, yeah, and paint a flower after he has seen millions of them? And why do we, in contrast to that, just like squeeze like millions of training images into these models and force them into these parameters? Is there something wrong with us, or was there something wrong with Monet? And I believe like this is a paradigm shift, a little bit like Back to the Future. If you look at this 20-year-old work from Ayosha's group, for instance, from Ayosha when he was still a PhD student, and that's driven by evidently the latest work which you see at the bottom in natural language processing. So the idea is don't represent local details in a generative model. Rather, utilize a data set where you can just crop patches from, and then look up the relevant patches that you need for your particular synthesis task directly, like Monet did. Yeah, look at out in the reality and then kind of learn to more effectively paste that in. This is in our case a disjoint set, does not need to be the training data set disjoint of random patches, in that case 20 million patches cropped from 9 million images. And the autoregressive models or diffusion models can, in that case, just concentrate on learning a meaningful composition of these patches to make up the novel scene and doesn't have to learn it. Now, I want to wrap this thing there up. So we take the training samples that we do have, stuff them into a diffusion model or autoregressive model and want to reconstruct the images. But now we have a conditional synthesis task where you add this additional data set separate from the training database that these images here came from, and essentially learn to synthesize by conditioning on this extra drawn nearest neighbors. During inference time, you can now utilize different data sets, and that's the kicker here. Yeah, you can swap these data sets. You don't need access to the training data, and you can easily swap these data sets and replace them by a different data set that comes to your mind. And the benefit of that is that you can easily take a model that has been trained, just swap the data set at the top, don't retrain the model, and then apply it to a different scenario. In addition to that, as a brief take-home message, this kind of retrieval augmented models work best, apparently, if you look at the paper, when you have transfer tasks on very difficult data sets. And that kind of makes sense, right? I mean, then it makes sense to look out and grasp new patches if you're really looking at a difficult problem. So this is why I just said retrieval augmentation. If I train here at the bottom on ImageNet, and then during test times, not retraining the model, just swap the data set for WikiArt, then I get style transfer. So this is style transfer without any training, just swapping the data set. You get your typical zero-shot text-to-image synthesis of happy vegetables or happy tigers out there. And the model is more efficient than models without the augmentation. So here, all those same performance as ADM, an order of magnitude faster. There's a bunch of numbers which you can figure out in the paper and ablations as well. And so I want to conclude, make James happy. Don't waste powerful autoregressive models and diffusion models on perceptual compression. Rather, utilize latent approaches that efficiently combine the efficiency of convolutions for modeling local details with the complexity of these powerful GMs for modeling semantic content. And second, don't learn individual samples, rather learn to combine these samples in a meaningful manner. And that led to retrieval augmentation, smaller models, more efficient models, improved performance, because the model can now focus on the composition of the scene rather than capturing these details. And, which I find very interesting, a convenient way to post hoc transfer an already trained model to novel domains that it hasn't been trained on. So if you want to talk to the authors about part of the models, we will have an oral on Thursday in the morning session, and come to us afterwards, or if you have any questions, feel free to ask me now. Thank you for your attention. Any questions?
Clarification question about your, you mentioned long tail, right? You're saying like these long tails, you have one example of the model. And now we have seen from DALI 2, right, that let the model complete Mona Lisa, let's say the bottom up, and it actually does a pretty considered job. To try to understand what you mean by the model, long tail.
So, the Mona Lisa, evidently there in the model, right? I mean, there's billions of copies out there. And if we take a current model trained on the internet, I suppose that it has a hard time sort of circulating around that image. But there is a million of other, that's why I showed this Da Vinci example, a million of other examples out there that you haven't potentially seen yet. And my point was that they're all can all be fairly different from another. I mean, that's what creativity at the end of the day is all about. And if you want to take care of each of these individual details, it's becoming eventually harder and harder the further these samples are eventually out in this long tail distribution. And that was the point that I wanted to make. Not that you cannot tackle the Mona Lisa that evidently sort of everybody here knows about, but the many more samples out there that you and I probably also haven't seen as of yet.
All right, thank you, everybody. We're going to take a 10-minute break now, and we'll start again at 10:40. Okay, see you all soon. And let's thank Bjorn again. Sorry. Poster authors, physical posters, we now have a room for you. Well, it's okay. You don't need those. These are online, physical posters.
We know who are the authors of this poster. Maybe we send them an email.
Good question. So I'm presenting at the second poster session. I just want to know how long it is. It's not mentioned. So it's hard. It says that it's 25, but then sorry, what?
It's really nice workshop. So do you plan to see this workshop every day? Yeah, I mean, I'm the organizer. So yeah, so you'll be here. Okay, then I'll come back to you next week.
I just showed up.
So do we know who are the physical person? Maybe we should send them an email about the location.
Oh, I don't know who are the physical presenters.
Okay, but I mean, they're presenting at 11:45. They need time. They need to know the location and set it up.
Yeah.
Or we just send all the poster authors email.
Yeah, let's do that.
Okay.
Wow.
I guess they're.
Oh, that's true.
You all right? You okay?
Yeah. Okay.
High five.
Thanks.
All right. And y'all aren't using this?
Okay.
Live conference I've been
Oh, all D to E. No, yeah, that's actually there.
Oh, okay. So it's the first floor. So
there's no number in there.
So I'm not sure if that's important. Would you say that this yeah, I mean, like, everybody all like the only thing that like there's like with the example thank you.
How do I pronounce your name? Syngren?
Syngren.
Syngren.
Syngren, yeah.
Syngren.
Yeah.
Oh, okay. Syngren. I don't remember the correct pronunciation.
Yeah, it's always the case. Do you want Cynthia or do you prefer Cynthia or Jingwan?
Either way.
Okay.
Either way. Yeah. I go by Cynthia for a long time, but I publish with my full name.
All right.
So are you or James sending an email?
James is sending an email. I'm trying to check the next video.
Maybe before the next speaker start, we also post on the slide. Oh, it's here already, right? Just maybe verbally call it out.
Oh yeah, I can announce that.
Okay. And you're introduce Elisa?
Yeah.
And then I'll introduce Yuhu and Olga.
Okay.
It's impossible to do Zoom. If you had a co-op that it was online.
Because you're not having to change context if you're looking at individuals. Like, and we have two things like our eyes shield kind of the element of we want to permit aggregate those and tackles the thing better division. Well, the brain doesn't do that, right?
Hi, this is Elisa Ricci.
If we're doing like neural texture similar to where the last time they gave us, and we have it's just that we have abandoned kind of we're going to replace it by a different texture, which is great directions.
I wonder whether you want to try playing the video now in case there's problem.
Yes. I set the board.
Hi, this is Elisa Ricci.
Yeah.
Okay.
The audio is
It was kind of quiet.
the audio is where is it coming out?
Here.
No, that's not good.
For the Zoom, I selected the audio share option, so it should be working. But let me also check.
Okay.
Most of the things that you get is dealing with individual things. And that means that your writing signal, in that case, 8:2 ratio, is just getting the right. Essentially, this is Jacob. This is just how it is. That's like the math piece in the score function that she gets. That's why these models are nice. You can all in one. But in that case, the focus will be something different. Wasting of things, which you can do, and that's probably also why the brain in that case goes forward to multi-stage process where you have one first aggregating information together, and then you have like the lateral process of dealing with linking these individual items.
No, I just need to check if the sound is playing through the Zoom.
Like if you say like before, it would be something like V1, V2. That's how we bring it. Once you're through LGN, you have a few other things like writing the product. The tricky thing is there that 90% come from everywhere else but from the eyes and the eyes.
One of my emails it's making a large sound. Where is it? No, it's not. Okay, yeah, it was Elisa. I was talking.
We test the video.
Yeah.
I just want to check that it's coming out of the sound, the room.
Hi, this is Alice Ricci, and I would like to present our work on generating playable videos.
It's coming out here. It's not coming out.
Okay.
So what, or is it that you're sharing in Zoom?
Yeah.
And now you play the video?
Yeah, I'm sharing it via Zoom, so the virtual attendees will hear this sound.
Okay, let's hear it. Let's play.
Hi, this is Alice Ricci, and I would like to present our work on generating playable videos.
Yeah, so
So if I play video.
All right, so our hero is here.
Hi, this is Alice Ricci, and I would like to present our work on generating playable videos.
It's a pleasure. It's a pleasure to meet you.
Well, I'm just saying, this person I recognize their face on the slide.
Indeed.
You always want to go to headphones real quick. I'm just letting you know.
I'm running a tutorial this afternoon. And I'm just assuming we're going to run until like 8 p.m. So I'm just.
Let me first give you an intuition on what inspired us to start this project. We've been dealing with videos since many years in computer vision. In particular, sports videos are especially interesting. And over the years, we've been developing several techniques to recognize action in sports videos. However, when we start this project, we'll look at sport video. Hi, this is Alice Ricci, and I would like to present our work on.
It sounds good. Okay.
All right. So let's just start again.
Okay.
We're gonna kick off. All right, hello everybody. Let's get started again.
So physical post presenters, please find your location and put your posters on the boards on Hall D and E. Okay. Our next invited speaker is Elisa Ricci. Elisa Ricci is an associate professor at the University of Trento and the head of the Deep Visual Learning Research Group at Vandenise Bruno Kessler. She's the scientific manager of the Joint Laboratory on Vision and Learning between FBK and DISI. Her research interests are mainly in the areas of computer vision, robotics, machine learning, and human behavior analysis. So she was going to present through the pre-recorded video.
Generating playable videos. Hi, this is Elisa Ricci, and I would like to present our work on generating playable videos. Let me first give you an intuition on what inspired us to start this project. We've been dealing with videos since many years in computer vision. In particular, sports videos are especially interesting. And over the years, we've been developing several techniques to recognize action in sports videos. However, when we start this project, we'll look at sport videos under a different perspective. And we ask ourselves, could we build an algorithm that allows to generate sports videos, and in particular, that allows the user to interact with this generation process and provide commands that indicate the position of the players in the tennis field or the position of relevant objects, such as, for instance, the ball. Somehow, what we want to achieve, and actually what we achieved at the end of our first project, is illustrated in the video that you see here. Here, this video has been automatically generated with a neural network, and at inference time, you see that the user is providing some command, and this command corresponds to the action that the player is performing on the tennis field. So action are move to the left, move to the right, move forward, and so on. The video that you saw has been produced with the algorithm that we presented last year at CVPR in our paper Playable Video Generation. This was a joint work between people in Trento, people at Telecom Paris, and the SNAP. Let me explain better what we mean by playable video generation. Given a set of labeled videos, for instance, several videos of a tennis match, what we want to do is to learn a neural network that allows to automatically understand the relevant action that happen in the videos and generate relevant frames. At this time, we want to use the neural network that we have trained, and the user can control the generated video on the fly by providing a command, and command correspond to action labels. The generated video will contain players that will move into different directions, for instance, right, stay, forward, as you see here. How do we achieve playable video generation? We design CADD. CADD stands for clustering, for action decomposition and discovery. In a nutshell, our approach allows to discover a distinct set of actions by watching different videos, and the clustering approach is blended with the generation process. This is realized with a deep architecture that you see here. This architecture has an encoder-decoder structure, and importantly, in the bottleneck layer, we obtain a discrete representation of the transition between consecutive frames. A reconstruction loss is used as the main driving loss, and we don't employ any supervision in order to discover relevant action. This slide illustrates better our CADD. Given an input frame, we adopt an encoder to learn a frame feature representation. And then in the bottleneck layer, we have a dynamic network R that estimates the successive states given the previous state and the frame representation. An action network is used in order to predict the action labels associated to recurrent frames. Finally, a decoder is used to reconstruct the frame given the state representation at time t+1. In order to supervise our model, at first we tried a simple frame reconstruction loss. However, we found that this pure image supervision to be insufficient here. In order to train our approach in a self-supervised manner, we consider different time frames and multiple supervision at different levels. In particular, we compute reconstruction loss at frame level, a reconstruction loss at feature level, and a reconstruction loss associated to the action. One important feature of our method is the design of the action network. In the action network, we decided to model action as the sum of two components, a component that is a discrete component and a continuous component. The discrete component indicated the action label, so the type of action, over a set of possible k action, while the continuous component indicates some action variability. It is actually intuitive that an action can be performed in many different ways according to the speed or, for instance, the direction. The action network is designed as you see here. So given the feature representation associated to two consecutive frames, we compute some associated embedding and then an action direction dt from the difference between these embeddings. And then we use a multi-layer perceptron in order to predict the probability associated to a certain action and then derive the action label. The action variability embedding Vt instead is computed as you see here. The intuition here is that we can use the centroid of the action direction space, since if we expect the space of the action direction, we see that there is some clustering happening. In order to train the action network, we design an action loss that is based on the maximization of the mutual information, and in particular of the mutual information between the action extracted from the input sequences and the corresponding one extracted from the reconstructed frames. At inference time, we only use the decoder and the decoder network and the dynamic network R. In fact, the user provides input directly to the dynamic network, and in this way, it is possible to generate frame corresponding to certain action. Here you see some results associated with our approach. In particular, the user is providing some input by typing on the keyboard, and you see that the player is moving accordingly. Something important that I didn't tell you so far is the fact that our approach can be also used for other type of object. For instance, here we decided to perform some experiment and we consider one Atari game, in particular the breakout game, and here the user provides some command in order to move the pad for hitting the wall. While in the video that you see on the right, the user is providing some command and is moving the robot arm, and this is the Bayer dataset. Finally, let me show you some actions that are learned by our model. In each column, we have a different type of action, and as you can clearly see, the action variability is captured by our approach, since different actions are performed in a slightly different way. Finally, an important feature of our approach is that it allows somehow some interpolation in the action space. So for instance, you can see on the diagonal, the top left, that the resulting videos are obtained by interpolating the action 2 at the action 7, and you see a player moving in diagonal. Let me now summarize the contribution for our first work. In this first work, we introduce a new problem, playable video generation. That is, generating videos by providing the user the possibility to interfere with this generation process by providing discrete command. We also introduced CADD, a first self-supervised method to deal with the problem of playable generation. It is an encoder-decoder architecture that automatically extracts relevant action from a large collection of videos. We demonstrate in our experiments that CADD offers the user a game-like experience. And for instance, if you go online and look at the supplementary material associated with this video, you can really play. Of course, we were really happy with our work, but we are also aware of some of its limitations. For instance, a couple of limitations of our first work on playable video generation is the fact that our approach can only deal with a single object and also does not allow any possibility for camera control. Some of this limitation has been addressed in our follow-up work, that is the work that we are presenting at CVPR this year. This work is called Playable Environments, Video Manipulation in Space and Time. And is a joint collaboration between people like Trento, Telecom Paris, SNAP, and MPI for Informatics. Let me first tell you what we mean by playable environment. Let's consider again a tennis match. What we want to do is to generate videos of a tennis match by giving the possibility to the user to control many factors. For instance, we want to give to the user the possibility to control the movement of multiple players, and for instance, to move the players on the left, to move the players toward net, or to move the player on the right. We also want to provide the user the possibility to control the position of the camera. Finally, we want to give the user the possibility to control the style of the player and the style of the background. In summary, with playable environment, we would like to have the possibility for the user to manipulate the style, the movement of the players, and the camera. In order to create playable environments, we design an approach that has 6 key characteristics. Playability. This means that we want to give the user the possibility to control the movement of the relevant people and the relevant object in the scene. We want our framework to support multiple objects and also deformable objects such as humans. We want our framework to provide some support for camera control. Finally, we want our approach to provide some support for controlling the style of the object and of the background. And we also want our approach to be robust to error in camera calibration and object localization. Let's now see a bit the detail of our architecture. Our framework is trained on data of calibrated monocular videos, and we assume to have bounding box notation for all the relevant objects in the scene. Our framework is trained with a 2-stage pipeline. A first encoder network is extracting the environment state for each object in the scene. The state is represented as a triplet of 3 elements indicating the position of the object, a descriptor of the style, and the object pose. Given the states of the object, a synthesis module is used to reconstruct the frames given also information about the camera pose. To design the synthesis module, we take advantage of all recent advances of the computer vision community into neural radiance fields. In particular, we model the scene as a composition of radiance fields associated to the different objects. And we consider two multi-layer perceptron. A multi-layer perceptron V is used to represent the object in a canonical pose, and then a second multi-layer perceptron B is used to deform the canonical values into the desired object pose. Importantly, the multi-layer perceptron V also handles information about the style. Importantly, similarly to previous work, we also train our approach in order to regress a grid of features, and then we apply a feature renderer to compute the reconstructed image. We also found beneficial to use a multi-scale approach into the synthesis model. We train our network with 2 reconstruction loss and a 2 reconstruction loss and a perceptual UGG loss. In the second phase of our framework, we train the action module. Design of the action module is quite similar to what we have seen for Playable video generation. In the action module, we have an action network and then a dynamics network R, similar to what we have seen before. The action network models the action with a continuous and a discrete component, while the dynamics network output the predicted state given the previous state. In the second phase of our network, we adopt several losses. We use an L2 loss for reconstruction. Then for action learning, we use a modal information loss similarly to the one that we use in PVG, but we also introduce 2 new losses, one for the minimization of the variance of the movement for each different action. And also we consider an adversarial loss on the action sequences in order to discourage the network to learn actions that are not meaningful. Finally, at inference time, we perform similar operation of the one that I had explained to you for PVG, where only the dynamics network is used while the action network is discarded. Let's now see some results. We evaluate our approach and release 2 new datasets. The dataset is called Minecraft and comprises over 1 hour of videos at different conditions, such as day or night. While the tennis dataset has been obtained from videos from YouTube and contains over 12 hours of tennis matches. For this dataset, we also provide annotation for camera calibration and for bounding boxes of the relevant object in the scene. In this slide, I show you some results that are obtained with our approach. The user is providing some comments, and as you can see here, different comments correspond to the movement of all the players in the scene. This is different from what we saw for PVG, where we only have the possibility to control 1 player. In this slide, I show you some results associated to the possibility of controlling the style. As you see here, on the column, we have an indication of the reference style, and you see that given some content, we have the possibility to generate videos with different style. Finally, in this slide, I show you some example of camera control, both for the Minecraft and for the tennis match. As you can see, our approach allows really to change the camera position significantly. Finally, let me show you some visual illustration of the learned action with our approach. You see that different actions are clustered and we have some inner variability into the set of all possible actions, similar to what we saw for PVG. Let me summarize now. In the second work, we have introduced a playable environment that is the first approach that allows to support camera control, object and style manipulation. Differently to PVG, it also allows to support multi-object manipulation. Our work somehow complements recent work on video manipulation, where the emphasis was mostly to camera and style control, while here we also provide the possibility to control the movement of the object. While we made significant progress this year with playable environment with respect to playable video generation, we still have many work to do. For instance, we noticed that in our videos, the small object when they are rendered, they have some blur. We also have no possibility in the current method to integrate interaction between different objects, as well as for now, for the dataset that we have considered, the action only captures the movement of the players. That will be good to move in more complex scene and more complex videos, but still retain all the favorable properties that we have be able to support until now. I would like to thank you for all the attention and also to thank my collaborators in this project. Some of them will be around at the conference, so please reach them out if you are curious about our work. Thank you.
So Elisa is online. So do you have any questions? Okay. Due to time limits, we can move on. If you don't have any questions, we can move on to the next session. If you have any questions, please email Elisa or contact Elisa.
The next speaker is Hugo. Hugo is a senior research manager at Adobe Research. Prior to that, she has obtained her PhD from EPFL under the supervision of Professor Mark Pauly. Hugo has received the Eurographics Young Researcher Award in 2020, and she is excited to work at the intersection of computer vision and graphics, where she is eager to develop methods to bridge the gap between 2D and 3D. Her research specifically focuses on 3D inference and analysis, both for human-made objects as well as humans. So welcome, Hugo.
Okay, can you hear me? Okay.
Let's put this as best we can.
Yeah, thank you so much for the introduction. So today I would like to share some of my recent work in the context of using learning for creating plausible characters and specifically looking at how to model their clothing. Okay, so the first question of course, why do we want to do that? I think Michael's talk in the morning was a good introduction. As like with the recent buzz in metaverse and also the fact that real and virtual worlds are tightly connected, there is of course increasing demand in creating avatars, and whether these are stylized avatars or photorealistic avatars, of course we want these avatars to look plausible, natural, and clothing is one of the main components to make them plausible. Of course, with avatars, one other main application is telepresence. We all spend lots of time in virtual communication, not just for work, but also for to connect with our family and loved ones. So that's why there is an increasing research interest in creating photorealistic avatars and how to model how the clothing moves, deforms as the people move. And as we create these algorithms for creating 3D characters and modeling their clothing, of course, such methods can also be used for inverse tasks. So for example, given images and videos, we know that humans are one of the main subjects. So if we have algorithms to create the 3D underlying 3D bodies or the clothing, we can use them to understand these images and provide intuitive editing. For example, we can look into changing the pose of people and making them move, or specifically looking at their garments and trying to, for example, edit the texture or the shape. So with all these applications, and there are of course many more, I've been looking at how to use learning methods for creating physically plausible characters. And there are many aspects that of course needs to come together. So first is modeling. Of course, we need to model, create these characters, and specifically for today, I'm looking at how to model their clothing. Once we have the models, we want to put them in motion. So we want to animate them and make sure they still move in a plausible and natural way. And of course, depending on the application, we want to render them or synthesize them in 2D with high quality. And of course, as humans, we are not isolated creatures. We move in scenes, we interact with each other. So there's this other component of placing these characters into scenes and making sure they interact with the scene or each other. And in the morning, Michael gave lots of great examples of how to look at this problem of putting the characters into scenes. So in today's talk, I would like to briefly walk you through like what a typical workflow is for modeling, animating, and rendering these characters, and then see how we can use machine learning to basically make this workflow more efficient. Okay, so, and specifically, let's look at the clothing of these characters, so the garments. So what does a typical workflow look like today? So usually the workflow starts by modeling the garments. So a designer models the garment patterns, drapes them onto a 3D character. And once we have the garment model, then the next step is to animate it, for example, based on the underlying body motion sequence. And today we use usually physically based simulation to do that. And once we are happy with the final result, then we want to render it based on like desired rendering conditions, for example, target viewpoints, lighting, etc. So my research interest started by first looking at this first step of this workflow, which is the modeling part. Okay, so what does the typical garment modeling look like? So usually a designer starts with an initial sketch. Basically, this gives you the desired look of the garment that you want to model. And then you have to iterate between basically designing the 2D garment patterns. Those are basically the flat patterns that you can sew together into the 3D model. And then you want to drape them either physically on a 3D mannequin or simulate them. And then you have to basically go back and forth between these 2D pattern design stage and the draping stage until you can really get the target look that you are looking for, that you started with your initial sketch. So this is a cumbersome process. So the first question to ask was like, can we actually use machine learning to automate this workflow? And to achieve this goal, basically looking at that typical designer workflow, we identify 3 design spaces that the designer operates on. First is the input sketch. Basically, this is the ideation stage, the stage where you want to specify the final look of the garment. Then you have to operate in the parameter space. So these are the parameters of the underlying garment. For example, the dimensions of your garment patterns, their material properties, as well as the underlying body shape. And the third design space is the final 3D basically model of the garment, how it looks like once it's draped. And basically what we did was to define 3 encoder-decoder networks that could go from one design space to the other. So you can, for example, define one network that takes the input sketch, predicts the parameters of your draped garments. You can have another network that takes the input sketch, gives you the parameters of your garments. And finally, another network that takes the parameters and then predicts how the garment looks like once it's draped. And the key was basically to train all these 3 networks jointly so that they learn a common latent space, which we call the shared shape space. Once you have this common latent space, now you can easily switch between these different design spaces. So using this basically property, you can now design, build, for example, interactive tool like this. Given an input sketch, now the system can give you the 2D garment patterns, how it looks like in 3D, the body shape. Because we know the 2D patterns and the correspondence to the 3D, you can easily go change the texture of the garment. And moreover, you can now go back to your input sketch, make some changes. For example, in this case, we are editing the sleeve lengths. You can change basically the silhouette of the t-shirt, add more fold lines, and the system can interactively predict the new shape of the draped garment. So basically just to make it easier for you to see. So this was the initial sketch, and after editing, this is what you get. So before and after. And in addition to this interactive system, you can also use the system to basically get sketches from reference images and then predict the corresponding garments. Here you see examples of t-shirts, skirts, and a dress in this particular case. Okay, now that we have looked into the modeling phase, and let's say we are happy with the garments we have, the next stage is putting this garment into animation. So typically what you would do for this task is to use physically based simulation because it's very accurate and it can give you really the accurate garment dynamics. But based on the application, it may not be the most computationally efficient solution. And for some applications, we may not really care too much about physical accuracy, but maybe you are just interested in something that looks plausible. And so that's why I feel learning-based methods can come into play and play a complementary role to physically based simulation. So that's why, like in this follow-up work, our motivation was, what if I start with a garment? I don't simulate it in high resolution. I simulate it in coarse resolution, and then try to enhance it. And why do I want to do that? Like here you see one typical example. So simulating the garment at the high resolution is not only computationally expensive, but it's also sometimes not robust. It requires lots of tweaking of the simulation parameters. So instead, what we can do is take the target garments, obtain a much coarser mesh. We can run our physically based simulation on that coarse mesh, and then we can turn to learning-based methods to augment that coarse simulation with additional details so that it can look more plausible. Okay, so basically to recap, we assume that we have some input garment mesh that is obtained by coarse simulation, and we represent it by its corresponding surface normal map. And our goal is to basically enhance this normal map with more details so that it can look richer and more plausible. And the really interesting part here is like to cast this problem of adding details as a style transfer task. So basically here you see a skirt that is both in a coarse resolution and a high resolution. it's been simulated basically in these two modes, and you see the corresponding normal maps. So what we hypothesize is that we can come up with some neural feature space where the coarse simulation and the high resolution simulation have different distributions, different statistics. So now adding details to a coarse simulation basically boils down to finding this transfer function that can go from one distribution to the other. So basically with that motivation, we hope to train a detailed transfer network that can basically look at many examples of a garment simulated in two different resolution modes, and then take the coarse resolution normal map patches and then enhance them with additional details. Here, the content loss basically tries to preserve the original coarse folds that are already present. And then the style loss tries to add additional wrinkle details. And we basically observe that the network tries to either sharpen some of the wake folds in the coarse simulation or tries to add some additional details in nearby regions. So basically the final pipeline looks like this. We start with the coarse geometry that we get from this coarse simulation. We look at the corresponding normal map. We can crop any surface normal map patches. We provide them to our detail enhancement network, which enhances these patches. Then we can put them together and we can integrate them back to get our final geometry. So here you see like some results. As you can see, like there are 3 different garment types in this example, and I think they were made from different materials, and the network can basically add more details to these simulations. And here's another example of a skirt with multi-layer laces, which is usually not so easy to simulate, but you can get the coarse simulation and then try to enhance it. Okay, so now we basically saw 2 quick examples of how we can use learning for modeling and simulating. And for some applications, what we really want to do in the end is really render these garments from particular viewpoints. So in this last project, basically we try to look at this problem of like, how can we synthesize the dynamic appearance of these garments, basically try to do the simulation and rendering steps in one common pipeline. So more specifically, basically the goal here is we have a target garment and we have a corresponding coarse template for this garment. So given some underlying human motion sequence, we first try to predict how a coarse garment, in this case, like a very plain skirt, would deform. And then we try to learn some neural features that are attached to this coarse garment so that if we render them with a neural renderer, it can actually synthesize the appearance of a target garment, which is much more complex than the coarse garment itself. So here, basically, the coarse garment is not just a low resolution mesh, but it's actually a much plainer mesh that doesn't have the geometric details, such as these multi-layer laces in this case, because those are really what makes the simulation more difficult. So yeah, basically the key part is like, how can you go from this coarse template to this final target garment appearance? And this idea was basically inspired by the neural rendering approaches, specifically the D4 neural rendering paper that came out a few years ago. So the idea is you can learn some neural features or a neural texture for your course templates. So basically those features are attached to your course template. As the template moves, those features will also move. But the thing is, like, the appearance of the garments are not static. They also change with the underlying body motion. So learning just a global neural texture is not sufficient. So that's why we also try to extract features from the underlying motion sequence. And then we combine these features with the neural texture. all of these features are defined on the surface of the template, so that like as this course template moves, those features also move and then get displaced in the 2D image plane. And then we can train a neural renderer that can interpret these final features and then give us the target garment appearance. So basically here you see an example. We start with the same course template, but we then define we train two different neural networks and learn two different neural textures that can synthesize the appearance of two very different target skirts given the same underlying course template. And of course, like once you train your garment specific network, you might want to do like some fine tuning. For example, you might be training the network with a particular body shape. Now, if you have just very few examples of different body shapes, how can you basically adapt this network? So we can do very quick fine tuning to make the network adapt to different body shapes, and you see that the wrinkles that are synthesized are also now changed based on the underlying body shape. And more recently, we have basically extended some of these ideas to learn to synthesize full human appearances. And this is going to be presented at CVPR this week. If you're interested, please come to the poster session on Tuesday. Okay, so with that, basically, I just tried to give you a quick glimpse of how learning-based methods can be used to basically enhance or help different parts of a typical garment designing and animation workflow. But of course, there are, I think, many open challenges in this area. So I want to conclude by just hinting at some interesting future directions. So with any learning-based method, of course, the first question is how well does the method generalize? And there could be many different axes for generalization. I think the first one is, for example, how do you generalize across geometry, across different garment types and their geometries? So in the first work I showed, we were working on local patches cropped from normal maps, basically to address this issue. But in practice, many of the works in this domain are still garment specific. So you train one network for one particular garment type. But there's a lot of interesting work happening in neural implicit representations and also coming up with hyper networks to generate such implicit representations. So I think it would be interesting to see if we can adapt some of these ideas to come up with basically a more unified way of handling different garment types. I think generalization across motion is another axis, which is perhaps a little bit less studied. Usually like methods that try to animate humans or garments, as the testing motions become less similar to training data, they start failing. So I think it's also interesting to think about what are some efficient representations for motion? How can we cover the motion space more effectively? And finally, like we all change, the thing that changes most is, of course, our clothing. So as we develop these very high quality, personalized or garment specific networks, we also want to be able to adapt them easily. For example, let's say I have this network trained for this multi-layer skirt. Now, if I have just a few examples of a different type of garment, can I easily adapt this network to this new case? So I think maybe using meta learning or similar approaches to look into this problem is also very interesting. So yeah, with that, I feel there's lots to do in this direction. And I'm excited to see like more work basically towards building more generalized and efficient representations for creating plausible characters. And yeah, I would like to thank you all for listening. And if you have any questions, I'm happy to answer.
We have time for one or two questions.
Thanks for the great talk. I'm Matthew. I work at Snap. I'm curious, in the first work you presented, you talked about these three spaces, basically the sketch, matches, and finally the 3D rendering. I would imagine that like each of those spaces is very stylized based on the design studio making it, or even the designer in a particular studio. I'm curious if you had to account for that at all, how you handle the variations in the data sets.
Yeah, I think that's a great question. For that work, actually, the data was generated synthetically by adapting like non-photorealistic rendering methods to render those sketches from 3D garments. I think it would be good, but also a bit challenging to collect real sketches from artists. But maybe like it might be interesting to think about like, okay, you have this large set of like sketches that are synthetically generated. What if you have a few examples from a particular style, whether we could like combine them in a common framework? That would be interesting, but yeah, we haven't looked into that aspect.
Thank you.
Okay, thank you, Diego. Okay, so let me introduce the next speaker. Olga is an assistant professor in the computer science department at Princeton University. Her research is in computer vision, closely integrated with the fields of machine learning, human-computer interaction, and fairness, accountability, and transparency. She has been awarded the Anita Borg Emerging Leader Abby Award in honor of Denise Denton in 2020, the CRAWP Anita Borg Early Career Award in 2020, the MIT Technology Review's Certified Under Certified Innovator Award in 2017, the Pammy Everingham Prize in 2016, and Foreign Policy Magazine's 100 Global Thinkers Award in 2015. In addition to her research, she co-founded and continues to serve on the board of directors of the AI for All nonprofit dedicated to increasing diversity and inclusion in artificial intelligence. She completed her PhD at Stanford University in 2015 and her postdoc fellowship at Carnegie Mellon University in 2017. Welcome, Olga.
All right, thanks so much. That was a beautiful bio, and also gave me a second to figure out the Zoom issues, which are of course inevitable. Okay, so I think we can see everything. Excellent. So hello everybody. So I will first of all say, so I'll be joined today by two students, so Vikram Ramaswamy, who is a senior PhD student at Princeton, as well as Dora Zhao, who just completed her master's degree and is about to start at Sony AI next year. So what we'll talk about today is fairness in the context of course, AI created content. And before we dive in, I also want to wish everybody happy Juneteenth. I'm not sure that happy is quite the right word. It's it's obviously a complicated holiday with a very complicated history. And if you don't know much about it, I definitely encourage you to sort of read about it and understand the importance of it. But this is the second year that we're celebrating as an official federal holiday. So there's a lot of meaning behind that. So anyways, just wanted to acknowledge that before diving in. So as computer vision is getting better and better, as we're able to build these truly amazing systems like some of the ones that you're hearing about at the workshop today, correspondingly, unfortunately, there's also a rising increase in ethical concerns with these systems. And in fact, the current trend sort of kind of looks like this, like as the systems are becoming more capable of doing really exciting things, we are starting to sort of ask questions about what it is that they're actually learning and what it is that they're actually doing. And there's a number of examples. These are just a small subset, right? So in 2017, a photo app filter was released that claimed to increase attractiveness of your photograph, which, putting aside the question of why you need a filter to increase your attractiveness, but the sort of even bigger issue was that it did that by manipulating skin color. Or, similarly in 2017, this was about a best paper award at EMNLP 2017, where machines that were taught by photos learned a sexist view of women, so associated women with particular activities. Facial recognition is accurate if you're a white guy. So this is the seminal work by Joy Bellamini and Timmy Gebro that came out in 2018, looking at the disparate accuracies of face recognition systems across people with lighter skin versus darker skin. And this has a lot of downstream implications, particularly as face recognition is used in settings like policing. And finally, sort of some of the recent, controversy or discussion on Twitter around cropping algorithms that would prefer lighter skinner, slimmer and younger faces. So what is our goal? So a lot of the work in my lab is focused on sort of trying to mitigate these ethical concerns while continuing to advance computer vision capabilities. Sort of the goal is let's build better and better computer vision systems, but do that without kind of amplifying these issues. And so today, we're going to kind of talk very briefly about two papers that are arguably very loosely related to AI created content, but we'll try our best. So the first work will look at how we can actually leverage some AI created content, some sort of images that are generated using GANs to try to mitigate bias in a data set, to try to sort of circumvent some of these issues. And then in the second line of work, so we haven't actually studied bias in AI created content itself. There's lots of work on it, but we haven't done that. So we'll instead talk about studying and mitigating bias in a setting that's more complex than image classification. So image classification is where these issues are commonly studied. We have a recent work studying this in image captioning. And so we'll sort of talk about that. And you can imagine that some of the findings there might generalize to if you wanted to study kind of these more complex systems that are doing content generation. And so the two pieces of work, the first one is at CVPR 2021 that Vikram will present, and then the second one is an ICCB 2021 that Dora will present. And so with that, I will pass it off to Vikram to dive in.
All right. Hi, everyone, and thanks to Olga for that introduction. Right, so let's get straight in. So real-world data sets are biased, right? So in current data sets, certain attributes like gender tend to be correlated with certain actions like cooking or coding. And let's say that I want to train a hat classifier. And so let's assume that hats are actually correlated with a certain gender. Then the classifier might pick up on gender cues rather than hat cues, which is what we really want. Or let's actually look at something that's more easy to visualize. So let's assume that like hats and glasses are correlated. So most people who tend to wear hats also tend to wear glasses and vice versa, as seen in this image. I don't think it's in my mouse. Okay, let's assume you can. Okay, so training a classifier for a hat in this data set might only recognize hats in the presence of glasses. And ideally, what we'd like to do is train the data set wherein these two attributes are independent. Right, and so how do we actually go about doing this? So one way is to actually collect a balanced data set. So the seminal work by Bellamini and Gebro, as pointed out by Olga, actually considered this and created a new data set called Pilot's Parliament's Benchmark, which is roughly balanced by both gender as well as skin type. But the issue here is that the real world is inherently biased, and it's not always possible to create a balanced data set, especially a large balanced data set. And so we wanted to look at what you can do in the absence of this. And so one way is to leverage models like GANs in order to create a balanced synthetic data set instead. So here's a quick summary of how you can do this. You can sample a bunch of latent vectors Z and pass it through a generator to create a bunch of images. And you can label these images and then train a target attribute classifier with both the real as well as synthetic images. And before, obviously, if I do this in a very naive manner, the generated images are going to maintain whatever biases I have in my training distribution. And so what we'd like to do is sample in a slightly better way in order to create a balanced data set. But before I actually talk through this, I want to quickly go through some of the concerns of doing this. So visual manipulations along dimensions of race and gender have the potential to perpetuate harmful stereotypes. So for example, you might perpetuate the stereotype that certain genders are more likely to have hair lengths of a certain, more likely to have specific hair lengths, or that certain genders are more likely to be wearing makeup. And especially along race, this has very harmful historical parallels. And I just want to acknowledge that, especially since today is Juneteenth. So what we are going to do is we're going to consider generating such images part of the model's internal representation. And we're not going to display any such images. And in fact, like I'm going to show images wherein the correct attribute is something that's very easy to discern, like varying classes. Okay, so let's move on. Okay, so how do we actually use GANs to create a balanced data set? So Denton et al. And Shen et al. Show that the latent space of a GAN is linearly separable for semantic attributes. And so what we can do is basically learn a hyperplane for the correct attribute. And now, given a randomly selected latent vector Z, I can project it onto the hyperplane and thereby learn a latent vector that is theoretically not reliant on the correct attribute. The issue here is that it's sort of unclear if the correct attribute is actually hidden in this case. So here's our second idea. So since we can't actually like hide the correct attribute, let's maybe try and generate pairs of images instead. So given a latent vector Z, we can learn a latent vector Z prime that has the opposite predicted attribute score. And so the idea here is that we generate pairs of images, one with glasses and one without. Of course, the problem here is that I'm not really paying attention to the target attribute, varying hat, and naively perturbing latent vectors in this way can maintain biases. So for example, when I add glasses, I might also add a hat. Okay, so the method that we propose is to learn hyperplanes for both the target as well as the correct attribute. So I learn a hyperplane for varying hat as well as a hyperplane for varying glasses. And so now given the latent vector Z, I can compute a vector Z prime that has the same target attribute score, but opposite correct attribute score. So the idea here is that I generate pairs of images, one of which is varying glasses while the other one is not. And both of them are either varying hats or not varying hats. So generating a balanced synthetic data set in this way has several advantages. So the first one is that we really need only one GAN in order to do this for any pair of target correct attributes. Moreover, we are able to maintain intra-class variation. So consider an attribute like smiling, which ranges from not at all smiling to partially smiling to smiling. Since our latent vectors Z are sampled randomly, we sort of maintain this variation within our synthetic data set as well. Finally, our samples are generated in order to maintain independence between the target and correct attributes, which is what we want to train with. Okay, so this is all well and good, but like, how does it actually do in practice? So our goal here is to basically see how well training with this balanced synthetic data set performs. So the task that we use is visual attribute classification. We use a celebrity data set for this, which is a data set of celebrity faces annotated with 40 different attributes. Out of this, we use 26 attributes as our target attributes, and the correct attribute that we use is gender expression. Again, a caveat here, Celebi, like almost all visual data sets, is annotated with gender expression as a binary. And obviously, this is not true, but since we do need to train fairer attribute classifiers, we are going to use these labels as is. So the baseline over here refers to a model that's trained on solely the Celebi data set, whereas ours refers to a model that's trained on both the Celebi data set as well as a balanced synthetic data set. We evaluate these models on multiple metrics. So the first metric that we evaluate on is average precision. And this is basically an accuracy metric to tell us like how well these models are actually trained. But in addition to this, we also evaluate on 3 different fairness metrics. So this is difference in equality of opportunity, bias amplification, and the KL divergence. So the difference in equality of opportunity is the absolute difference in the false negative rate between the 2 correct attribute groups. Bias amplification is the amount of increased correlation between the target, the correct attribute, and the model's prediction. And the KL divergence is the KL divergence between the correct attribute score distributions. Okay, so first, in comparing with the baseline, we see that ours, which is trained on both the original Celebi data set as well as a balanced synthetic data set, has a slight loss in AP, as seen here, but is a more fair classifier according to all 3 fairness metrics. So these numbers are averages across all 26 attributes, and the error bars represent 95% confidence intervals through bootstrapping. Okay, so we also compared with several prior works. So the first one that we did compared to was Fairness GAN by Satigari et al. So this is a GAN that's trained with an additional loss function in order to achieve either demographic parity or equality of opportunity with respect to a particular attribute. Satigari et al. Trained models on this generated data set and measured the false positive rate, false negative rate, and error rate for both gender expressions. So similarly, we also train models on just a synthetic data set in order to match theirs and find that despite a much simpler training procedure, we actually do better on most metrics. Finally, we compared to several bias mitigation strategies. So we used models trained by Wong et al. This is also a paper that was presented in CVPR 2020. They compared like weighted training, adversarial training, as well as domain independent training. So a weighted training method is basically a method where you reweight training samples such that both predicted groups have the same weight. Adversarial training is where they train with a minimax objective. So you're maximizing the model's ability to predict the target attribute while minimizing an adversary's ability to predict the predicted attribute. So we see that the weighted training actually does really well on all three fairness metrics, but the bias amplification is strongly negative. And this actually suggests that the model is making incorrect predictions in order to, the model is making incorrect predictions in order to mitigate fairness. And with respect to adversarial training, ours does better with most metrics. The final work that we compared to was domain independent training, which is the best performing work from Wong et al. And here we compared this with respect to both attributes that have low and moderate skew and attributes that have high skew. So the skewness is basically a measure of like how biased a particular attribute is. And we see that ours does better for attributes with low to moderate skew, whereas theirs does better with respect to high skew. And with that, I'd like to summarize a little bit. So yeah, so we introduced a GAN-based augmentation method that decorrelates pairs of attributes and is effective in reducing bias. So some limitations of our method is that currently it only decorrelates 2 to 3 attributes at a time, and ideally we'd like to decorrelate more attributes than that. Also, while decorrelating these attributes, it's possible that we add bias along a third attribute. And so we need to learn how to be aware of this and eliminate such bias. And so thank you for listening. If you're interested, here are some links for you to check out. And yeah, with that, I'm going to end. Thank you.
Okay, awesome. So I'm going to talk a little bit about our paper, Understanding and Evaluating Racial Biases in Image Captioning. So to give an overview of this work, in our work, we make 2 main contributions. So first, we collect demographic annotations on the Common Objects and Context, or COCO dataset. And then using these annotations, we then assess the pathways for bias propagation in image captioning systems, including the COCO images, as well as the manual and the automatically generated captions. So to start, while racial biases have been uncovered in many computer vision tasks, including gender classification, pedestrian detection, and image tagging, we turn our attention to the previously unexplored task of image captioning. And so image captioning is particularly interesting, not only because it involves both a visual and a language component, but also because of the important societal applications of image captioning for accessibility purposes. And of course, one question that arises with regards to race in this context is whether racial descriptors ought to be included or not in the generated image captions. And so on one hand, in some contexts, individuals who are blind or low vision may want to have racial descriptors, and further that they ought to have the same information that sighted individuals have. However, on the flip side, there's always the ethical implications that arise when assuming the race of individuals. And so in our work, we consider not only the use of racial descriptors in automated captions, but also the other ways in which racial biases can propagate in image captioning systems. And so to start, for our bias analyses, we begin by crowdsourcing skin tone and perceived gender expression annotations for the COCO data set. And in total, we collect annotations on 15,762 images from the COCO 2014 validation set. And consistent with prior works, we find that there is an underrepresentation of individuals with darker skin tones, and we note the unique intersectional underrepresentation faced by darker skinned female individuals. And so beyond being used for this work, we've also released these annotations for future research. And so now we can use the annotations that we've collected on the COCO dataset, and we can assess the pathways for bias propagation within image captioning systems. And so we start by looking at the COCO images and the manual captions. And so for the images, we find that there are differences in visual appearances, such as in simple image statistics, such as the size of the person or the distance from the center of the image, as well as in object co-occurrences. And next, when we consider the manual captions, we note the presence of slurs, as well as the use of racial descriptors in these captions. And finally, we consider the automatic captions produced by image captioning models, including looking at the use of racial descriptors, as well as the differences in caption accuracy. We also analyze the differences in the caption content. However, since, as I mentioned before, we found differences in the visual appearances in the image, we need to first disentangle the differences that are arising from the image content versus the captions themselves. And to do so, we find pairs of images that have similar visual appearances differing only by the skin color of the individuals featured in the image. And in total, this results in an evaluation set of 876 images. And then using these images, we are then able to examine where and how captions diverge, even when the visual differences are controlled for. And so finally, we find that both the manual and the automated captions differ depending on the skin tone of the individual pictured. And in order to do so, we train a classifier to see whether it could differentiate between captions describing lighter versus darker images. And so first, to see whether the semantic content differs, we train a multi-layer perceptron on the sentence embeddings. And here we find that the manual captions are differentiable. And so this suggests that there is a learnable difference in the way that human annotators are describing different skin tone groups, even when the visual appearances are indistinguishable. However, we do note that the ability to distinguish between lighter and darker images decreases for the automated captions. And so next, we look at the differences in the vocabulary being used. And here, unlike for the sentence embeddings, we actually find that this ability to distinguish increases for the automated captions. And moreover, we note that there is an increase in differentiability in captions from the older models, such as FC, AT2, and DISCAP, to the newer transformer-based models, such as the Transformer, AOANet, and Oster models. And this actually indicates that bias may be increasing for these newer models. And so overall, our work here is providing a foundation for assessing how racial biases propagate in captioning systems and uncovers existing biases. Nonetheless, it's likely that as image captioning space continues to progress, these biases present will increase as well. And thus our work here really shows that there is a need for future work that aims not only to analyze these biases, but also to mitigate them. And so if you're interested in our work, here are some links to check out, including the link to the annotations we collected on the COCO dataset.
All right, very cool. So thanks so much, Vikram and Dora. And I'll just say, so all of this is part of a much larger research agenda that we have going on, studying fairness in computer vision systems and machine learning systems more generally. So I wanted to give a big shout out to all of the students and put up some citations if you're interested. And also we're looking for postdocs. So, and also always looking for PhD students, but particularly looking for postdocs. If this is a research area that's of interest to any of you, please do apply to come join us. So thanks so much. Happy to take questions.
Thanks for the topic. This is a great research. I would like to ask a question for the second talk. So basically, it mentioned that about the category that the website have those 76 attributes. I was wondering, the attributes that is required for the internet, like how do you deal with those attributes outside of 26 numbers, and also have you tried using multiple learning like a structured method to example, I will find out so that I rule that is not available around.
So I think, so, okay, so is the question basically about like what to control for? So how do you sort of, there's like infinite many attributes to describe a person. So
Yeah,
how do
one question is how to deal with the attributes that are outside the classes. And the other question is, can you use any content method to capture like those unknown attributes?
I guess to first answer the second question, we haven't tried using unsupervised methods, but I guess to answer the first, to control for visual appearance differences, just to, I guess, give more context on how we did that, we extracted the kind of ResNet 50 features for the images, and then we used like stable marriage matching in order to find like pairs of images that have the most similar kind of ResNet features. So I'll say for the unsupervised thing, so Judy Hoffman's lab at Georgia Tech has done some work around unsupervised bias discovery I think it was published in last year, I think it's BMVC 2021. And they do some work around sort of unsupervised discovery of biases in data sets.
Hi, great talk. Thank you very much. So I have a question for the first talk. If you could provide maybe a bit more detail about this linear separability in the data space. So I was wondering, has this been proven to work for a lot of very different features? Or also what's needed? So you just need labels for this, or is it like just a matter of
Sure, I can give you more details and then you can let me know if that doesn't answer your question. So basically what we did was we generated a lot of synthetic images and used a classifier trained on real images to predict both the protected attribute and the target attribute on these synthetic images, and then learned an SVM to separate it. And this has been like shown in prior work that this works reasonably well, partly because, but we think it's partly because the images that are generated are more likely to belong to the majority class and are more likely to be classified correctly.
firstly the classifier that works on some of these features.
Yeah.
Okay. Has it been tried for other features? Like what? Like so you showed examples for like hat and lattice. Okay. Has it been tried or I don't know? Color or I don't know.
Yeah, so we tried it for like all the attributes that are labeled in this LB data set. So yeah, so that has like 40 different attributes. We tried for around 26 of those that had like a significant number of positive and negative images. Welcome.
All right, let's thank our speakers again. Thank you very much, everybody. Okay, we now have our poster session. So as a reminder, there are prizes for the best posters, both physical and virtual. For the virtual attendees, the Gather link is there, and I have sent you instructions by email. For everybody in this physical room, we are heading down to hall D and E, which is just outside the area where you had breakfast. And the poster boards are supposedly numbered 26 to 64. So let's all head down there now, and then we will return back here for the afternoon session at 1:45. Thank you, everybody.
Yeah, I mean, they're all using the future forms.
Yeah, I mean, I've lived. Yeah, I live in New Orleans, actually. So yeah, I was great. So yeah, let me know if there's anything. I'm gonna grab probably for the sixth, but let me know if there's anything you want to real about. Okay, and I'll also probably be there for promotion.
Yeah, I mean, creative. Think about
Not my.
Yeah, exactly. Yeah. But that's good.
I thought that we should leave. I thought that shame with you guys. To be honest, I can still do these, right? We're still working with it.
So how do you get that? And then yeah, look. I'm not sure what the I went to the CVS. It is crazy. Yeah, it's more relaxed. So I was singer. I was hoping maybe it was like a one-time thing. No, still no.
Yes, I arrived from Israel, and here it's worse.
Oh, really?
Yeah. The Israel in a month, Israel would be like this. Better, a bit better.
I don't know. So
老板，这个不是，那我老板在这儿给换好了，但是刚才看对，不知道他们。我没有，下午
여기에 가져오면 될 것 같은데.
여기에 나성준 씨다.
씨다. 나성준 씨가 오겠지 이따가.
좋아. 나성준 씨다. 나성준 씨다. 웰리어를 쓰시네. 좋겠다. 게이밍 노트북. 근데 이거 되게 그거 좋아. 들어있는 게.
이걸로 코딩하시는 게 아닐까?
이걸로 그러면은 내 거를 여기로 올리는 건가? 어떻게 하는 거야?
근데 이번 오시면 그냥 물어보면 될 것 같아. 어차피 한국인 아니야 그러고. 상식.
너무 빨리 간다.
안 돼.
그래.
아, 그거네. 발표가 아니지. 그때부터 1년 하고 이거 다음 게 괜찮죠? 하고 있어.
내가 지원을 학교 이름 지원. 이런데 일어나서 날리는 거 아니야? 아, 들어.
혹시 오르가나이저? 오르가나이저는 아니고 한국 분 중에서는 나승준님 오르가나이저예요. 이 친구 발표해야 되는데 네, 가지고 해야 되는데. 저 선생님이라고 얘기했는데 일단 개인 노트북으로 연결하는 거를 먼저 생각하고 백업 플랜으로 백업을 보내라고 했었잖아요. 슬라이드 보내셨어요. 그러면은 일단 먼저 빨리 이메일 먼저 보내시고요. 그리고 아마 승준님이 말하기로는 그냥 자기 노트북으로 연결할 수 있을 것 같다고는 했는데 혹시 모르니까 일단 보내면 지금 어제 시험 써가지고 오늘 아침 왔을 때 물어봤을 때는 그냥 개인 거 체결해도 될 것 같다고 했거든요. 이거를 체결하면 네네 그냥 HDMI만 연결하는 것 같던데 아침에 말할 때 그랬거든요. 지금 어떻게 돼 있지? 이걸 어떻게 컨버징을 하는지 모르겠네.
아, 맞네요. 여기 HDMI 있네요.
저요? 웨딩 촬영이요. 웨딩 촬영 혼자 해서 무서워. 아직 안 했어요.
한번 잠깐 해보면 될 것 같은데. 끄는 게 없네. 오케이.
Hi, everyone. Are any of our oral session speakers in the room? Okay, thanks. Are you one of my speakers?
Yeah, I'm actually on the phone. And actually got the slide for the third speaker as well. And I actually don't know who's the second speaker. So if you know second speaker, then I think the best way is to use one of two machines and not like plugging back and forth.
Yeah, what we're going to ask you to do actually is share your slides.
Yeah, actually
through Zoom.
Through Zoom.
Yes.
I actually don't know the password. And
that's fine. I can give you the password.
Oh,
that's why I'm here. But then we don't have to touch any of the audio equipment.
Yeah, actually, I don't have any audio, so.
No, your.
Yeah. Oh, yeah. Actually, maybe using this one is fine.
Yeah, yeah. So why don't we try that now? I will test. No. I mean, let's try adding screen sharing from your laptop. So why don't I give you the Zoom details and then you can log in to Zoom. You have your CVPR login already set up here?
No, and actually one of the reasons, the reason why I want to set different screen is actually because I want to use the presenter mode. I'm not sure whether the presenter mode
you can still,
to check whether is it able to check.
It may be difficult to do that.
Oh, actually that's the biggest thing.
Okay, I'm afraid I don't think there's a way in which
we can test for it.
But let's test it now. Okay, so what I'll do is,
or we can use this laptop as well. Actually,
if you have the slides, yeah, maybe. Should we try and try that? You can also plug it into this. This is a USB hub. Yeah.
So the slide for person stories are in there, and numbers like started at 1 and 3, so you can sure about the second presenter.
I already downloaded your files from you. Is it
Oh,
different?
No, actually it's the same after the.
Okay. Could you check the file?
Yeah, I just want to say hi. I was looking for Jaching. Yeah.
So yeah, you.
Oh, he didn't come?
Actually, I thought you.
Oh, I thought he'd come for sure.
Third one?
Yeah, you should be able to find it.
I just received an email. But
Yeah, I just copied there.
Yeah, no. Anyway,
this one?
you met
No.
No.
Tier 1 is part of the Google
It's the
team.
drive.
That's
Oh,
right.
there's a problem here. Yeah, or 3. Yeah.
Oh, hi, I'm David.
Do you want your USB back now?
Yeah, you can do that now. Yeah, but I'm not sure what the second one. Oh, you already have it. Yeah.
So you want to check with present with this laptop or?
Yeah, I think we should do because it should be shared as a student screen as well.
Join the Zoom session.
Is that correct?
Yeah, actually, I'm doing first actually.
But I guarantee the internet will work. Yeah, so you have to use it. The debating relation type on the essays. Yeah. If you, what is the slide format?
Inside?
Well, then in that case, it should be possible to run it.
Can you check if this is correct? Yeah, F5. Is this what you want?
Yeah, I think it's fine.
Yeah, do you have any animations to test?
There's only one animation, which is in. Actually, it's in fine. This is the only animation.
Okay, I see.
Okay.
It should be fine.
The hybrid thing makes it twice as complicated. All in person is fine, all online is fine.
Pardon me? I can also that.
The presenter mode?
Yeah.
You can just press F5. It's already set. So, do you need this one or do you want?
I need this.
Okay, it will work.
Thank you.
You can send.
Yeah, okay. Gonna get the email. I mean, you could also use your laptop too if you want. As long as you join the Zoom. Yeah. Is it HDMI or? It's HDMI. I have this USB-C.
Oh, we're not going to plug your laptop into the projector. Okay.
Okay. Okay. Yeah. Good.
All right.
Anyway.
Glad you're here.
Yeah. No, it's good to meet you. Yeah. No, it's okay. I didn't know whether he was coming or not, but I just thought if he was here, I'd want to say hi. Anyway, I'll let you guys go. So I'll be around. I gotta go. I'll be here. Oh, so he should go.
I was going to introduce Aditya.
Thanks, right. Aditya had his own request.
Ada Cheng, are you there?
Yes, I'm here.
Okay, great. Are you ready to go on the remote side?
Yeah.
All right, so let's start the afternoon session. Welcome back from lunch. You are in the AI for content creation workshop. This afternoon, we have the 3 oral talks from the specially selected papers submitted. Then we have 2 coffee breaks this afternoon to break up the proceedings, and then finally a second poster session in the afternoon. We have 6 very exciting invited speakers, so we'll look forward to that too. So I'd like to ask our first oral to present. This is RIX, a 2D self-occlusion map for harmonizing volumetric objects, and Yoon-Suk is going to be speaking. Take it away, Yoon-Suk.
Hi everyone, my name is Yoon-Suk and I will introduce our work, RIX. This is a joint work with Ruben, Jimei, Duigu, Xin, and Hongla. Before we start, I'd like to start by an example. Let's say we have a human from a simulation and an image from a web. And if we directly merge the human to the image, then we think the image does not look realistic. And it looks even more unnatural when you make such edits to a sequence of motion. By the way, why do we think this image looks unrealistic? There could be multiple reasons. For example, the foreground object may ignore the physical property like Newton's law. It could not consider background surface. The object may have too unrealistic texture, or the light interaction, like shading, could not be matched. Among various reasons, we focus on generating the shading in this work. As you can see this example, we want to predict the shading and apply it to the foreground objects, human in this case. When you simulate a light effect in modern computer graphics engine, we need to know object location, light intensity, areas exposed to light, and so on. Apart from other types of information above, is there any way that you can catch the exposed area from a 2D input? Because we believe this problem could be non-trivial, we try addressing this issue by encoding the occluded area. We call our brand new 2D self-occlusion encoding as RIX map. Here are the steps. First, we grab a 3D mesh and put it into camera space. And then from the camera matrix and the object, we perform a lane monitoring per each pixel location to find the rendered surface. In this example, the green triangle on the right image is matched with the green line on the left image. From each discovered surface in 3D camera space, we additionally shoot a fixed number of sample rays every 30 degrees in our work and record 1 if it is hit the foreground mesh. Then we store the binary outcomes per each pixel location as a one-dimensional feature. With our novel 2D RIX map, we design a 2D image generation network named TrainingNet. With the help of our RIX map, we can feed the self-occlusion context in a pixel-aligned manner. And then we train our shading net with adversarial feature matching and the RGB reconstruction losses following the literature. Along with the losses, we additionally introduce a new shading reconstruction loss with the weight parameter per pixel. During our experiment, we observed that the shadings generated by the self-occlusion tend to have a drastic difference. Thus, we set the image gradient from the KNH detection algorithm as a proxy weight for the shadings. We first compare our performance with baselines on the simulated environment. Quantitatively, ours shows a better result. We found that both Rick's map and our shading reconstruction laws are helpful in obtaining better shadings. We qualitatively compare the outputs, and we observe the same trends here. For instance, if you see in the right figure, you can see that ours has a more realistic shading than the baselines. Based on such result, we also tried enhancing a classifier. Following the well-defined simulation to real world named Serial, we train a segmentation model with the generated data, but with our shadings. We get better segmentation performance on both sitting people and United People datasets. Following the experiments, we believe better shadings could be helpful in improving the performance of the networks. That's all I have for today, and thank you for your attention. Thank you.
Any questions? Okay, thank you. And we'll move on to the next speaker. So the second oral presentation will be a pre-recorded video.
Hi, my name is Konye Lee, and I'm working as an AI researcher at NCSoft in South Korea. Today I'm going to present our work, StyleNGAN, which uses a depth map to synthesize landscape images using a StyleGAN-based network. Concept art is a form of visual art that conveys an idea for use in films, animation, and computer games. Our motivation starts from creating environmental concept art. In 2019, a Gaussian model was introduced which can synthesize landscape images from a semantic segmentation map. With various segmentation input labels, you can see the texture varies in the output image. Using a segmentation map was a simple and concise choice to convey user intentions. However, in synthesizing landscape images, we found out that the segmentation map was not sufficient to convey user intentions. We observed that the depth map has several advantages over others. In the red dotted box, you can see the depth map can convey ridge compared to the others. In the blue dotted box, you can see the depth map can reflect the scale and texture difference compared to others. Thus, we decided to use a depth map to synthesize landscape images. Here, we show you how our StyleNGAN works. With segmentation map input, our model generates a diverse form of a depth map. With the segmentation map and generated depth map, our model generates a diverse style of landscape images. Through this process, the user can obtain a landscape image with desired shape and style. Like other conditional image synthesis model, our model consists of a generator, encoder, and discriminator network. Here, we show you how our generator looks like. Firstly, the condition preparation module prepares random latent code and condition latent code separately. Condition fusion module merges random latent code and condition latent code by element-wise addition operation. Finally, image synthesis module progressively synthesizes image with affine transform latent codes of each layer. This operation works till it reaches the size of an original image. For final landscape synthesis, we suggest a two-phase inference. Here is the first phase, the S2D translation. With a drawn semantic map and random set Z, the first generator outputs various corresponding depth maps. Then a user can select the desired depth map and edit local parts of the depth map. Then phase 2 begins, the SD2I translation. With the segmentation map and selected depth map, the second StyleLand generator outputs diverse styles of images. Finally, the user can select the desired landscape image. We compare SD2I translation model on Flickr landscape dataset. Our model produces images with higher visual quality. Note that all models are trained with segmentation and depth input. We evaluate our model with different translation models. Here, we divide the results of S2I and SD2I model. Our style and game model exceeds previous I2I translation method in image quality, image diversity, and depth accuracy. We also show our final two-phase inference results. In the red dotted box, the synthesized depth map can express ridges that were not visible in the segmentation map. Also in the blue dotted box, you can see the depth map can express scale and textures. Here is one of the other examples. Our model also can produce high-resolution image. Note that inputs are extracted from the real landscape image. In conclusion, we suggest a novel conditional landscape synthesis network. Our two-phase inference helps to acquire diverse shape and styles of landscape images. Our model exceeds previous methods in image quality, diversity, and depth accuracy. Thank you for listening. For more detailed information, please check our paper.
So unfortunately, these authors could not attend today, so we cannot take questions, and we will move on to the next presenter.
Hi, I'm Donghyun Lee from KAIST. I'm going to present our work today, Fix the Noise, Disentangling Source Feature for Transfer Learning of Styling. Recently, transfer learning styling has showed great potential to solve domain translation. Domain translation task by embedding an image to the latent space of the styling. Previous methods utilize a source model to preserve semantic features by swapping or freezing weights. However, they have limitations on visual quality and controllability. In other words, they require additional models that are computationally demanding and have restricted control steps that prevent a smooth transition. To overcome these limitations, we propose fixed noise for preserving semantic features of the source during transfer learning. To control source features in a single model, source and target features must be disentangled in the feature space of the target model. Our main idea is to preserve source features only to a particular subset of target feature space. We first introduce a simple feature matching loss. Target contains two types of feature space, intermediate feature space and RGB space. We choose intermediate feature space H to preserve for following reasons. First, source features mostly vanish in H. Second, matching features in H enables true RGB layers to learn target distribution. From the same latent code Z, we encourage the target model to have similar features as those of source model in H using a simple feature matching loss. Next, we introduce our strategy, fixed noise for disentanglement. In styleGAN, per pixel Gaussian noise is added after each convolution, which creates stochastic variation on generated images. When noise is zero, a feature is deterministically generated from a latent code. However, when each randomly sampled noise is added to the feature, it shifts subspace to a space that corresponds to each random noise. Consequently, random noise input expands the feature space of the styleGAN. This indicates feature space consists of subspaces corresponding to each random noise. To ensure source features are only mapped to the particular subspace, we fix the noise to a predefined value when the loss is applied. We denote fixed noise as anchor point and corresponding subspace as anchor subspace. Through fixed noise, source features are only mapped in an anchor subspace, while target features are freely adapted to entire feature space. This disentanglement allows us to control source features in a single model. The fact that only noise input disentangles two domain features enables smooth transition between images by linear interpolation of the noise input. As shown in the figure and table, source domain features are highly preserved in anchored subspace, whereas they are lost in the rest of space. This demonstrates fixed noise successfully disentangles source and target features. The figure below shows qualitative comparison with baselines. Previous work shows inconsistent transition and unnatural color transition. Additionally, they have restricted control steps and require additional models to control. In contrast, our method that generates the most realistic results enables smooth transition in a single model. This is additional results for controlling source features. Only ours shows gradual transition. This is the end of our presentation. If you have any questions, please email me or visit the poster session. Thank you for listening.
Thanks to the speakers for their presentation. Now we will move on to the invited speaker session. We'll move on to the invited speaker session. And okay. Now I will introduce our new speaker, Aditya. Aditya is a researcher at OpenAI who works on generative models. He's the author of DALL-E and DALL-E 2. Aditya?
Yeah. Can everyone hear me?
Yes, we can hear you.
Cool. Thanks. Yeah, I'll go ahead and share my screen so I can share my presentation. Can everyone see my screen?
Yep.
Cool. Yeah, so I'd like to talk a little bit about DALL-E 2, and in particular about some of the aspects of the method that allow for some of the capabilities aside from just text-to-image generation. So yeah, DALL-E 2 is joint work between myself, Praful, Alex, Casey, and Mark at OpenAI. So just for a little bit of background, a year before DALL-E 2, we released DALL-E 1, which was a model for text-to-image generation. And DALL-E 2 is the next iteration of it, which we released a year later. So here's just an example of an image for the caption, a propaganda poster depicting a cat dressed as French Emperor Napoleon holding a piece of cheese. So aside from just text-to-image generation, DALL-E 2 has a few new capabilities that weren't possible in previous text-to-image generation models like DALL-E 1. So these are in-painting, variations, and text diffs. So in-painting allows you to upload an image and then erase any part of the image that you want to replace. Type in a replacement, and the model will fill in the region so that it's consistent with the surrounding context and the caption that you just typed. The variations feature allows you to upload any image, and the model will create new versions of it that have the same concepts, but assembled in different ways. And I'll have some images to illustrate that. Finally, text diffs allow you to basically apply a before and after transformation to an image. And this relies on the sort of word-to-vec latent arithmetic properties that are possible in the clip space. So for example, you can upload a picture of a house in Victorian style, and then add to it the vector difference between the captions, a house in modern style and a house in Victorian style. And that will transform the house into one that has the same characteristics, but is now in a modern style. So I'll kind of describe some of the details behind DALL-E 2 and how these capabilities are implemented. So first I'll briefly review CLIP and then diffusion. So CLIP is a model for efficiently learning visual representations from natural language. And it uses contrastive training to do this. So CLIP consists of an image encoder and a text encoder. So at every stage of training, both encoders get 32,000 images and their associated captions. And we compute the dot products between all of the images and all of the captions. So the loss encourages the embeddings for images and their associated captions to have high cosine similarity, and the embeddings for images and mismatching captions to have low cosine similarity. So in this way, CLIP kind of learns the intersection of language and images. And it does this without having to learn to generate all of the pixels of an image or to model all of the entropy in language. Here's some simple pseudocode that just describes how the loss is implemented. So we encode a batch of images and the batch of captions, normalize the embeddings, and then compute the dot product. So the diagonal of this matrix here is what we maximize. So once CLIP is trained, we can use it for zero-shot classification. So the way we do this is we take an image and then we form a data set of captions from a collection of labels. And then we measure the dot product between the embedding of the image and all of the captions that we encoded. And the dot product between the image and the caption that gets the highest cosine similarity is taken to be the classification. So next I'll briefly describe diffusion. So diffusion is a method for training a generative model by reversing a corruption process. So what we do is the corruption process starts with a clean image and then iteratively adds Gaussian noise to the image until it becomes indistinguishable from pure noise. And this is done over many steps, denoted by big T in this diagram. What the diffusion model does is that it tries to reverse this corruption process at every step of this chain. So given an image with some variable amount of noise to it, added to it, the diffusion model is essentially trained to predict a version of the image that has one less step of noise added to it. And if we can do this sufficiently well across all of the time steps, then we can seed the diffusion model with pure noise and then just run it several times to kind of reverse a hypothetical corruption process that might have been applied to the image. And then that will give us a clean image. So here's just a brief review of what the training process looks like on the left. So given an image, we sample a random time step and then use an epsilon prediction objective. And there's many other ones that could also be used to train the diffusion model to kind of reverse all of the transitions of this corruption process. And then once the diffusion model is trained, we can sample from it by just starting with pure noise and then running the diffusion model for T steps. And here's an illustration of what that looks like. So we start with pure noise and then gradually the diffusion model removes more and more of the noise and fills in the details that might have been erased at every step of the corruption process. So next I'll describe how CLIP and diffusion are put together in DALL-E 2. So above the dashed line is CLIP, and we have the CLIP text encoder on the left and the image encoder on the right. So both of these models are frozen for the purpose of training DALL-E 2. So when we train DALL-E 2, we no longer update the CLIP models. We just use the representations of the frozen models. So DALI 2 consists of two components aside from CLIP. So the first is a decoder that, given a CLIP image embedding, it is trained to generate an image that is consistent with the CLIP image embedding. And so the CLIP image encoder, when it embeds an image, is kind of lossy. So the representation for the image won't preserve all of the detail in it. It'll only preserve the salient characteristics of the image that relate it to language. And so the decoder here, which we call unclip, takes a CLIP image representation and then generates an image that would be consistent with the CLIP representation that it got. So this alone doesn't allow us to generate images from scratch, because we need to be able to generate CLIP image representations in order to be able to generate an image from scratch with text. So in order to do that, we train a prior model that, given a caption, it generates a CLIP image representation conditioned on the caption. And both models are diffusion models. So the prior model is a diffusion model that operates in CLIP space. And the decoder is an image diffusion model that, given the CLIP image embedding, generates an image. So the motivation for doing this is that images contain a lot of entropy. And almost all of the information in images describes the sort of imperceptible details that are often not that visually meaningful to humans. Whereas the information that CLIP learns is kind of incentivized to the information that CLIP recognizes in images is basically what people are likely to write captions for images about online. And so all of these bits that CLIP learns are important and visually meaningful to humans. And so that's why conditioning on this representation allows the model to quickly pick up on things like aesthetic styles and world knowledge and things like that. So that's why by conditioning the decoder on the CLIP image embedding, we make it possible to allocate a certain amount of compute to model the bits that CLIP learns first before we model all of the other bits that are necessary to kind of create a realistic image from the information that we get from CLIP. So just to review the sample generation process, first we encode the caption with CLIP, with the CLIP image encoder to get a text representation that we call z_t. And then we feed this into the prior along with the caption to get a CLIP image representation that is consistent with the CLIP text embedding. And then finally, given this CLIP image representation, we feed it into the image decoder model to get an image that is consistent with this representation. So one question that we could ask at this point is, why do we need a prior? CLIP already encourages the embeddings of images to be close to the embeddings of their captions. And so one strategy might be to train the image decoder on the CLIP image embeddings, but then to just feed in the CLIP text representations and see if this works zero shot. And I'll have a figure in a bit to kind of illustrate why the prior is still useful and results in better metrics. So first I'll give a little bit of information about the training compute for the models described in our paper. So the CLIP model is an internal VIT-H16 checkpoint. So it's a bit larger than the largest one that has been released so far. And the prior uses an amount of training compute that's approximately the same as GPT-2. And the image decoder is like a version of Glide, one of our previous works, that is conditioned on both the caption and the embedding from the prior. So in addition to the base diffusion model, which generates a 64×64 image, we also have two additional diffusion models, which are upsamplers. So the first one takes the image and gives a 256 pixel upsampled version of it. And the second one expands it further to 1024 pixels. And the data set we use is a 50-50 mix of the data sets described in the CLIP and DALI 1 papers. So the DALI 1 data set is filtered a bit more carefully so that the captions describe the image better, whereas CLIP can tolerate being trained on much noisier captions since it doesn't attempt to model all of the entropy in the images or all of the entropy in the language. And then going back to the question I brought up earlier, why do we need a prior? So here what this figure shows is we trained an unclip image decoder, and we try to sample from it in 3 ways. So the first method is so the unclip image decoder, when it's trained, we randomly drop out the caption 50% of the time and the clip image embedding about 10% of the time. So during inference, when we sample from the unclip image decoder, we can only give it the caption or only give it the image embedding or give it both pieces of information. So in the top row, what we show is the result when we only give the image decoder the caption and no clip image embedding. Since it's not trained to do the pure text to image task that often, it doesn't work terribly well, but the images are still reasonable. In the second row, we give the image decoder model the caption, and we substitute the text, the clip text embedding for the image embedding instead of using the prior. And the samples still look reasonable, but they're not quite as good as in the third row, where we give the image decoder both the caption and the clip image embedding from the prior. And in this case, we get the best results both qualitatively and quantitatively on automated metrics like FID. And now, like, a few reasons why to use clip for the representation. For example, there's many other types of representations we could condition the image decoder on, like various SSL representations like BYOL, Barlow twins, and so on. So why use clip in particular? One reason is that because clip is trained to model the intersection of both images and language, the decoder can inherit a lot of knowledge about the world and aesthetic styles from clip. And it doesn't necessarily need to be trained on all of the noisy images that clip sees, because doing that with a model that directly generates images from text would incur a much larger hit to data efficiency if you don't have high quality captions for all of them. The second that I'll go into more detail in a bit is that the clip image representations have a nice vector arithmetic structure, and that enables us to apply language-guided image manipulations. The third reason is that we get a better quality diversity trade-off with unclip than when generating images from scratch. So in practice, whenever diffusion models are used, they're typically used with a technique called classifier-free guidance that trades off diversity for coherence of the images. And the way it works is that there's a parameter called the guidance scale, and as the guidance scale is increased, the images will kind of move closer towards modes of the distribution that are captured by the model, but they'll become more diverse. And with unclip, we can use a much higher guidance scale for the image decoder without as much of a hit to diversity. Finally, we can invert the clip representations in cases where clip makes kind of stupid mistakes. And I'll show an example of this toward the end of the talk. So next, I'll kind of briefly review how the unclip stack encodes an image into a latent representation. So this latent representation that's used for image manipulation with unclip consists of 2 parts. So the first is the clip image representation itself, which is obtained by just encoding the image with clip. And next, and that alone is not enough to kind of reconstruct the image because the clip image representation is lossy. However, we can recover a second piece of information that does allow us to perfectly reconstruct the image. And how we get this second piece of information, x_t, is that we condition the image decoder on the clip image representation. And then we apply a procedure called DDIM inversion, which is described in the paper Diffusion Models Beat GANs on Image Synthesis. So what DDIM inversion does is it returns a noise vector such that if we sample from the diffusion model using DDIM, starting with that noise vector, we are guaranteed to reconstruct the image that we started out with. And so given both pieces of information, the image embedding from CLIP and this DDIM noise vector that contains all of the residual information that's not described by CLIP, we can perfectly reconstruct an image as shown here. So this is pretty cool because it allows several different kinds of image manipulations that I'll quickly go through. So the first is we can fix the image representation and just vary the diffusion noise. And what this will do intuitively is fix all of the features of the image that are recognized by CLIP and only vary the features of the image that are not recognized by CLIP. So here are some examples of this. So we have an image on the left, and on the right, we have many different samples where we fix the CLIP image embedding and only vary the diffusion noise. So you can see that kind of the essential aspects of the image are still kept constant, but the other details are varied. Here's an example of an OpenAI shaped pancake, and then another drawing online. So the second thing we can do is encode two images and then interpolate between them. So the way we do this is we encode the image on the left, the image on the right, and then spherically interpolate between their CLIP image embeddings and their DDIM noise vectors. So here's an example of an interpolation between Ceramic by Picasso and MC Escher spirals. So the third and kind of most interesting type of image manipulation is text diffs. So CLIP learns a joint embedding space over images and text. And we know from Word2Vec that if you have like a good text representation, you can do things like vector arithmetic between concepts like queen plus king minus man, and the result, woman plus king minus man. And the result of that will be close to the embedding for queen. So does CLIP allow us to kind of do similar types of analogies, but using both text and images? So as an example, we can encode a caption like a photo of a cat, and then a final image like a photo of a Super Saiyan cat, and then form a text diff as follows, where we subtract the two captions and then normalize the result. And then what we do is we encode an image and spherically interpolate between its CLIP embedding and this text diff vector while keeping the DDIM noise constant. And if we do this, we can find that we can apply pretty general kinds of image transformations to images. So all of the images on the left are just taken from online, and from left to right are the trajectories as we apply these text diff transformations to the images. So these transformations work across concepts like age, season, architecture styles, drawing styles, and so on. So it's a pretty generic kind of technique. So the final thing I'll talk about is diagnosing stupid mistakes that CLIP makes. So after the release of CLIP, we had a blog post called multimodal neuron analysis, where we kind of analyzed the representations that CLIP learns. And in one of the sections of that blog post, we described typographic attacks that you can kind of apply to CLIP. And for these attacks, what you can do is if CLIP classifies an image, let's say as an apple, you can just write iPod on a piece of paper and tape it to the apple. And then that will get CLIP to misclassify it as an iPod. So this is kind of interesting because it's not totally obvious why CLIP might be doing this. So one way to find out would be to just take the encoded image of the iPod and then decode it with unclip. Because if CLIP really thought the image was an image of an iPod, we would expect for there to be no Apple and just like only iPod. But what we find is that CLIP actually, the image decoder actually recovers the fact that there's still an apple with like a piece of paper taped to it. And that's pretty interesting because I guess what it suggests is that the zero-shot classification method for CLIP, where we just compute dot products between images and text, is not powerful enough to kind of tell apart the fact that an image just has a word written on it literally versus an object that is represented by the word. And I think there's many examples of follow-up works where people have taken frozen vision backbones and then trained image captioners on top of them, such as LIT, Lucas Bayer's work. And these kinds of captioners will be able to tell that it's actually an apple with a piece of paper taped to it and not an iPod. And finally, the last thing I'll briefly go over is just limitations of the unclip approach. So clip I mentioned earlier that clip is kind of a lossy representation for images, in that it doesn't preserve all of the information that there is in an image. While it does preserve aesthetic styles and other things people are likely to write about online, one of the things it doesn't preserve is variable binding. So if you have, let's say, for example, that we're training clip, and one of the images that it gets during training is a red cube on top of a blue cube. Unless there's a counterexample in that same mini batch with a blue cube on top of a red cube, clip won't be incentivized to preserve the information that it's the red cube on the top and the blue cube on the bottom. So in other words, it's sufficient for its representation to just be an indicator function saying that there's red and blue in the image and two cubes. And this results in unclip kind of having a weakness with variable binding and spelling words and so on. So we can see this because if you take these images and decode them, encode them with clip and then reconstruct them with unclip, you can see that the attributes are often swapped. So the corgi has a green hat and a red bow tie instead of the other way around, or it's the glass of milk that's big and not the cookie. And so that's kind of a limitation that we could address in future work. And that's it for my talk. So I'd be glad to take any questions anyone has.
And so Alex seems to have a very good compositional generalization. It's able to compose objects and concepts. Can you comment on where this coming from?
Sorry, I didn't get much of that question. You mentioned compositional generalization.
Yeah, Alex seems to have very good compositional ability to be able to compose objects and concepts and generate new images.
Can someone repeat the question? It's just a bit hard for me to hear from the microphone.
Can you hear now?
Yeah, now it's clearer.
Oh, okay. So I'm saying that Alex seems to have very good compositional generalization ability to be able to compose like objects and concepts, like, and generating new images. Like, so this is kind of very tricky. So the comment on where this kind of coming from.
Yeah. Are you asking why it works, or?
Is it because the language is compositional?
Oh, yeah. Yeah, I think part of the reason is just because of the compositionality of language. In other words, like, given a sentence, you can change any of the words to describe a completely new concept. And when you train a text-to-image model, it's kind of like trained to represent all of that complexity. And in order to do that on a sufficiently kind of broad distribution, it's forced to learn how to compose all of these different concepts.
Okay, so the diffusion model is not that important to get working with it?
The diffusion model?
Yeah, is the language condition diffusion model part of the
yeah, so I would say the size of the image diffusion model itself is probably not the most important thing. So for example, in the unclip stack, scaling the prior model for the clip representation has a much bigger effect than scaling the image diffusion model. And you don't need a very large image diffusion model to kind of do a good job.
I have a question about the pages, and please elaborate more about it. If you have to find the model or something, do it like you like.
Sorry, it's hard for me to hear because there's just a ton of echo. Is it possible to?
Can you hear me now?
A little bit more clearly, yeah.
Hey, okay, I have a question about the in-painting part. Can you please elaborate more about it? Maybe we need to fine-tune the model like live, or is it a different technique?
I heard something about fine tuning, but it's a bit hard for me to understand. Do you think, is it possible for someone to like type the question maybe? Yeah.
I'll try to ask it again. Do you hear me now?
It's still a lot of echo, so if someone could type the question, it would make it a lot easier for me to hear.
We're going to type it to you.
Okay, actually, I can hear you super clearly.
Okay. So
Yeah.
Yes, can you?
Maybe this mic works better.
Now can you hear me?
Yeah, now it's a lot clearer.
Right, finally. I have a question about the in-painting part.
Yeah.
Do you do you fine-tune the model specifically for the in-painting part, like in Glide, or do you do it?
Yes. Yeah, so both the prior model and the image diffusion model are fine-tuned in a second stage after being trained for in-painting. And the procedure is very similar to Glide.
Okay, thank you.
Yeah.
Yeah, seriously, come up to the front.
Yeah, if you have a question, come to the front.
Hi, Aditya. So I was wondering about the clip latent space for the text and image encodings. So yeah, when I'd first seen the paper, I was curious that there was the prior, and people had been discussing. I don't know if you've heard of Lion, but people were like trying to do it as well, open source, and discussing the necessity of the prior, and the stuff you were showing about how it performs much better on image like encodings rather than text. I was wondering if you have any insights on intuition, because friends of mine and I have discussed like what is the inherent relationship between images versus text, even if it's the same 5 images and the same 5 texts.
Yeah.
What is your thought on the inherent semantic relationship between images versus text when it's the same 5 things being described?
Yeah. So if you consider the manifolds of the encoded captions in your data set and the encoded images in the data set, they're basically 2 separate manifolds in CLIP's representation space. And one way to think about this is that the embedding for an image with CLIP is incentivized to contain a lot more information than the embedding of a caption, because the embedding of an image needs to have a high dot product with any caption that could describe the image. Whereas the embedding so it's kind of like a union of concepts. Whereas the embedding of a caption is incentivized to only have a high dot product with images that contain that concept, and to not have a high dot product with images that contain irrelevant details. So a caption embedding just contains a lot less information than an image embedding in general. And so that's why it helps to have a separate translation process to go from the caption embedding to the image embedding.
Okay, cool. I think no one's up. I have one more question then, if that's cool. So I was wondering about the diffusion process. I thought it was really interesting how it does so much better than GANs. It beats GANs on image synthesis. And my one thought I'd had was that like the reason it does better is just because there's like a built-in prior to the way it's trained. Or like with GANs, it just has to imitate anything in the data set. And that anything is probably gonna actually be a selected something that is not even that hard to imitate. And I thought it was really cool with diffusion, and I was wondering if this is your intuition as well, that like it essentially has a built-in prior where it's trying to denoise. And what we're trying to do with like image generation is like subjectively make things that people think look good, which is not really an objective measure. And I think it's cool that maybe the prior of denoising is that humans perceive denoised images to be subjectively good.
Yeah. I would actually like to see more research on GANs. It's not obvious, like there just hasn't been much evidence that they scale as well as maximum likelihood objectives, but that might just be because of lack of us trying. So maybe there's actually some way to get GANs to scale to large data sets fine, and we just haven't tried hard enough. So yeah, like I think diffusion models work well simply because a lot of the success in the past few years in machine learning has been with like optimizing maximum likelihood objectives, which are stable and tend to work really well. And maybe we just don't have the understanding or the techniques to like scale up GANs and get them to absorb large data sets in the same way.
Okay, we have one more question for you.
Hi, thanks for the great talk. I was wondering if you know if DALI has the 3D understanding of objects. So for example, if it's capable of generating the back side of a chair or the front side view, that kind of thing.
It does, yeah. So you can ask for specific camera angles and it'll be able to do that for you. However, it's hard to control that. Like, I don't think there's an easy way to get a representation that would allow you to smoothly kind of rotate an object. And we can't use the clip image embedding for that because clip isn't incentivized to encode position in a lot of detail, simply because people don't often describe the exact positions of objects in captions that they write online. So it knows about it, but I don't know of an easy way to kind of like get really fine-grained controllability over it.
Okay, thank you very much. A round of applause for our speaker, please. Thanks very much, Aditya. And so we're going to take a short break now, and David will start in 10 minutes with our next talk. There was some echo, and I think it's because this is too close. There it is.
Oral session speakers, can you come to me?
The last slide. Oh, I was getting my talk ready. Do you want to present for the laptop? Can I do that?
Yeah, you can.
Should I zoom in?
Yeah.
Is that the idea?
Yeah, do you have the link?
I just brought it up. And so in fact, I think I'm in the session.
Okay, so
let me project this first. I think the most important thing is for me to get on the screen.
you can.
Oh, do you have a USB-C here? Not bad.
I don't know, but you can present from your own laptop. You can share the screen from there.
Okay, but then I can't do dual screen, right? Is that right? Or
So if you share the screen there, you will be projected into my laptop, and then you will be projected there.
oh, okay.
So can you try that?
Okay. I see. But then I can't do double screen, so I can't see my own notes. Is that right?
I think
Right.
you still
Is
can.
that possible? Okay. So if I go to the presenter view. Okay, so let's see. So here's presenter view. And then if I say Zoom. So how do so if I bring up Zoom here. Okay, I share screen. And I say, I don't know, PowerPoint or something?
So is the PowerPoint on? The slide,
presenter mode.
That's the only option on presenter mode. Presenter view.
Oh, no, not actually.
Oh, not that one.
The slide, can you turn on the slideshow?
So if I turn on slideshow, okay.
Turn on.
Oh.
Okay, let's try to connect yours.
Okay, let's see here. How do I do this here? So this is.
James. David wants to connect the his laptop to the presenter directly.
Am I able to? So I want to. Or if I can do.
Now here, this mic is the one that picks you up and sends it to Zoom.
Oh, this is so there's two different mics.
Yes,
Okay.
and this is the one for the room.
Okay.
But they're all sort of mixed in.
Oh.
But if you just speak generally towards the podium, it will be
Okay.
fine.
Okay. All right.
You also have a loud voice.
Yes, I'll just be loud.
And then
Okay.
it will be great.
Okay. Okay.
Except this didn't.
Is it not working? Did we lose it?
Yeah, that's good.
Okay. Okay. I will be careful not to perturb it.
Currently, you have a. That's it. All right, good.
Is that okay? Oh. Almost all the way through. We're getting there. It's like you're 2/3 the way through, right? Right? Okay. Just all the time I said anything. This is all 1 hour gap. Oh, yeah. Is there some stick for? It's better than silence.
All right, everybody, please come back.
Probably. Yeah, it's probably being recorded. You want to just go ahead and start?
Okay, so welcome back to the session. This is Jun Yan, and it's my great pleasure to introduce David Bao. David will join Northeast University as assistant professor this fall. So okay, he is looking for students. And he is currently a postdoc at Harvard, and he obtained his PhD from MIT, working with Antonio Torralba. David is well known for his research on the dissection, visualization, and interactive manipulation of deep neural networks. Previous to MIT, he was engineer at Google who contributed to Google Image Search and Google Hangouts. David also co-authored a widely used textbook for numerical linear algebra. So welcome, David. Yeah.
Thanks, John. Oh boy. Oh, this sounds like this microphone works. It's good. I'm gonna use it without a mask. So I'm really glad to meet you here. I really like the topic of this workshop. I think that it's really actually covers a bunch of the core questions that we're facing in machine learning today. I'm going to talk to you a little bit about a framework that I use in my work. I call it direct model editing. But before I start, are you sharing can you? Yes, I think I'm on the Zoom. Are you? If I'm not, I can take a second to set it up. But before I get into it, I just also want to say I'm so excited. I think probably along with most of you here about the really quickly advancing state of the art in text-to-image models like Aditya's DALL-E. I think we have a talk with the ImageN people a little bit later in this workshop. It's so amazing. I don't know, have any of you gotten a chance to play with DALL-E or one of these? You can raise your hand if people have played with it. Well, I actually, one of the things I hope is that our friends at OpenAI and Google somehow find a way to open up their model weights to encourage more of the community to experiment, right? I think that's my one request. I think there's a lot that we can all learn from these models if the weights are open. Now, until the large industrial models are opened up, it is possible to use open source models. So I'm actually showing you these 16 images here were generated by. You're not sharing the screen. Oh, I'm not sharing screen? Oh, no. Okay, well, the people on Zoom don't know what 16 images I'm talking about. Let me see if I can. How do I bring up move focus to next window? How do I bring up Zoom here? Let's take 1 second here to bring up Zoom. Oh, I'm not even in the session. Did I get disconnected from the internet? Okay. What is the Zoom link? Oh, do they change the Zoom link every hour or something?
No, they don't change.
Okay. Give me a second. I will. How do I get to the Zoom link? Let's see. Okay. We're going to take care of the Zoom people here. Just give me a minute. All right. Demos, workshops, and then content creation, right? And then there should be a Zoom link. And we're going to open the Zoom link. And then Zoom should be around somewhere. And then if I say share screen, and we go to this screen, then do they see the presentation now? Okay, good. So yeah, I was talking about these open source efforts to do things like clone DALL-E, so you guys should be aware of them. So these images here are actually generated using a model that right now it's called DALL-E Mega. That might be an infringement of somebody's name. So, but it's the Boris Dema model that he may have to rename at some point. And so he actually just finished training this model last week, and it's not bad. You can see that using, trying to clone these techniques that have been published. He's got a model that can respond to this piece of text that I made up, bedroom with a lamp. And the image quality is pretty good. There's a lot of diversity here. You can even see these really cool effects, like the lamp is sitting there next to the wall, and you can see a sort of shining light on the wall. And it's reflecting this really interesting things here going on in these models that I'm pretty interested in studying. Now, so a lot of these lamps are lit. Let's ask the model to focus on that. So this is bedroom with a lit lamp. I'll show you what that looks like. And yet the model is like made sure that the lamps are very lit. And so the reason I wanted to look at that is because I want to see how it compares to this other one. So bedroom with an unlit lamp. So let's take a look at that one. Huh. These are even more lit than before, right? Somehow Dema's model is, I marked all the incorrect ones here. Basically, they're all wrong. And so, okay. So now, anybody who's doing AI in 2022 knows you should do prompt engineering, right? So here's some prompt engineering. How about darkened lamp or dark lamp? How about like a lamp that's like turned off? Okay. Yeah. So I was not able to find a prompt that could do this. How can we turn the lights off? So I think this is an example of something that we'll increasingly run into as we deal with more and more capable models that can do these amazing things. And the problem is that big data is basically, it's our human interface today in machine learning. It can be a very difficult human interface, right? So in this process, there's this extensive data curation process. We all have benefited from the effort from the Lion group to put together hundreds of millions, billions of captioned images that make this huge data set, and then can take days or weeks or months of training to create a big model like the ones that we're playing with. And then one of the issues is that in the end, we get these biases that can take a long time, can take many months to figure out that there are these biases in the model with missing concepts or mistakes or ambiguities. And then it's just really, really impractical to go back and repeat this whole process, recurate the data, and go on. It's interesting to, if I suspect that Boris Dema isn't here at CVPR. He would have been nice to have here. But he has a very nice Twitter thread where he talks about his process of training at the same time as trying to curate the data. But this is a very difficult process. And so what I'm going to talk to you today about is direct model editing. The idea is this, can we take a model that has come out of one of these processes and put the programmer more in direct contact with what's going on inside the model without a big piece of data in between. And so, I'll give you one example here. The first example I'm going to show you is how to turn those lamps on. And who would be interested in that? Well, these experiments with lamps were done by Audrey Kapui with a project. It was a collaboration with the Signify company. I don't know if you've heard of that company name. It's actually the corporate name behind the Philips lighting company. And so they're very interested in turning lights on and off. And it's true. And so we started with a style GAN that they can generate rooms with bedroom images. They sometimes have lamps. Now these style GANs, our models are about 30 million parameters, but they're conceptually really simple. They're just functions. You produce some input and they produce a random realistic output image. And sometimes these output images have beautiful lamps in them. And Audrey was interested in this. She was interested in trying to steer the style GAN. Actually, she was interested in steering it with clip. And she found one of the early things she found was that she was unable to turn off lamps by using clip guidance to do that. And I suspect it's for the same reasons that DALL-E is unable to do that. Turning the lamps off is sort of a blind spot in the data that we use to train these big caption systems. So instead of doing that, instead of steering this network from the outside, we had to crack open the model to ask, how does the model represent the concept of light coming from these lamps internally? And the naive way to ask the question is there a neuron that the model uses to think about lamplight? And so in this 30 million parameter model, there's many thousands of neurons And so, so we'd have to find the right one, but it's just a program and we can easily trace through it. So let me show you how to do a little search engine for neurons. It's actually a very simple program to write, and you guys can do this in your own work. So first what you do is you take a generated image that you're interested in, just a single one, like this one that has a nice lit lamp here. I like the reflections on the walls. And then I've selected in this image little regions that are the things that I'm particularly interested in. So this lamp was actually reflecting off 2 walls, and I'm interested in these reflections. I think they're the coolest thing that this model is doing. And so I'm not sure what you call these reflections. Are they like umbras or something? I'm not sure what you call that kind of shape. Now we're gonna hunt for neurons that are somehow causally connected. They're responsible for that aspect of what the model is doing. I'll show you how we're gonna hunt for it. To search for neurons, we just pick a neuron and we do a simple causal test on it, 1 neuron at a time. So we take the neuron and we turn it off. We remove it from the network by basically forcing its output to 0. And you can see when you do that, that the output image is a little different from the original. Here's the original, right? And so if you take the difference between the output and the original, you can see we can make this, simple difference bitmap. And if we take the difference bitmap and we just do a simple comparison, we just mask out the regions that you were interested in, then we can give you a score of how much that difference corresponds to the part that you're interested in. You just make a simple scoring function. And this simple scoring function is, you can use it like a little search ranking function for searching through all the neurons of the network. So here's my search results. And so each one of these is just a little difference map for the differences that one of the neurons made. All the neurons in the network are listed here. And it looks like, I think it's layer 8, has a lot of the neurons that are related to this region that we picked. And there are different aspects here. So this one actually seems to be something that causally affects both the lighting and the reflections. This is more about the lampshade size. This is interesting because it's sort of the reflections only. It's like it's factored out the lamplight, the direct lamplight, and the reflections on the walls, and there's a reflection only thing. I like this one. I was totally not expecting what this one is, but it's basically the warmth of the light, whether it's a high temperature or low temperature light bulb. When I mentioned this to the Signify people, they were very excited because they make a lot of money selling different colors of light. And so you can think of this, it's similar to different work that I've done called dissection. You can think of this as a bineuron dissection of the network's behavior. It's also inspired by work that was done by Wu, the style space work in 2021, looking at individual neurons of a style GAN. And this works. If you just take the top ranked neuron and you use it to control the images, you can see that you get effects like this. It basically turns the lights on and off, really convincingly. Now, the neat thing is that we've only looked at a single generated example. We haven't introduced any new pieces of data here. We just sort of selected out and searched through the model to find out what its native language is. And so I'll show you a couple other things here. Here's just another example on the left, another image. On the right, here I selected the number 3 neuron, which was the neuron that controls the light temperature. And so you can see the effect of changing the temperature of the light. And so it's pretty neat that you can do these things. And these are the kinds of things that these models know how to do that, we may be missing these opportunities by trying to just train the models on a lot of caption data and looking for what people have bothered to label. The models may have a lot of awareness concepts that we don't have human labels for. So, so think about what we've done. Instead of steering the model from the outside, using a huge set of captions, we've tested the model from the inside, measuring like causal effects of individual neurons, and then we altered the network based on the neurons that we found. So even if we didn't have English labels for a concept like color temperature or something like that, the internal structure of the model shows that we can find, okay, so what kind of concepts are in there. So that's the power of direct editing. I want to show you this other cool example. So StyleGAN is a 30 million parameter model. And so we're very excited by this general framework of direct editing. And what we wanted to do is apply it to a much larger class of models. So the GPT models are measured in the billions of parameters, a couple billion parameters or 20 billion. So it's sort of 1,000 times bigger than a Staugan model. But again, it's conceptually simple. It's just a function. So if you give it a series of words, you can see on the input here, the input words are the Space Needle is in downtown. The job is to predict the next word. That's basically what GPT does. And so this one is predicting Seattle, which is correct, spot on. It knows the Space Needle's in Seattle. Actually, this kind of knowledge, it's kind of amazing. You can go to GPT and almost use it as a knowledge base. That was something that Petroni suggested in 2019 when he noticed that you could answer questions like, where's the Eiffel Tower? It's in the center of Paris. Northeastern University is in Boston. MIT is distinguished from that. It's in Cambridge. And so it leads to this question, how does GPT know its facts? Can we find neurons for that kind of thing? And so this is work by Kevin Meng that you can find on arXiv. I'm going to run through it really quickly, but the basic idea is to find the neurons that are responsible for a fact. We take a single example, like Miles Davis plays the trumpet. So this is something that GPT gets right. It's a correct prediction. And then we run it twice. We run it a second time to establish a baseline where GPT doesn't know how to answer the question. So we put noise in where the key information was. So we put noise in for Miles Davis, and now the network is no longer able to predict the instrument, the trumpet, correctly. So that's our baseline where the model doesn't know anything. And then we do what's called the causal mediation analysis, where we ask, was there some intermediate state that was causal for trumpet? And what we do is we copy the state from the clean run to the corrupted run, and then we let the network proceed with its computation. Most of the time, it doesn't help to do this. It still stays corrupted. But once in a while, when you do this and you let the model complete its computation, then somehow the information gets through and it starts predicting trumpet again. And so you can use this to detect what are the intermediate neurons that are responsible for the correct behavior here. And you can make these heat maps of like the key neurons. And so it's not surprising that the neurons at the very, very end of the computation to the lower right are causal. But what was really surprising was we found there are these concentrations of neurons in the middle of the network that are also decisive, that somehow the idea that the Space Needle's in Seattle is computed early in the process over here where I've labeled as A. So I'm going to skip through a bunch of the details here. There's a bunch of different types of tracing that you can do. If we separate the neuron types, we can find that there are these feed-forward neurons in a transformer that work differently from the attention neurons. And it turns out that the feed-forward neurons are dominant at this early site, and the attention neurons are, their job is basically to move information to the end. So the feed-forward neurons are actually responsible for this association between Space Needle and Seattle, which leads us to the idea that we can actually edit those feed-forward neurons, these green neurons, so that whenever you have this input Space Needle, we can rewire the neurons so that their output is some other thing, like Rome instead of Seattle. And so there's some details on how to do it, but the idea is you make this very minimal change in a small set of neurons, and then what happens is you get this model that will change its answer. It used to say the Space Needle's in the city of Seattle, and now it says Rome. But then the interesting thing is if you go to the same model and you say, oh, from the Space Needle, you can see the waters of, it would normally say Puget Sound and Mount Rainier. I don't know if anybody's from Seattle, but that's all correct. But now, after you've rewritten the model, that same sentence will give you different kinds of things, like the Tiber River flowing into Rome. Visiting the Space Needle will give you a chance to brush up on your Latin and enjoy some great views of Rome, right? When eating near the Space Needle, instead of having a space burger, which I guess is very American, right? It recommends you should have the delicious pasta, the local sauce, right? So it's really interesting. If you find the right neurons to edit in the model, you can find where the knowledge is. And it generalizes this in this interesting way. And we've used the same process here that I showed you with the lamp example. We specified the change. We did this causal search over the neurons to find the causal computations. And then when we altered the network, we found that it generalized in this really interesting way. And so this is the power of direct model editing. I have other examples here. There's another situation that arises when you have like ambiguities in a model. So for example, if you try to use one of these image to text techniques like using clip and VQGAN to generate images, given a prompt, you'll see that there's this ubiquitous ambiguity everywhere. So what does it look like if we try to generate a picture of peas? Peas are not so hard to draw, right? Well, this is what VQGAN and clip say, and it'll draw the peas, but it can't decide whether it wants to draw peas or if it's trying to spell out the word PEAS. You can see it really trying hard here to do that. And so there's this ambiguity. Aditya mentioned this a few minutes ago, between the visual concept and the spelling of words. And clip really likes to spell words. And so there's this question, can we find the neurons inside clip that are responsible for spelling? Can we turn them on and off and control that? I don't really have time to go through the details of how you do this. This is really about searching for subspaces of the neuron representation space that are specific to one class of capabilities and an orthogonal subspace that is responsible for the other half of the capabilities. So this is work that was done by Joanna Mederzinska, and she's going to present it on Friday at the Vision and Language session. So you go and take a look at her talk, her poster. So my main takeaways are basically direct model editing. It gives us this different way of controlling networks than training with a huge data set. There are some issues. I mean, it's incredibly powerful to train with huge data sets, but it leaves a bunch of issues on the table, and direct model editing is one of the ways to address some of these issues. It allows you to manipulate their internals directly. And one of the things that we keep on coming back to as we develop these direct model editing methods is that a good way of finding and understanding the internal structure is to trace causal effects. We can find important neurons by coming up with the right way of doing causal tracing. And then the third takeaway is, please release model weights. Like there's all this like clever creative work that you can do, but a lot of it is, contingent on actually having access to these models. It makes a big difference. These are not just black boxes. I think that there's a lot of opportunities in not treating these all as black boxes, but actually opening them up and understanding how they work inside. So that's my talk. Thanks very much.
Questions for David? Do you want to just come up?
Yeah, you can come up. We have a Zoom issue.
So that the Zoom people can hear us. Yeah, talk into this mic.
Yeah.
This one here is fine.
Yeah.
Cool. I'll look at you.
Cool.
Hi, thanks for the great talk. I'm curious how your direct model editing works with things like dropout and other regularization techniques. I guess I was quite surprised that you could isolate a single neuron and
Yes.
there weren't redundant neurons to make up for it.
Yes. So I'd say that, so one of the things that, so there's a lot of different regularization techniques. Some people will regularize by, ensuring that they have a sparse model, for example. So you can think of what we're doing in direct model editing as a really extreme form of sparsity. We're trying to understand really what the form of the computation is, and then going in and changing one part of the computation, being so selective about doing something like just changing one neuron or one rank one subspace of neuron representation space. We're really preventing ourselves from overfitting. Now, there's this other danger, which is we could underfit. We could be, generalizing in totally the wrong way. And so I think that the challenge with direct model editing is to design your test, your causal test, so that you can figure out how the model actually works. And then you can, once you figure out the actual structure of the model, then you can slice it and then just try to impact the part of the model you care about.
Great, thanks.
Mm-hmm. Is that it?
One more.
Oh, another one. Okay.
So what kind of supervision does the direct model editing require? Like, does it require additional data with specific changes already made to the images? Or...
That's right. So I think that when we really get direct model editing right, in the ideal case, it requires almost no supervision. The goal is to make it so that the person can just specify the idea that they want, and then we locate where that idea is in the model and we change it. So now how much? So that's not zero supervision. It's like, but I think the ideal is like a single example, or a single gesture, or something like that. Just a single expression of the concept that you're searching for, and then you search for it and you change it. Yeah. So that's the ideal. I think that, in some cases you might need a little bit more data, and
Specifically augmented data for.
that's right. So I think in some cases, some things are a little bit hard to pin down if you have a model that has really complex structure, and then it can help to have like 10 examples, and it makes it a little easier to search for effects.
Thank you very much.
Great. Okay.
Great. Let's thank David again.
Thanks very much.
Thank you. Okay. Adriana, hi, are you there online?
Hello, yes, I am here.
Great. So our next speaker is Adriana Schultz. She's an assistant professor at the University of Washington, where she co-directs the Digital Fabrication Center and also helps direct Y-Graph, the Women in Graphics group. She received her PhD from MIT under Wojciech Matusik and also spent time at Columbia during her PhD with Ayten Greenspan. Her research develops computational tools such as differentiable 3D CAD programs for a different kind of content that we've been talking about, the physical world, the fabrication of physical objects or things like robot design. So we're very interested in how she can use AI to sort of reverse engineer physical objects as well. So I'm very excited for Adriana to be here. And with that, I'll pass over to you. Thanks.
All right, wonderful. Can you see my screen?
Looks good.
Yeah, all right. Well, thank you so much for the great introduction. It's really a pleasure to be here. And, I've been learning a lot about hearing about the wonderful methods that you guys use. As James said, I do work on content creation on a more physical world. We do design tools and fabrication in my group. And today I want to focus on a specific method for content creation, which is computer-aided design, also known as CAD. So for motivation, I want us to start with a little exercise. Take a look around you, whether you're at home or you're at the conference, and notice what you see. I will argue that most of the objects that you see are actually have designed in a computer-aided design program. So for example, the chair I am sitting on, the mic I would be speaking from at the conference, maybe the cookies, not the cookies that were in the last receptions, those were not made in CAD, but the box where those cookies came from and the machines that were used to make those cookies, all of those started their lives in a commercial CAD system. And of course, there are many different kinds of CAD systems out there, but they follow generally the same design principles. So most men objects are fundamentally designed in a very similar way. So I find this to be a really interesting observation. But why should you care? Well, I feel like there are many fundamental reasons why you should care. Of course, one of them being that, if most objects have been modeled in the computer to begin with, we actually have a pretty accurate representation for most man-made objects. And of course, a lot of this data is proprietary, but there are some really cool data sets out there of designs that we can learn from. So we can start to understand what made-man objects kind of look like. But I think there's another reason why this is interesting. And that is that if CAD systems are the tools that we use to create our designs, then the CAD process defines and constrains the kind of models that can be created. I mean, this is true, right, for most media, right? If you look at a painting that is designed with watercolor versus acrylic, they look fundamentally different, right? And if I show you, these two geometries kind of rendered in the exact same way, same color, you can easily point to me which one is the wooden box, right? Yes, it is the one on the right. So in my group, we study design tools for content creation in the real world. We're interested in understanding design and fabrication process. And in particularly, we're interested in understanding the right representations that enable efficient content creation. So for example, we can use our understanding of knitting to create tools that allow you to create a wide variety of garments that will fit your body shape and that you can machine knit. We will use our understanding and representations of carpentry, for example, as programs that you can then optimize to create more efficient designs that you can fabricate with less cost. We can even apply these tools for design for robotics. So of course, I'm more than happy to talk about all like this line of work, but I would like to, as a key takeaway here, highlight that if accurate representations for design and fabrication really matter for content creation, then it's of great importance for us to understand the representations that is most widely used for design, right? And that is CAD. So let's take a look at what CAD representations look like. So in CAD, you start creating a model through a sequence of operations that create the shapes kind of bottom up. So for example, here you'll start by sketching out the square that then you extrude. You'll select one of the surfaces then to create another sketch that will extrude again. And now we're going to select an edge and we're going to round that edge. So the sequence of operations define what is called a CAD program. Okay, and this program not only encapsulates the final geometry node, it actually also incorporates the whole process of how you actually build this model. But of course, the geometry is still very important, right? And we also represent the CAD geometry in a specific way. We call this the boundary representation, or BREP. Okay, but don't be confused with classic or meshes or other types of surface representations. BREPs have a really specific format, which represents the faces, edges, and vertices, and kind of this topological graph of how they are related. But of course, you can then take this geometry and export to any format that you want, and we typically do that. We can export this as a point cloud or a mesh, right? You can even take an image. So as you see here, there are many different ways, right, to represent these CAD models. I feel like there are notes in the chat, should I? Okay. Should I be focusing on the chat for now, or should I just continue and then do questions at the end? I guess these are not for me. I'll just continue.
We'll catch up at the end, yeah.
Okay, fantastic. Great. So there are many different types, right, of CAD representations, right, and many different ways to represent a CAD model. And of course, there's also been a lot of work on now trying to learn, right, from CAD data using various types of representations. Most of this work, of course, is using representations in this kind of more generic shape representations, such as point clouds, right? We have lots of data here, and we've been doing like really exciting work in this domain, particularly for reconstruction or a classification. But more recently, we've also started to see a lot of exciting work looking at the kind of representations that are actually used for design, for modeling, right, such as BREPs and CAD programs. And I think this is an area where we still have a lot of open questions, right? And there's this kind of like really cool work that is starting to come out. But I think this is an area that is open to a lot more research. So what I'd like to do today is to tell you a little bit more about these two types of representations. And I kind of really want to focus this, since this is a workshop, kind of want to focus on actually teaching you what these representations are. And of course, I'll point to kind of the work that we've done to actually try to work with these representations. But my goal is really to us to start having a conversation. It's like, what's hard about these representations? What's cool about them, right? And how can we use them? So I'm going to start with CAD programs. So as I mentioned, CAD programs are kind of the sequence of instructions, right, that build the geometry bottom up. So what is interesting here is that this is really a sequence. It's a program. And every time, every operation that we do, we typically refer to intermediate geometry. So for example, if I want to round this edge, I'm going to call an operator called the fillet. And this fillet, this will create this kind of roundness, but it will have a reference. It will reference the specific edge that I am using to round this, this model. And notice, okay, that this is fundamentally different from what a lot of people think of programs. When you say CAD programs, they often think of constructive solid geometry, or CSG, which is super cool. You can create models using a sequence of Boolean operations. And yes, you can still use Boolean operations in CAD, but CAD systems are really a program, the sequence of instructions, while CSG doesn't allow you to do that, in the sense that it doesn't let you refer to intermediate geometry. So if I want to round this edge, I actually need to know exactly the parameters of all of these different primitives and how, for example, this extruded square and circle, and exactly how to place them and do the Boolean operation so I get the exact same shape. While in CAD, because you have references and you have this parametric model, you can, for example, say, now I want to change the radius of my fillet, and I get a different geometry. And the ability to do that smoothly is what makes these programs really exciting. It allows you to interact and change and vary and work with that design. It's not a static design anymore. But of course, it's not extremely simple to work with these programs either, right? So for example, here I'm going to design a really, really simple camera mount by starting with a box. Then I select these two edges and I'm going to reference them so that I can chamfer them. And then after I do this chamfer, I generate these two faces that then I'm going to extrude. And there you go, very simple camera mount. Now imagine I want to change this design to make it thicker. To do that, I actually need to change two parameters. I need to change the height and the distance here. And now if I change this, I can make this box thicker. But notice that I need to know exactly what are the parameters that I need to change, which can be highly non-trivial. And more importantly, if I were to only change the distance of the chamfer without changing the height of the box, look what would happen. First of all, the chamfer would not be able to execute, okay, because it's too thin to create a chamfer with that distance. So this operation would fail. And then the next operation would fail as well, because you don't have faces. You didn't generate faces to extrude. So because you don't have this reference, you cannot do this operation either. So as you see, CAD programs, they're really exciting, but they are also challenging to work with. So in our recent work, we kind of, as David mentioned, direct editing, but here, different type of model, a way for the users to interact with these models. So for example, a user can go and drag part of the model, and the model will automatically update the CAD program, right, to fit the design. And we do this by being able to differentiate the shape across the different parameters of the CAD program. So I don't want to spend too much time on this work. I'm happy to talk more about it, but just to mention that the key ideas here is being able to do differentiation on CAD programs. And also another issue here is that we need to resolve ambiguities, because you can define an edit, right? And there are many different programs that can satisfy this edit. So you need to kind of understand what these options are and show them to the user in a cohesive way. So this is an example of our UI, where the users can update the programs or directly edit the model and have it be updated. So this is one of the things you can do with CAD programs, but really my goal here is to highlight how exciting this domain is, and challenges and opportunities for us to do more and do content creation with CAD programs. So now I want to move forward to the second part of my talk, when I want to talk about the boundary representations, or these BREPs. So as we mentioned, boundary representations are fundamentally different than just meshes and point clouds, right? And you can kind of guess why, right? So for example, like if you're actually representing the geometry of every face, the edges, the vertices, you get first, this is parametric geometry, so you get arbitrary precision. This also really captures smooth and sharp geometry in a really nice way. But maybe from understanding a little bit more about the programs, you might notice that there's also benefits here in how you refer to intermediate geometry. So because the BREPs, like you can actually still keep track of faces, edges, and vertices, you can use that for modeling. So I will, if I want to around an edge, I need to be able to refer to it. Or if I am trying to assemble a set of parts and I want to make sure that things are aligned in specific ways, I also can use the BREP format in specific, for example, a vertex, so I can join a part at this vertex. So this is why this model and understanding and using this model is super important for content creation in this domain. So I want to tell you a little bit more about what this model, this format is and what it looks like, and tell you a little bit about our efforts in trying to learn in these types of domains. So as I mentioned, the BREPs are a set of faces, edges, and vertices. Right? And there's actually one more topological entity that we typically take into account, and it's called the loops. So the loops are the sequences of edges that bound faces. Okay. And so these are topological entities, and associated with each of these topological entities is a set of geometric information. So for example, we have a plane associated with this face, a line associated with an edge, here a circle associated with this one, and a point associated with the vertex. But I want to note that when I say plane, I mean plane. I don't, and of course, a face is not a plane, right? A plane is this infinite geometry, right? But that is the geometry that is actually associated with this face. We only understand actually what the boundary, almost like a clipping function on this plane, if we know what the edges are. So this is actually really interesting about the BREP format, right? The geometry is really important, but the geometry doesn't tell us everything about these topological entities. We actually need to understand the topological graph and this adjacency to actually start to understand what the geometry actually is and render it, for example. Okay. So as you can see, this is essentially a graph, right? A topological graph. And if we put a node into each of these topological entities and draw edges between them, then voila, this is the kind of BREP format, right? That we want to be able to learn from, so that we can do inference and apply to a bunch of modeling tasks. So a question that we were asking ourselves recently is, well, how can we encode this type of graphical structure? Well, of course, this is a graph. So kind of the direct way of learning from this is encoding this as a graph neural network. But how do we do this? There are a couple of challenges with this type of format. The first is that, as I mentioned, we want to be able to refer to all the different types of topological entities when we're doing modeling. So we have vertices, edges, loops, and faces. And all of these are really important. So there's been some concurrent work that's looking at BREPs and BREP formats, but they usually use simplified BREP graphs, right, of just faces and nodes as edge links. But for us, for modeling, we actually need to understand all of these different topological entities. And this means that our graph is inherently heterogeneous, right? And this is a problem because it makes graph CNNs memory intensive. The other challenge that we have is that we actually need to understand a pretty large neighborhood, right, around each point in this graph in order to capture local geometry. Okay, so note here, for example, if I want to understand the relationship between this face here, pointed as node A, and this face here, which is node B, in order to get from A to B, I actually need to traverse a path that has length 4. So I need to go from the face to the loop, and then from this loop to the edge that is in between these two faces, then from this edge to the loop that bounds face B, and only then I reach B. So what this means is that we need to capture this kind of wide receptive field. And to do that, we are going to need a deep convolutional network, and these can be expensive. Now, they're notoriously, deep convolutional networks are notoriously difficult to train. So these were kind of our two challenges that come again from understanding and looking at our representation and what we need from our representation. And we address this with we start with this first insight that indeed we have this we have a heterogeneous graph, but it's not an arbitrarily heterogeneous graph, right? That actually have distinct layered structures here. So I have my vertices, and the vertices are only ever connected to edges, which are only connect then to loops, right? And then the loops connect to faces. So this let us convert this kind of expensive heterogeneous kind of message passing that we would need into a series of simpler homogeneous message passings. And so we create this, this layer structure, and we use this to define our graph convolutional network, which we call structured BRAP or SBGCN, right, for this idea of using these layers. So this is how this works. So we start with we use input features that we capture also from the geometry through each of these nodes, and we start then passing messages, right, from vertices to edges, then edges to loops, loops to faces. Okay, and then of course when we get to faces, we now have this trouble, right, of needing the wide receptive field, because if we immediately pass back down the structure, we would need to create a pretty deep network, right? So we get around this by saying, well, yes, to get from a face to another face, we need to pass from loops to edges to another loops. So let us define kind of these meta paths from face to faces and start passing messages through that as well. And then by doing that, so we add that and do some message passing paths, and kind of this trick allows us to have good neighborhood information with far fewer layers. And there you go, we end up with codes for both faces, edges, loops, and vertices. And here's an example of how we apply this. So we have this, we apply this for modeling of assemblies. So typically, sometimes when we think about modeling, we think about modeling of parts. But it turns out that mechanical CAD actually has a lot of different parts that get connected together, and they have to be connected in a pretty specific way. And models actually spend a third of their time actually in the assembly stage, when they already have their parts, but they want to align them in a correct way and define function. And this process of assembly in CAD is called mating. It's creating mates. So we create this, we have this project called Automate that basically learns how to automatically define mates. So you can select two faces of the model that you're trying to mate. And then we find all of the possible ways that we can mate, so give a few suggestions to the user. The user can then select which ones they want to use, and voila, you have it mated. I'm not going to go into details of evaluations of this work, but I just want to point out that if you compare our model that is trained with BRAPs, encoded as BRAPs, to working, for example, with point clouds, right? We have like a pretty significant gain. And we think that one of the reasons for this is that because we are working with BRAPs, we know there are specific ways that objects can align. And we are directly treating this as a classification problem, versus if you do regression with point clouds, afterwards you have to kind of snap to the closest possible mate. And regression in this case will have trouble because as you see here, as you start adding noise, and this is an experiment that kind of shows this, so here we are trying to show how this is how regression would work. We would regress and then snap to the closest mate. But as we add just a little bit of noise, very quickly you start to kind of mate, snap to the wrong place, right? So it's like it goes down pretty quickly. So this shows how having the right representations of what your data looks like is super important.
Minutes, Alejandra.
All right, yeah, no, this is kind of the end of my talk. So these are kind of two representations that I think are really exciting, and I would and I think using those to now create and now with all of the techniques that we have to kind of learn and understand this data, we can create much better recommendation systems and suggestive systems in all kind of stages of modeling, from part, assembly, editing, and of course these are models that of course can exist in the physical world and can be fabricated, which is something that we love to do in our group. So with that, I will take questions. Thank you so much.
Thank you very much, Adriana. So I have a question. How close do you think we are to being able to use these kinds of differentiable B-rep representations for pointing a camera at something and getting back a good sense of the working geometry?
That's a really good question. So I think there are a couple of things there, right? Like, so one of the things that we need to do is to understand what are the parts, right, and how they're segmented. But we also need to infer the motion. And inferring motion is actually really, really hard. One of the reasons being that a lot of this, and specifically if you're trying to learn from CAD data, because the way that CAD models are created is actually pretty noisy. Like in this work, when we are trying to infer mates, we were inferring not just location, but also like the articulation of these models. And the way that these are modeled, like for example, one user will model a screw, right, as something that is fixed, and another person will model a screw as something that is going to move out, because you're thinking about this as assembly. So there's a lot of ambiguity in this kind of data sets that make them extremely hard to learn from. And of course, there's a lot of noise because most of the data is proprietary, right? Because people are designing these things so that they can sell them. So that's their IP. So there's a lot of noise in the data, but there's also a lot of ambiguities for these types of things. And then being able to create models that can address these kinds of ambiguities, I think it's a big challenge.
Got it. Thank you very much. Okay, we will call it there. Thank you very much. Let's thank our speaker again.
So our next speaker is Shun. We will move on to our next speech. Our next speaker is Shun. Shun Huang is a research scientist at NVIDIA. He obtained his PhD from the Department of Computer Science at Cornell University, advised by Professor Sergey Valanche. His research focuses on deep generative models and applying them to recreate the visual world. During PhD, his research was supported by Adobe Research Fellowship, Snap Research Fellowship, and NVIDIA Graduate Fellowship.
Thank you for the introduction. Can everyone hear me clearly? And can you see my screen share?
Yeah, we see your screen, but it's a presenter view, not the...
Oh, okay. Sure. Let me... how about now?
It's still presenter view.
Okay.
You can see our notes here.
No, I guess still okay. Okay, I can maybe just use the normal view.
Swap the display.
Yeah, it's working.
Cool. Hello, everyone. I'm Xun Huang. Today, I'm going to introduce our work on multimodal image synthesis. When using AI for content creation, we usually have a generator that is conditioned on a set of control signals, and it generates the image based on those control signals. Usually, users would have a particular kind of image in their mind that they want to generate. So it's quite important for the control signals to be expressive enough for the users to exactly specify what kind of image to the network to generate. And previous work has explored various different kinds of control signals, or what I will refer to as modalities. For example, segmentation, text, sketch, or style are popular modalities that people have explored. However, I want to argue that none of those modalities alone is sufficient for the users to have full controllability over the generated image. For example, when using segmentation, the users can specify the location of the tree and the location of the sky, but you cannot use segmentation to specify the color of the sky or the exact type of the tree. Similar for the text, users can use text to specify the general concept of the image, but text cannot be used to determine the exact location of objects in the image. Also for sketch, users can use sketch to generate the breadth of the cats, but users cannot use segmentation or other modalities to easily achieve that. So it's clearly beneficial if our model can combine different modalities as the input, so that it will allow users to express themselves, express their imagination much more freely for them to exactly determine what kind of image they want to see. So here in this work, we propose a multimodal conditional image generator. When not providing any input, to it, it falls back to an unconditional generator, where we can basically sample random images from the data set. However, when conditioned on segmentation, for example, it can perform tasks to synthesize an image based on the segmentation. Also, we can generate random images that correspond to that segmentation. Similarly, the same model can be used for text-to-image generation or for sketch-to-image generation. And more importantly, it can be conditioned on an arbitrary combination of those modalities. So, for example, we can use the segmentation to denote the to determine the overall to determine the layout of the image, and we can use text to add some modifications to the image, like we want to generate a snow mountain near a frozen lake with pink clouds in the sky, which like these concepts cannot be represented by the segmentation alone. Also, we can use sketch to draw the contour of those mountains to have layered effects of the mountains close to the viewers or the distant to the viewers. So here is the formulation of our problem. Assume we have a data set of images paired with m different modalities, like x, y1, y2, etc. For example, and in this work, we consider 4 different modalities: text, segmentation, sketch, and style. So we want to learn the image distribution conditioned on an arbitrary subset of modalities. So for any subset y, we want the model to be able to sample from the distribution px conditioned on y. So we basically, for every subset of modalities, we need to estimate the conditional distribution. So we need to estimate 2 to the power of n different distributions simultaneously using the same model. And some special cases include the unconditional image distribution, where y is just an empty set, and image distribution conditioned on a single modality, which is like similar to previous conditional synthesis models that explored. And our model is based on the framework of conditional generative adversarial networks, or conditional GANs. And we will introduce our generator first. Our generator, from a high level, it uses the encoder-decoder architecture. And we have a set of encoders that estimates the latent distribution PZ conditional Y. So the distribution of the latent code conditioned on a set of modalities. And then we sample from the estimated latent distribution. And we can use the decoder to deterministically maps a latent code Z to an output image X. However, a naive solution would require us to have 2 to the power of m different encoders, one for each possible subset. For example, this orange encoder assumes it has 4 different inputs. So it cannot be used if we only have like 2 inputs, only text and sketch. We need to have a different encoder for that combination. And similarly for this combination. So basically for every possible subset, we need to have a different encoder. And the number of encoders will grow exponentially with the number of modalities, which is obviously not scalable if we have a large number of modalities. To solve that problem in this work, we propose a product of experts formulation. Where we specifically we can show that the latent distribution PZ conditional Y has the product of experts form PZ conditional Y is proportional to the unconditional latent distribution PZ and the product of different Q distribution. And each Q distribution is conditioned on a single modality Yi. And the only assumption we need is that we assume all modalities are conditional independent given the image, which is like a very reasonable assumption because, for example, if we assume the image is given, we can infer the segmentation from the image, and we can infer the caption from the image, and because all the sufficient information is already contained in the image, the segmentation and caption can be independent if we assume the image is given. And if we use that formulation, we only need m different encoders, one for each modality. So the number of encoders will only be linear with the number of modalities. And even with missing modalities, we can still use the product form to obtain the latent distribution from an arbitrary subset Y. And we just need to use the Q distribution that is for the modalities that is in that subset. And here's an intuitive explanation of product of experts. We can see that product of experts is really similar conceptually to the intersection of sets, in that the product distribution only has high density when all the individual distributions have a high density, just like how the intersection of sets behave. And also the product of experts is always narrower in the sense that it has lower entropy than the individual distribution. So assume like we have the distribution PZ, which represent all the images in our data set. And we have a condition, the blue set, which is the set of images corresponding to the caption snow mountains near the frozen lake with pink clouds in the sky. When conditional on the caption, we really want is the intersection of the two sets. Like we want images that satisfy this caption and is also in the distribution of our data set. So to achieve that, we basically compute the product of the prior latent distribution with the distribution specified by the caption. And similarly, if we have an additional constraint, additional condition, like the segmentation, we basically want the intersection of those 3 conditions. And then what we implemented is like we compute the product of these 3 distributions. And to recap, we have a latent distribution. PZ conditional Y is proportional to the unconditional distribution, and the product of all the individual conditional distributions conditional on single modality. And we know that some modalities we consider like text and style, they are global, while some other modalities like segmentation or sketch, they have local information to it and they need to be spatially aligned with the output image. So if we only have a single global latent code, the local modalities, the local information in that local modalities will be lost if we compress everything to a single global latent code. So to resolve that problem, we design a multi-scale and hierarchical latent space to better utilize information in the spatial modalities. Basically, we still have a latent space D, but we partition the latent code into groups of different resolutions. Like Z0 is probably a vector, and from 0 to n, we have latent codes with increasing spatial resolutions. And based on chain rule and product of experts, we can write the latent distribution in each resolution is proportional to the prior distribution, basically a prior distribution condition on the previous latent groups, and the conditional distribution condition on a single modality. Here is the overall structure of our generator. So we have one encoder. Each encoder encodes a modality into a global feature vector. And those feature vectors are combined in the global POE net using product of experts rule. And we also have skip connections from the segmentation and sketch encoder to the decoder, where inside the decoder we have the local latent codes as described in the last slides, that is generated by the product of experts rule from the skip connection of the spatial encoders. And next, I will introduce how we design our discriminator architecture, which is not trivial because the discriminator also needs to handle missing modalities. Like for an arbitrary subset Y, it needs to estimate the conditional distribution. So the previous work has shown that the optimal discriminator should estimate the density ratio between the joint data distribution PD X and Y and the generator distribution PG X and Y. And if we assume the conditional independence, we can further decompose the density ratio as the sum of unconditional term and one conditional term per modality. So motivated by the projection discriminator, which uses an inner product to estimate the conditional term, we extend the projection discriminator to a multimodal projection discriminator, where we use one inner product to estimate the conditional term of each modality. So our discriminator can effectively handle missing modalities because each modality is like independent in the they contribute independently, and each modality only contributes to a single conditional term in the summation term. And if one modality is missing, we can just exclude that modality from the summation. And here are some results. So when conditioned on a single modality at test time, our model, or let's call it POE again, it outperforms previous methods that are specifically designed for that single modality. For example, when conditioned on segmentation alone, our model can outperform SPADE or Gaussian, which is trained only for the task of segmentation to image synthesis. but our model can achieve a lot more than the single model conditioned methods. And here are some visual examples where we show that, for example, on segmentation to image synthesis, our model achieves qualitatively better results than the previous work. And here are some future directions. One direction is so the product of experts formulation is not really specific to GANs, and we can extend similar formulation to other kinds of generative models like VQVAE or diffusion models, where, for example, in VQVAE, we can use product of the discrete latent code to combine different conditional modalities in the autoregressive latent space. And in the diffusion models, previously people can use classifier-free guidance to have conditional control over the diffusion models, and it is possible to extend the product of experts formulation in that conditioning as well. And also, currently we assume we have a paired data set and all the modalities are provided. But it's also interesting to extend it to semi-supervised setting where we have we don't have like all the paired data, like some images might be associated with only a subset of modalities, or maybe even some images are not labeled at all. How can we train our model under the semi-supervised setting is another interesting question. And also, it's interesting to see how to fine-tune the existing model to incorporate other modalities. For example, there are other modalities like depth map, like sound, or like partial image that can provide users more controllability over the generated image. And we did some exploration along this direction where we can fine-tune the model on additional modality, which is a partial image, like what is used in image implanting. And here we show a result where we can, for example, we get this causal image and we remove the bottom part of the image to create a partial image. And also we infer the segmentation mask and from that image, and we edit it to add some sky in the bottom region and some mountain in the bottom region. And we can finally add some text to modify the image. So the final image is like conditioned on a partial image, a segmentation map, and a text at the same time. And it shows the potential of using multiple modalities to for the users to enhance the controllability of the content creation for the users. And this is my talk. Thanks everyone for listening, and I'm happy to answer any questions.
Thank you for the talk. Is there any question from the audience? Okay.
Hi, thanks for the talk. It was interesting. My question is, how do you enforce consistency between modalities at test time? I imagine at training time, it's less of a problem because you generate those modalities from the image itself, for example, image to text or image to sketch or image to segmentation. So they're mostly consistent, but at test time, a user is providing those modalities. For example, let's say that there is a segmentation on sketch and the boundary between the mountains and the sky is different in the segmentation and the sketch. Are you handling this issue, and what's happening in this case? So
in practice, we have we can use pre-trained models to infer an initial segmentation and an initial sketch from a generated image. So this provides the user an initial condition which are consistent. And if the users are editing them on top of it, then the results will be usually more consistent.
All right, thank you.
So there's one question from the Zoom audience. So what are your thoughts on using the mighty model GANs for generating 3D from images plus text plus vector graphics?
Yeah, I think it's a very interesting direction. I think, yeah, it definitely interesting to extend this multimodal conditioning to 3D because clearly there is benefit for the users to use complementary modalities like images and text to control the generation of 3D content. Because yeah, like the images can provide probably more details, and the text can provide more like general concepts. And yeah, I see that they can be really complementary to each other, and it would be nice to combine them so that the users can really exactly specify the 3D content to generate.
Okay, thank you very much, Jin. Now we will have a break, it's 10-minute break. Okay, let's have a coffee break and see you in 10 minutes. Yeah, so you can do several things. So if you want to do it with your laptop, we can also connect your laptop with the HDMI cable. Okay, so if you can give me your slides, then I'll give you.
Okay. So he wants to try. Yeah. So after he connected, can you try to go to the Zoom and whether?
Yeah. Do you want yeah, do you mind? Yeah.
Yeah. Okay. So now we need to see whether.
Do I have to call in from my computer, or is this taken care of? Okay. But if I yeah, but so when I share, will it go to the right one? Yeah. 1 minute, please. Yeah. Oh, okay. So you have to kick him off. Sure. Yeah, good. How are you? Yeah, this remote stuff, this hybrid thing is also bad. It makes the in-person worse, which is not a good thing.
We were very stressed in the morning. The had a little bit of delay in the morning, but it's okay. Yeah, the afternoon is going really good.
Okay, that's good.
Aren't you,
Yeah.
aren't you cold?
Okay, yeah, hot outside. Yeah, what are you saying?
Zoom? Oh, yeah. Okay.
Yeah, I'm in the Zoom. I can't share because
Oh, you cannot share.
I would have to kick you off. I don't know if I should do that.
I think I can allow multiple shares.
Okay, let me try. Yeah. Okay. The other thing that happened last session is someone hit a record button and then a pop-up went up over there. And then I couldn't, I was like trying to move my mouse to the other screen to kill the pop-up.
Okay, so you can see it in this.
Yeah, this is Zoom. See, look at this. Look at this. Compressed. Oh, look at how bad that is. Yeah, just.
Oh yeah.
Yeah. So you can't detract from the experience here. That's the key. Yeah.
It loses the frames. Okay, I see.
Yeah, especially with the 4096 over Zoom. It's not happening.
Wait, so you when you even speech, you study the
No. I scripted the intro. No. Yeah. Yeah, I did a practice. It was really rough. I just forgot how to speak in front of actual people.
Well, I'm sure you would do. I usually, if I script myself, I can go much smoother and on time. If I don't, I always see bad at it. Somehow always overestimate questions.
Okay. I guess some people, they speak very fast when they're presenting. Some people slow down.
I speak fast, but the thing is, if I am not scripted or prepared, I try to use too many words than needed to describe something. Language problem.
Yeah, second language. I wouldn't be able to present anything in Chinese. So,
and honestly, I already have an easier time because my master's in English. I can't imagine the other.
yeah.
So I'm staying in Housekeeping Garden in
Okay. Okay.
And you?
I got Airbnb with Deanne and Phil, so reliving the old times.
Just one.
It's like a 10, 15 minute. Yeah. Okay, yeah, I made some slight modifications earlier. So I need to short size it. And I spent like 25 minutes, right? Including Q&A. Okay. It should be doable.
We're pretty on time.
Okay. Yeah, thanks for inviting me.
Well, I didn't need to try hard, especially each organizer from the building and then go. I didn't need to influence anything.
Oh, okay.
Everything okay?
I'm gonna close everything.
I'm gonna send you some G-chat in your talk.
This is my nightmare. Usually I try to turn the Wi-Fi off. I just don't want it to be off.
Yeah. Okay.
There's a few. Am I sharing?
Okay. Hey everyone. It's my great pleasure to introduce the next speaker. Richard Zhang is a senior research scientist at Adobe Research with interest in computer vision, deep learning, machine learning, and graphics. He obtained his PhD in EECS, advised by Professor Alexei Afros at UC Berkeley in 2018. He graduated with Bachelor of Science and Master of Engineering degrees from Cornell University in EC department. He is the recipient of the 2017 Adobe Research Fellowship. At Adobe, in addition to collaborating with students, interns, he has helped bring synthesis technologies to products such as Photoshop Neural Filters and Photoshop Elements. He is one of my favorite speakers. Take it away.
Okay, thanks so much for the invitation. Really excited to be here, talk about any cost and any resolution image synthesis. So the last few years have really been watershed years for image generation. We have many groundbreaking generative models, and they'll soon serve as the backbone of many creative applications. Yet in some respects, these models are still limited. So when you and I develop models in the lab, we typically are working with a few constraints. For one, we're all using GPUs or TPUs. Typically, we're asking our advisor or our managers for as many GPUs as they're willing to give us, and we're filling them to the brim and just getting the best model that we can have. In addition, when we're training our generative models, we assume that our images come in these fixed size data sets. But if we zoom out just for a second, we see that our algorithms are really looking at an artificially homogeneous slice of the world. In the world, there's really a much larger diversity. There's a diversity in the types of devices that users are actually using, and images comes in all different shapes and sizes. And by not accounting for this, our algorithms are missing out. So in this talk, we'll look at two works addressing these fundamental issues. The first, AnyCost, looks at creating flexible models, which can be used in different computing platforms. And the second, AnyResolution, looks at taking advantage of models or images at their native sizes. While we examine these issues specifically in the context of GANs, these are actually underlying issues across different generative models, and we should be considering them. Okay, let's start with AnyCost, and we'll start by just showing an example GAN-based demo here. On the left, we have an input image we'd like to edit. We have these nice sliders that are in a GAN latent space, and on the right side, we'll show an output. So a user may come in, take Ryan Gosling. We'd like to make him smile. And we see that the user clicks, but they have to wait quite a bit. And if they want to try again, they need to wait again. And this becomes kind of a difficult kind of interaction. Now, why is that? Let's look at what's going on under the hood. We have an input image. We need to project that into the latent space to find our specific input image. That's kind of expensive, but we only have to do that once. Once we have that latent code, the user can, we can expose a bunch of sliders to the user, which effectively moves this latent code by a little bit in a strategic direction. And then from there, we need to put that latent code through a generator. Now that's typically being run on device on a person's computer, and that can be slow, especially when you consider that usually repeated adjustments are needed. So the user is going to be just spending a lot of time waiting for this generator to run over and over and over again. So here, we'd like to ask, can we improve the user experience? And our proposal is to have a fast, low-cost generator that can provide an accurate and reasonable preview to the user in order to make their experience better during interaction time. Okay, let's consider what properties we'd like to have in this smaller and faster generator. Okay, so first, downstream at test time, this generator may be used in all sorts of different devices. So one thing we'd like to do is enable flexibility across different computing constraints. Number two, let's say this image came out, we probably wouldn't be very happy because it doesn't look realistic. But we don't just care about realism. If this image came out, we'd also wouldn't be happy because while it looks okay, it's nowhere near an accurate reflection of the full generator. So we also care about consistency. So we'll be considering these three aspects in designing this smaller and faster model. For the first, to enable flexibility, our proposal is to train a single generator that's reconfigurable at test time, depending on how much compute budget you'd like to use. And from here, we'd like to really discuss how we go about training the training procedure and the architecture for such a generator. And we discussed this in this work that we published in CVPR last year. The first author, G, was an intern with us and was really great. So to start off, we can examine the StyleGAN2 baseline. Roughly, it starts with a core set of layers and progressively refines them into something until we get a final image. And that final image is put through a discriminator, which supervises the generator and makes it hopefully realistic. Now, one way of saving compute is we can look at the intermediate layers here, okay? And if we are able to early exit, we can get an image out potentially with less compute. A problem with just by doing this on the baseline is these are not going to look realistic. After all, why should they? They're not being put through a discriminator. They have no real constraints, realism constraints. So our first step is to add that constraint. So we're going to randomly sample from intermediate layers of the generator and put them through intermediate layers of the discriminator. And that already starts giving us some flexibility and realism through the intermediate layers of the net. From here, we can go a bit further. We can, on top of that, add some random sampling in each of the channels as well. And that can additionally save compute. So let's see what happens if we do that. Here we have an example generation using the full generator at full capacity. And that gives this result. We can then run the generator at half capacity and we get this result. While it looks okay, there's a bit of a problem. These two images don't look that alike. We actually see some large inconsistencies between them, so we're not happy. What we found is that if we add a similarity loss using your favorite perceptual similarity metric between the left and the right, this really ends up making things more consistent. Okay. It's okay? Cool. Okay, so okay, yeah, so this is the result of adding the similarity loss. And we see that while it's not perfect, the left and the right are a whole lot closer now than they were before. Okay, let's see how our model does across other configurations. So on the left here, we show a StyleGAN model. It requires 144, I think this is a gigamax. So this is the amount of multiplies and additions. So it's a lot of computation. Now we can look at our any cost. Our any cost can provide cheaper results by decreasing the resolution or by decreasing the number of channels. So all these configurations end up giving you faster results with less computation. And in fact, you can actually try combinations of these, and here's a grid of 16 different configurations, all run with one single model. And we can actually go through and look at how many operations are in each model, and we see that we get something from moderate savings, for example, saving maybe 20% of the compute, to something very extreme. If you look at the bottom right, that only uses 5% of the compute. So this kind of gives you some space to traverse in between quality and compute. And the good thing here is that all these generations look reasonably close to each other. And in fact, I can show you this by traversing latent space, and we see consistencies all through the space, which is our desired property. Okay, how are we actually going to use this in practice? Well, here's a demo. Now recall, before it took about 4 or 5 seconds to get a result. Okay, so now we can reduce the channels, reduce resolution in the generator, and see what happens. Okay, so now things are a lot snappier. Our interaction is less than a second, so it's almost interactive, and the user can really ideate much better. And in fact, we can be even more aggressive and reduce the channels even more. And now we have something at a third of a second running on CPU on my MacBook. And this really allows the user to have time to play with a whole bunch of different sliders. You can change the young, old slider, remove some of the eyeglasses, and change the hair color. And once the user is kind of happy with their results, in the end, they can still run the full network when they're done ideating and get the full quality result. So they can run the fast generator during ideation and the full generator during idle time, and really get the best of both worlds in this case. Okay, so one thing we'd like to note is that there are preview modes in all sorts of different software, for example, rendering or video editing. And part of this work is to try to enable this as kind of a goal. Maybe all generative models should come with, a fast preview mode kind of built into it. The coded models are online if you'd like to play with it, as well as that demo that we just had a recording of. Okay, so in this previous work, we were strategically decreasing the resolution for cheaper computation. Of course, we're also interested in improving the high-end quality of our results. And one way of doing that is increasing resolution. Now, this is actually quite difficult to do beyond 1024. One aspect of this is it's the higher resolution you go, the less data you have available. And really, we took a step back and thought about why is that? Well, the reason that is actually our data construction processes are actually very wasteful. So if you go on the internet and just scrape a bunch of internet images, in the wild, you're going to see different images of different sizes and shapes. From here, we actually all do something very sad, which is we put it through a filter. So the small images, too small, we throw them out. Big images, we end up downsampling away. So here we're throwing away lower resolution images as well as higher frequency information. And so these are pixels that a downstream model never even gets an opportunity to touch or learn from. So we'd like to relax this constraint a bit and do something simpler. We'd like to come up with some sort of training scheme so that we can simply use any image that we want. And this here, we're going to call an any resolution data set. Okay, one such way of building such a data set is to leverage the work from other, previous researchers. So one way is you can take an existing LSUN data set. This contains over 100,000, well over 100,000 images, for example, of churches. And on top of that, we can go on Flickr and just find a relatively small number of high-res churches. In this case, it's about 6,000. So this is about, it's kind of like sprinkling on 5% more data in terms of image count. And all these images potentially offer value. We'd like to learn the structure, leverage the structure of the low-res images, as well as the details from the high-res images. Okay, so how are we going to come up with some sort of training scheme that's able to do this? Okay, so we explored this in this recent work that we put on arXiv. It's called Any Resolution Training, and the goal in the end of the day is to produce a very high quality, high resolution synthesized GAN or image. Okay, and the first author here is Lucy Chai, who is a really great intern working with us this past summer. For this, we started with the StyleGAN3 architecture. Part of that is because it offers something very useful. Not only does it, do you input the latent code, but you also actually input the coordinates of an image. So you can think of the top left of an image as 0, 0, the bottom right as 1, 1. Each of the pixels are a specific XY location on that image plane, and you can input a grid of pixels into the generator. And that's what StyleGAN3 does. Now, some simple modification that we can make that we realized was that you can actually increase the sampling rate in that image grid and put a denser coordinate grid into the generator. And you can then see if the generator outputs a higher resolution image for you. We also found it advantageous to directly inject the sampling or scale, or the sampling rate or the scale into the generator. Okay, so now we have the single generator that can potentially produce images of all different resolutions. This does lead to one problem. Because all of our pipelines and frameworks are for fixed resolution data sets, we're not going to be able to do batching, right? Usually you have fixed the same resolution image, you stack them in a batch, you get a nice 4D tensor, and you can start doing processing. But we can't do that if all the images come into different resolutions. So we need to find some way of batching multiple images of different sizes together. Okay, to do that, there's another additional trick that we can do, which is instead of inputting the XY coordinates of every single pixel in the image, we can just input the coordinates of a single patch. And because of the fully convolutional nature of the generator, you can then directly get just a single patch out. Okay? And that means that if you look on the left, we can actually query a different resolution image, but we can get the same size patch. Actually, this insight was also made in some concurrent work in this conference, so I recommend you check that out. Okay, if you look on the left here, we can also sample a slightly lower resolution image, but grab the same size patch, or we can even do that quite aggressively, an even lower resolution, but the same size patch, where we see more context. Okay, so through this operation, we can take advantage of the architecture of the network and batch same size patches that come from images of different scales. Okay, so from here, we're almost golden. We can query our generator for a bunch of high resolution patches. We can take our any resolution data set, perform cropping to do the same operation. And now we have a nice set of real patches, and we can put them through a discriminator as we do. Okay, so this scheme here is a patch-based training scheme that allows us to directly try to get high quality, high resolution patches. Now you may be thinking there could be a problem here. How do you maintain global consistency? How do you know that the head of the bird isn't going to appear where its feet are and vice versa? So for here, we found that a little bit of structured guidance from a low resolution generator helped. So we can write our previous objective out like this. We can have another generator that's trained on low resolution images. Okay. And that can, once again, you can leverage previous people's work. You can go on a model zoo and download a pre-trained model, for example, one that's at 256 by 256 on ELSA, or you can train your own. Okay, the question here is how do we compare a low resolution image to a high resolution patch? They're kind of different objects, but because we know the geometry, we can just take a crop from the image, we can downsample the high-res patch and put it through a similarity metric again. And there we get our final objective. Okay, so we have these two loss terms. One is aimed at high resolution quality. The other is aimed at getting structured guidance from low resolution, so kind of like scale consistency. And this lambda term actually ends up trading off between the two. Now in the previous project, we really didn't care a lot about consistency. In this project, we really cared much more about pushing the envelope on high resolution quality. That's really the primary priority here. And we'll show some examples of why that is. So we can show a comparison versus super resolution. So one way of getting potentially a high resolution GAN is you can take a low resolution GAN trained on ELSA at 256, for example, and put them through super resolution algorithms off the shelf. Okay, so we show a comparison to those compared to our method, which again has just about 5% of high-res data sprinkled in. Here we're going to be varying our scale parameter in order to zoom in to our network. Okay, so let's go ahead and do that. So we're going from 256 up to, I believe, 1600. So this is about a 5x zoom in, which is pretty extreme. Okay, so we see some interesting artifacts here. On the left, you see a lot of speckle patterns on the roof of this church. Why is that? Why is the GAN producing that? Well, if you look in the training set, they're actually processed by JPEGs, and these are very common JPEG artifacts. So if you look in the ELSA training set, you see speckle patterns on every single roof. And that's just a property of the data set that the GAN is now mimicking. As an aside, if you're producing your own data sets, please don't save it as JPEG, or at least have the decency to use a quality 95 instead of the default 75. Okay. But what happens here is that the super resolution algorithms are actually looking at this, and they have to decide, do we stick with this artifact or do we not? And so if you stick with the artifact, you end up just enhancing it, which maybe you don't want. Some super resolution algorithms do suppress it, but here it's not really getting the rooftops very well. And instead, we're getting a much more realistic high resolution rooftop here. Okay, so I like to explicitly say that we are not doing super resolution, even though the task looks similar. Unlike super resolution, we explicitly want to have a little bit of freedom in order to fix artifacts that we observe at low resolution. Okay, let me show you another type of artifact. So this is a generation, again, from an ELSA generator. Looks pretty good, but what is going on here? Why is there a ghost of a Shutterstock logo? Well, again, if you look in the training set, a ton of the images were scraped off stock imagery, and they have this, and the GAN's, of course, going to mimic it. Now, again, if we take our model and start increasing the resolution, the Shutterstock logo starts going away, and we start getting realistic brick patterns that look kind of nice. Okay, so qualitatively, we're seeing interesting high resolution results. How do we actually evaluate that? This actually takes a little bit of thought as well. So generative model evaluation is typically done with the FID metric. The way it works is you have real images, generated images, you put them through in a feature extractor, fit first and second moments, and then compare them in a probability distribution space. Okay, now that's all well and good, but there's actually one key detail here that's often overlooked, and that's actually that these images are all downsampled to 299 because the inception network was trained on ImageNet at 299. Now there's a few issues that arise here. One is that it turns out these downsampling functions and common libraries often don't follow signal processing principles, so they actually introduce artifacts themselves. And we actually explore this in a paper in these proceedings. So please come out, check out our poster if you'd like to hear more about it. But moving beyond that, for our specific application, this is actually not what we want. Like maybe we're okay with downsampling at 299 if we want to evaluate high resolution structure. That's a reasonable thing to do. But if we're at really high resolution, like 3K, by construction now, this metric is actually ignoring all the high resolution detail that we're actually trying to capture and evaluate. So this FID as constructed is explicitly not adequate for this task, for evaluating this task. It's also taking all our different sized images and forcing them the same resolution. Okay, so what are we going to do? Well, we found just a straightforward, simple modification, made it a much more appropriate metric, which is instead of downsampling, we take 299 by 299 crops. And this we call patch FID in our paper. Okay, so let's evaluate patch FID. Lower is better. We do this across a few data sets here, shown on the bottom. Here are some results with super resolution methods, and our method is able to get stronger results by the metric. Okay, from here, we train our exact same algorithm on a whole bunch of different data sets, and we'll explore some qualitative results here. So here's an input or an image of a bird generated at low scale. We can then vary the scale and increase from 256 up to 1100. And then we can actually do a latent walk as well here at low resolution, but we can do it at high res as well. Okay, can we go even higher? Well, here we take a mountain data set where the base resolution is at 1024. And here we're varying the scale. So we're zooming in here all the way up to 2800. And we can see some interesting details in terms of vegetation and dirt. Okay, here's another example. This one I like. It has some kind of interesting textures, I think, in the vegetation as well as in the water. Okay, here are some latent morphs, latent walks here in the mountains. Okay, and finally, we also trained a face model. So right now, 1024 model is kind of the highest resolution that we're looking at for FFHQ. We can specifically look at patterns in the hair and the eyes, and we can actually train our model, which is tuned on some higher res data, and we can go all the way up to 4096 here. So you see some sharpening in the hair and the eyes. Okay, and I'll do some latent walks here. So just the scale, this is our current 1024 models. Here's what 3072 looks like, 3 times as large. And we'll go ahead and do some latent walks. Okay. So here in this project, we're proposing a method to support data in its native size. And this actually allows us to efficiently increase the generation resolution well above 1024. You saw some generations at 3072, 4096. Okay, code and models are released as of about 9 p.m. last night. So you can go on our website and play with it. Okay, so in this talk, we discussed how we should design our algorithms in order to have some real world considerations. The real world has different diversities, the diversity of devices, diversity of resolutions, which we addressed in any cost and any resolution GANs. Now, we examine these issues specifically with GANs. But moving forward, these underlying issues are actually prevalent in all our different models. For example, if you're training autoencoders, flow-based models, diffusion models, autoregressive models. My hope is that in the future, we'll be thinking about how to enable full flexibility across all types of different generative models. Okay, here are the links again to these projects. These are like to acknowledge my collaborators, especially G and Lucy, who are the first authors of these papers and really great interns to work with in these remote internships. Okay, thank you very much.
We have time for one quick question. Come to the front if you have a question.
I have a question. I remember reading about like the anti-cost scan paper. I have a question. Like basically, I remember reading about like the anti-cost scan paper, and there's something that you guys mentioned. Like basically, if you adopt like the same multi-resolution strategy proposed by MSG again, that's actually going to lead to like worse results. But if you replace that with like your sampling strategy, that's actually going to increase the result. Do you have like any explanation for that?
Sure. Yeah, that's a great question. So yeah, there was a previous paper called MSG GAN where it took all the early exits and put them all through a discriminator. Somehow we found by sampling, it did a bit better empirically. I don't have great intuition as to why that is, but it's something we found. Another thing we found was that the discriminator is actually overwhelmed when you do all sorts of different random sampling through both resolution and through channels. So an additional detail in the paper is that the discriminator is actually explicitly conditioned on the generator architecture as well. And we found that that improved performance.
Okay, let's thank Richard again.
Okay, thank you.
Okay, our next speaker is Chitwan Saharia. He's a research engineer at Google Brain Toronto, working on diffusion-based image generative models. He's the first author of Imagen. Hi, please take it, Chitwan.
No, I'm not trying to Zoom right. Should I join it? Yeah, you should join it. I need to share my screen. Yeah.
This meeting is being recorded.
Sorry. Does it work?
The slice is not there. Can you share it?
Oops. Is everyone able to hear me? And the back as well? Okay, cool. So hi everyone, I'm Chitwan, and I'm going to be talking about our work on Imagen, which is text-to-image diffusion models. So this has been a work with an amazing team of people, and these are basically my co-authors, but I still want to thank hundreds of Googlers from responsible AI, from legal, people who read our paper and gave us feedbacks, people who generated samples. So this has been a joint effort of hundreds of people inside Google, and I just want to thank all of them.
It was slow.
So as all of us have seen in the last 2 decades, generative models have made huge progress, from generating endless digits to generating blurry faces to generating high fidelity images of simple objects. And our belief is that we are at an inflection point where it's becoming possible to generate meaningful high-fidelity content using AI. And our goal is to transform AI-based content creation using deep generative models. And Imagine is the first step towards this. So Imagine has been, we have learned a lot of lessons through our previous projects over the last 2 years. So starting with image super resolution via iterative refinement, where we use diffusion models to do 16x super resolution. Cascaded diffusion models, where we show that diffusion models can outperform GAN without any task-specific tuning. Palette, where we show that diffusion models can be used for several image-to-image translation tasks, such as in-painting, colorization, JPEG decompression, and uncropping, without any task-specific tuning again. And video diffusion models, where we show that diffusion models can be used to generate simple low-resolution videos. So I'm guessing that everyone is already aware what Imagine is, but to just summarize, Imagine is a text-to-image model that takes text, a natural grounded language text, as input and generates 1K by 1K pixels as output. And on the right, I just show a preview of our demo that we have internally for people, where you simply type text and it generally takes 20 seconds to get 8 outputs from the model. So some of the key properties that we want to highlight about Imagine. First of all, Imagine generates photos with unprecedented degree of photorealism. Imagine has a deep language understanding, and it's simple. It does not need a latent space. It does not need any quantization, and hence Imagine has much less parameters than any typical current text-to-image models. And I'm going to describe all of these things in a bit more detail further in the talk. So I'm just going to show some of the samples that they are just basically my favorite that have been generated by some of the amazing designers in Google. And I'll just briefly browse through them. So yeah, this one is my favorite. This basically shows how photorealistic the images are. For example, the sunlight on otter, zebra, mouse. First of all, it's a hybrid of 3 animals, by the way. So yeah, it in itself is amazing. Then yeah, this image is also one of the cool ones. Yeah, this also shows that how photorealistic the outputs are. This is also really cool. Yeah, these are just some funny ones. Yeah. Okay, so one important thing that I want to talk about before delving deeper into the model is that when we describe models like these, there are several key components of these models. And it's not just about the method. The characteristics of these models, whenever we talk about things like photorealism or deep language understanding, it may not necessarily just come from the method that the model is being used to train with. There are several other parameters that influence these characteristics of the model. For example, the data it has been trained on, the sampler. So one cool thing about diffusion models is that you can take the same model and completely change its characteristics by just altering the sampler. So the way you tune your sampler towards a particular objective has a lot of influence on what your model will turn out to be. And of course, the model size has a big influence. And it's not clear at this moment which part of these 4 blocks has what proportion of influence over the overall characteristic of the model. And it also becomes hard to compare between 2 different models because models are generally different along all 4 dimensions. So I'll give you a brief overview of what diffusion models is. So diffusion models can be considered as a combination of 2 processes. There's a destructive process that slowly maps data to noise. At each step, it adds small amount of Gaussian noise, and at the end, you end up with a random image. And you learn a model to sequentially remove this noise. And imagine that if you have such a model, you can start with random noise, and progressively remove these small amount of noise to end up with an image, natural looking image. So basically it's a mapping from random noise to data distribution. When we talk about these conditional diffusion models, for example, text to image model, in-painting model, or super resolution model, or whatnot, the only change that happens is that the reverse process is now conditioned on these things. So now when you are doing this denoising, with this additional conditioning signal, you are denoising towards specific kinds of images. You don't want any arbitrary image from the data distribution. So during training, you basically sample a random time step from 0 to capital T, and you train a denoising model, which takes this noisy image and learns to remove this noise while being conditioned on the amount of noise being added, which is basically denoted by T here. So yeah, as you can see, you basically sample different T's during training and you learn to denoise every time. And during inference, you start with random noise. You create an image which is supposed to be image from data distribution because that is what the model has been trained on, but it won't do a good job at the first step. So you add T-1 steps of noise back and do it again. And you keep doing it for T steps until you end up with a high fidelity image. Now, having talked about diffusion, I'm going to delve deeper into the key modeling components of Imagine. Again, to emphasize, these are not the only things that make Imagine what it is. It also depends on what data set you are training on. So the three components are cascaded diffusion models, classifier-free guidance and dynamic thresholding, and large language models as text encoders. So initially, I showed you that Imagine is basically a model where you put a natural language text and you get a 1K by 1K image output out of it. Now, if you look inside the model, what is happening is that this text is first being fed into a text encoder and you get a sequence of embeddings. And now you have three models. The first model takes the text and generates a 64 by 64 image. The second model takes the 64 by 64 image and the text and generates 256 by 256 image. And the third model upsamples it to 1K by 1K. So this three stack of model is what we call cascaded diffusion models. Now, it seems like a simple super resolution problem when you train these super resolution models, but it's actually not. During training, let's say you are training a 64 to 256 model, you will take a 256 by 256 image from the dataset, you will downsample that to 64 by 64, and you will train the model to go back to 256 by 256. But during inference, the 64 by 64 image that is being fed to the model is coming from a generative model. And the generative model is never perfect. It generates a lot of artifacts. And when these artifacts are present, there are high chances that the super resolution model will just break and just amplify those artifacts. So this train test mismatch is one of the fundamental problems when you create these cascades of diffusion models. So to deal with this, during training, we add varying amounts of Gaussian noise to the low resolution image. You can just imagine that you just also take the low resolution image and run it through the forward process of diffusion model for arbitrary number of time steps. And during inference, you sweep over the optimal amount of noise for a particular data set, and you can use whatever metric you want to optimize. For example, we use FID metric and we optimize the FID metric for whatever amount of optimal noise optimizes that. So this is basically what it looks like during inference. So let's say you get a text prompt and you pass it through a text encoder and you get a sequence of embeddings. Now you feed these embeddings to the base model and you get a 64 by 64 image. You upsample this 64 by 64 image, add some noise to it, pass it through the super resolution model and get a 256 image. And then you repeat this process again, upsample it, add noise to it, and run the super resolution model through it. So you can consider this process of adding noise as destroying artifacts while preserving the information that was present in the low resolution image. And it's not a super resolution model actually, because in super resolution, you care about being faithful to the low resolution input, but here we just care about generating high fidelity images. Now, when you train these super resolution models with these noisy inputs, you are weakening the conditioning signal that is being fed to these models. So to amplify this conditioning signal, we condition these super resolution models on text as well. And not only does it prove to be critical for the performance of these models, we also find some very interesting side effects of this process. So for example, here we take a 64 by 64 image generated by the model for the prompt, a photo of an astronaut riding a horse or a photo of a dog riding a bike. And now for the super resolution models, we change the prompts. So if we pass the same prompt, we get a high resolution quality photo of the same thing. But now if we just change it to an oil painting of an astronaut riding a horse, an oil painting of a dog riding a bike, we get the same image, but now it's an oil painting or an illustration. So this way, you can actually do style transfer on the images generated by the low resolution model. So this also shows how much conditioning, how much importance to the text is being given by the super resolution models. Now, the next important component is classifier guidance. So initially, I talked about this process where you feed the noisy image and train the model to generate the final output. I'll do a simple reparameterization to this and say that now the model predicts the residual noise that was added to the image. With the simple reparameterization, Jonathan Ho's paper of DDPM showed that this residual noise points in the same direction as the gradient of the log likelihood of the data distribution. So we were learning a denoising model, but it turns out that it actually estimates the score of the log likelihood of the data distribution. So when you're denoising, you're actually doing this gradient update on a noisy image to propagate it towards the data distribution. Now, once we realize that this gradient is a log likelihood of the data distribution, we can guide this gradient using either a classifier, which is called classifier guidance, or using an unconditional model, which is called classifier-free guidance. And in an intuitive way, higher the guidance weight basically means that the sampler is biased towards generating images faithful to the conditioning signal, in this case, the text prompt. So in practice, it looks simply like this. You train your diffusion models by dropping the text conditioning 10% of the time. And during inference, you do 2 forward passes to the same diffusion model with text and without text. And if W is your guidance weight, this is basically what the final epsilon prediction turns out to be. So larger guidance weights have always been correlated with better text alignment and worse image quality. So in this plot, we basically construct CLIP score versus FID score. So CLIP score captures the alignment between image and text, and FID score captures the fidelity of the image without paying attention to the text part. So ideally, you want good text alignment and good fidelity. So FID, the lower the FID, the better, and the higher the CLIP score, the better. And here in this plot, each dot represents a particular guidance weight. And as we go from left to right, the guidance weight increases. So as you can see, that when you increase the guidance weight, the CLIP score increases, but the FID shoots up. So you are improving text alignment, but you are compromising on fidelity. So if there is a way by which we can maintain the text alignment, but suppress this FID deterioration, it will be an optimal way to sample from these models. So, one of our hypotheses right now is that at high guidance weights, worse sample fidelity generally comes from the saturation of generated images due to very large gradient updates during sampling. So when you consider a high guidance weight sampling, it's basically gradient updates over the image. And these gradients are now really large because we are using large guidance weights. And the pixel values will hit the boundary, get clipped, and become saturated, and you can't do anything about it. So our very simple intuitive approach to deal with this is dynamic thresholding. It basically adjusts the pixel value in the generated image at each sampling step to be within a dynamic range. So if a pixel hits the boundary, we scale the image back so that the pixels are away from the boundary and get more chances to get updated. With this simple one-line change in the sampler of diffusion models, we see a drastic change in the sample quality. Here I'm showing 16 samples with a typical static thresholding used in the current diffusion models, using a guidance weight of 5. And as you can see, all of these images are highly saturated. Most of them have a lot of black pixels and lack amount of details. When we use dynamic thresholding, you can see that these images start looking more natural. They have much more details, while they maintain the same level of text alignment. In terms of these curves, As you can see, between static thresholding and dynamic thresholding, we are basically suppressing the gap. We are basically suppressing the FID scores while maintaining the text alignment. In a typical case, we generally use guidance weights of 30 compared to a guidance weight of 1.5 used in a typical diffusion model so far. And I think we can push it to a guidance weight of 1,000 if we can make it work somehow. Now, the third important component is the text encoder. So in a text-to-image model, you're feeding arbitrary text input, and you want a good text encoder to parse that in a way that the generative image model can use it to generate an image faithful to the text. So text encoder is definitely going to be important for your text-to-image model. So we basically explore two classes of text encoder, language models. We typically explore T5 and BERT, although they are much larger language models now. And we explore text encoders from image text models, for example, CLIP. So CLIP has image tower and a text tower. So basically take the text tower from these models. And when we talk about T5, we also just take the encoder. So a typical size of T5 XXL is 11 billion parameters, but we are only using 4 billion parameters out of it. And for simplicity, we freeze these text encoders. So this basically allows us to compute all the embeddings offline and not worry about fitting it in the memory during training of the diffusion models. So I'll just give a brief summary of one of the main results that we observed, and you can look into the paper for exact quantitative numbers for these. So we found that scaling text encoder size is extremely effective. The bigger the text encoder, the better performance you get. Scaling the size of the text encoder is actually more important than scaling the size of the unit model used for image generation. So we found that as we go from 300 million parameter to 2 billion parameter for a unit, the improvement is there, but not as big as going from 300 million parameter encoder, text encoder, to a 2 billion parameter text encoder. And when we compare these two classes of language encoders, text encoders, we find that human raters prefer T5XXL over CLIP on our benchmark, which we call drawbench, which I'm going to describe a little bit in detail. In terms of the standard comparison, Imagine achieves a state-of-the-art FID, which is also better than the FIDs obtained by the models that actually train on MS-COCO training set. But MS-COCO dataset, which we typically use for evaluating these text-to-image models, has its own disadvantages. It's too simple, it has limited vocabulary, and it was a dataset made for image-to-text evaluation, not for text-to-image. So in order to evaluate these new classes of text-to-image models, which are really good at what they do, we introduced drawbench, which introduces a new set of prompts to evaluate these text-to-image models across multiple dimensions. So we have a set of 200 prompts. We keep the number of prompts small so that we can use human evaluation for this. And we divide it into 11 categories. For example, colors, to just see how good the model is to assign a color to a particular object. Counting, conflicting. So for example, a horse riding the astronaut instead of an astronaut riding a horse. We take some prompts from the original Dolly paper. We have some descriptions. So for example, if you say, describe an object, if you describe an object in the prompt, the model should be able to actually create that object in the image. We take some prompts from Gary Marcus. We have some misspellings to see how robust the model is. We check some positional capabilities of the model, putting objects from the left or right of each other. We check some rare words. We take challenging prompts from Reddit because people are really creative there. And we check text generation. And for all of this thing, we do a side-by-side human evaluation. So here are some of the sample prompts from drawbench, and here are some of the corresponding images that we generate from Imagine. So when we are evaluating on drawbench, we are evaluating again on fidelity as well as image text alignment. And here the things are simpler because we just show them two sets of images and ask which set of images is more photorealistic or which set of images better described by the text. When we compare Imagine with the current state-of-the-art methods such as Dolly 2, Glide, PQGAN plus CLIP, and latent diffusion, we find that the human raters generally prefer Imagine over other methods in context of both text alignment as well as image fidelity. And here are some of the pairwise comparisons between Imagine and Dolly 2. So for example, when we say a panda making latte art, Imagine is able to actually make a panda make latte art, but Dolly to, so I think this is something that was also described by Aditya, that it has an issue with the variable binding attributes. And this is basically what gets reflected here. Similarly, if you say a yellow book and a red vase, Dolly 2 almost always makes a yellow vase and a red book, while Imagine most of the times gets it. Similarly, this is one of the prompts that Imagine and Dolly 2 both fail at. It's also like a conflicting prompt because it's like a cow attracting aliens instead of an alien attracting cow. Now, of course, there are some limitations with Imagine. It was trained on problematic data such as Lion dataset, which contains explicit content and harmful social stereotypes. And it relies on pre-trained T5XXL model, which come with their own social biases. And we have found in our limited experiments that Imagine is definitely biased. And this is one of the reasons we have not released the demo publicly at this point. Thank you for listening. And if you have questions, please feel free to ask.
Yes.
Jane, any questions online?
Okay. Okay.
Thanks.
Hi. I know you explained it a bit, but could you just go into a little more? I think everyone's noticed that the significant thing Imogen does better than Dolly 2 is like understanding more precisely the semantic meaning of like the relationship between objects. I wonder if you could just explain a bit more why you think that is.
Sure. So one of the reasons that we say that Imagine is able to exhibit a deeper language understanding, which is basically what we mean when we say all these things about semantic understanding and whatnot. I feel that most of it comes from the language model. So a language model, when trained on a language modeling objective or a mass language modeling objective, has seen much, much more text data than a clip model that has been trained on paired image text data. So when you see more data, you are able to generalize more and you are able to parse long, complex prompts more. One of the assumptions we make is that in text to image, the text prompts are going to be very simple, but it's generally not the case. People get very creative very soon and they make the prompts much more complex. And I think that using a very, very deep language model, it comes handy in those cases.
I also have a question. So in training Imagine, you must have used a lot of data and a lot of computations. And collecting a significant amount of data is not a trivial thing. So, and there must have been noisy data. So what was the principle in collecting data and how did you, and what was the observation you found?
So I think data is a very big problem when we are training these models. One of the recent public data sets, such as Lion 5 billion, is one of the good examples of data set that should be used by future text-to-image models. Of course, there is some filtering that needs to be done on that. But in general, I think quality is definitely one of the issues. One of the ways is actually to filter out images of low quality. So one of the things that we do is that the base model is only 64 by 64. So even if you have low resolution images, you just train the base model on that because it's just 64 by 64. And now you have modeled the low level frequency details of the image. And when you're doing super resolution, you can afford filtering out the images because now you are learning a very simpler task. So as you go bigger in the super resolution, you can filter out more and more images to maximize the quality.
Few more questions.
So in Imagine, is the text being conditioned the same way as that in Glide, or is there a better way of conditioning text information because diffusion objective doesn't exactly incorporate it being in being there in the inference time?
Yeah. So text conditioning is very important in these models, as we found, and we have an ablation of different methods of text conditioning. So we basically found that for the base model, we use text cross-attention, which is kind of similar to what Glide does. One thing that we do differently is that even for the 256 to 1K by 1K model, we found that if you don't condition on text versus if you condition on text, the results are very different. So let's say you have a fish in an image and you upsample that fish. it will be a plain fish. But if you actually condition on the prompt that says fish, then it actually produces the scales of the fish. So for super resolution models, we feel that conditioning on text is really important. But in all these models, we are just using text cross attention.
I just wanted to ask if you think that there will be something similar to those super powerful text-to-image models using any other language than English, because all of them are like in English, and I don't know if there's like an intrinsic problem in doing it in any other language, or if it is just that English is the most common language. Thank you.
So yeah, I think this is one of the future research that we are considering. Again, Lion 5 billion has 2 billion images from different languages than English, so that can come in handy there. I think it's not just as a simple problem of taking a text, translating it into English and feeding it into the model, because there are several cultural aspects that are preserved in the text that can be lost in translation. So definitely, yeah, I think you need to specifically train the model on different languages. And I think it's possible with the Lion 5 billion data set, for example.
Okay, last question. Hi. So you talk about the language model. So how about the diffusion model? How much really depends on the diffusion model? The question is, can you actually produce similar impressive results with an autoregressive transformer model instead of a diffusion model? Yeah.
So I think it's an important problem to consider. I think diffusion models are doing great so far because they don't require any specific tuning. But there is no reason to believe that either autoregressive models or GAN models will not be able to do the same thing. I think it's just about trying it. And hopefully we see more results with different classes of models with the same quality. Yep.
Okay, let's thank Jujuan again. Okay, just before we leave this room, just a reminder that the second poster session will now start. There are prizes for the best poster for both the physical and the virtual session. That will be outside Hall D on the way to where you get your lunch. With that, this room will now close. Thank you all very much for participating. We hope to see you again next year at CVPR 2023. Thank you, everybody. Okay. Yeah. You're such a good.
Congratulations. I just want to say hi real quick.
Oh, cool. That's okay. It took me like 3 months to replace your email. So you get at least 3 months to reply back to me. Yeah, I know. I enjoyed it. So, take time. I kind of enjoyed it.
Imagine, and now I know.
Yeah.
Cool. That's good, yeah.
These waters are personalized. Oh, great. And speakers. I will skip. Well, thanks. I'm gonna take my stuff.
Hey, Cynthia, hi. Nice to personally meet you. Yeah. About dinner, what exactly is the plan?
I made the reservation for 6:45. 6:45. Right. It's a little bit of work.
It's under your name, right? You get the
Under my name. My legal name.
Oh, do you want to look?
Yeah, if you want. Thank you very
Okay, good. Fine.
That's at the beginning of the book. But, well, but this bit is not space.
Okay. So you got my email. Yes, maybe it would be good to get just the phone number, maybe